Tak jsem slyšet, ja. Okay, so, hello. Okay. So, hello. Welcome to the Cauldron. I'm very happy you all came, and I hope we will survive the event, especially I will survive it. It's organized again at the Charles University by our two departments, EUC and CAM. So I would like to introduce Professor Neshetřil, and he will say us a couple of words.
Thank you, Honza. So it's my great pleasure to welcome you in Prague, to rainy Prague. I mean, you selected 3 days of the heavy rain, and maybe you will see the Moldau, Vltava, full of water. You know, hopefully there will be no flood. I mean, and we had a heavy flood 20 years ago. I mean, it didn't infect this building, but almost it infected this building. It was really very high. And this meeting is organized traditionally. I think it is third installment or four? I think four, yeah. Fourth installment of the Cauldron in Prague. And I mean, I will not thank to the main organizer, but I think there will be another opportunity still during these days. But it's very nice that you are here. You are actually in one of the oldest buildings of the Charles University. And this is a little paradox that the youngest discipline, which is computer science, is located in the oldest building. We are very happy here. Actually, we somehow put some effort to be located here, and so this is how it is. Yeah. So I hope that you will have a good time and that it will be a fruitful meeting. And again, welcome in the name of this our departments and the Faculty of Mathematics and Physics of Charles University. Welcome. Thank you.
Thank you. So I have just a couple of remarks. So first, I would like to thank to our sponsors. You know, things have increased in price since the COVID time, and without them, we cannot make it so nice as we have it. And we have the organizers. Some of us are here, so if something goes wrong, probably you could speak with me, and I will try to fix it. We have several volunteers which will help with the setup of the rooms, and they will check that everything goes correctly, and I will try to arrange chairs for every track, so we stay in time, because we have extremely busy schedule. The schedule is subject of change. We have the first change today afternoon. The RISC-V BOF is moving early, and because we are resolving conflict, and we are replacing, I forgot, which is the talk which is moving late.
The RISC-V BOF moves to 3:30, and the integrating librsec into the GNU library moves to Sunday at 10. The live talk schedule's been updated, the PDF's been updated, and we're going to walk around and scratch it out on the printouts or get new printouts.
Yeah, thank you. And we are going to have even more changes, especially the steering committee QA will be moved earlier on Monday because Jason is leaving and he will not be able to answer any questions otherwise. So this is for organization committee. We have also a code of conduct. So in case something goes wrong, you can contact these people. There's a Jason and Maxim, and no, not here, Carlos, and yeah, so so I guess, yeah, at the moment Carlos is the contact person for yeah, okay, so so we have at least 2 persons here. And as you know, we are having some floods. I have checked that GNU is good in swimming, so that's how we will manage to have the dinner, which is in the lowest position of the Prague, because all the wastewater goes down. And we will have a dinner in the sewers. No, we will have up on the sewers. So one thing is that the venue is relatively far. It's 1 hour walk. So we will try to organize public transport there in some groups. You can walk if the weather allows. This path which goes around the Prague Castle is significantly nicer than the default path which Google suggests. So I would suggest to go by this way. And I guess that's everything for introductions. We have 2 tracks starting. The 3rd track is starting later. We have this room, the room which is upstairs, just above our heads. And the 3rd room is smaller and it's just behind my back. So I hope you will enjoy, and I should let you some time to move to the other room in case you go to the other track. So thank you very much.
Testing, testing. 1, 2. Please don't put... This, I think, is working. And maybe this will... I should plug in as well.
So maybe if I'm sharing, I can introduce you. And
yeah, if I can...
Okay, so it's my pleasure to introduce the first talk, which is by David Malcolm about diagnostics in GCC 15. So I hope we will see some ASCII art as well, right? Okay, thank you. And also, please speak to microphone if you have questions.
Oh, yeah. Maybe have that ready to pass out, I guess. All right. Good morning, everybody. I'm David Malcolm. I work at Red Hat on GCC, focusing on diagnostics, which is what this talk is about. I'm going to be talking about user experience improvements I've been making for GCC 15 in terms of nicer looking text output. I'm going to talk about Serif output, which is a machine readable format for diagnostics. Various internal improvements I've made that make it easier for developers of GCC to write new warnings, which might be of interest if you're a GCC developer or work on GCC plugins. I've been working on taking all this diagnostic code and making it available to other projects as a shared library using called libdiagnostics, so that people don't have to reinvent the wheel. And I'll also talk about some of the more out there or experimental things that may or may not land for GCC 15. So the first thing I talk about is I took a look at how GCC's terminal output, the color scheme. So forgive me if this is a bit of a bike shedding discussion. So looking at GCC 14 and earlier, here's a couple of screenshots from Compiler Explorer. I've got URLs on all the slides, which are not yet available, I'm afraid, but I'll upload them after the talk. And so here at the top we have a warning about a mismatch in a format string where you've passed in %i and you're passing a const char star, but asking a %i to consume it, which is wrong. And here there's a type def. So two type defs that are being added together, and they're structs, and the C compiler doesn't know how to handle that, so that's a type error. And the coloring here is a bit random and haphazard. It happens that there is a color chosen for the severity. So the top one, it uses purple for the severity of warning, and the other one, it uses red for the severity error. And it happens to use, for the first range in the source code, it uses the severity, and then it sort of alternates between green and dark blue for other labeled ranges in a diagnostic, which is a choice, I suppose. Well, it's not really, it sort of happened. And so for GCC 15, I thought, well, what should these things look like? Is there a better way of doing it? And so what I've done is I've thought a lot of the time with a diagnostic, you have two different things that you're trying to draw a contrast between. So for example, in the top warning, you have, well, it's a type mismatch. So you have, what is the type that you were expecting versus what is the type that you got? And it's sort of the expected type versus the actual type. And here I have, you'll notice that previously, the message of the warning, where it's saying format %i expects argument of type int, but argument blah, 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 blah. I've now got color in there, so the format %i is colored green, expects argument of type int star, which is also colored green. And you'll see that in the quoted source, the bit that corresponds to the %i is also colored green, whereas argument 2 has type const char star the const char star is in dark blue, as is the part that is corresponds to that in the source code. So the idea being there are two different things here that we can use color to group and contrast between, so that the eye is drawn to, oh, that's the sort of intness part of the problem, and that's the const char star part of the problem. And it sort of also highlights the relationship between the message and the source code and the parts within the source code that are of those properties. And again, and going on to the bad binary operation, again, the two things that I'm highlighting here are the left-hand side and the right-hand side of the infix plus operation. And so you'll see that we have an S, which happens to be a type def, and you see the S and the thing that it's a type def of are highlighted in green, as is the left-hand side. And similarly, and T and struct T, those things get the dark blue colorization. So I think this is a nice, maybe it's subtle, but it's a nice way of sort of grouping and contrasting in our messages. From an implementation point of view, there's a new, in the GCC subdirectory, diagnostic highlight colors.h, and we have, there's a basically highlight, there's sort of symbolic names to avoid you having to sort of spell out what you mean. So in one of these type mismatches, inside the implementation, we can talk about highlight colors, : expected versus highlight colors actual, and it's very clear what you mean inside the implementation. Similarly, left-hand side and right-hand side. And I implemented this and ran into a problem, which is that it was implementable using GCC's existing internal API, but it was horrible because you had, the messages were like a dense mass of % this, % that, and that, and lots and lots of arguments, and you're trying to figure out which one corresponds to what, and so on. So we sort of ran into, well, I want to be able to, in my formatted printing, be able to say, this isn't just a type that I want in quote marks, this is a expected type that I want in quote marks, and this is an actual type that I want in quote marks. So I sort of want the idea to be able to carry more, maybe semantic information about things. And so traditionally, well, we can add a new format code to the pretty print format thing inside GCC, but we're running out of letters for percent whatever. It's basically, I had to kind of trawl through all the different front ends, which have their own, there's sort of a base level of format codes, and then there's front end specific ones that consume other ones. And so then, if you do add a new format code to our pretty printing routines, you have to teach -w format about it so that it knows how to type check it. And finally, just the formatting code is increasingly convoluted, and I talk about that later in this talk, how I've simplified that. What I came up with was the sort of the one format code to rule them all, which is %e, which is an element, and basically it consumes a pp element star for vararg, which is actually a pp markup in the namespace element star through a type def. And the idea is the element inside pp markup is an abstract base class that has virtual functions for interacting. Well, it has a single one, which is add to phase 2, and it takes a markup context. And the idea is there are operations inside context for interacting with the formatting subsystem, saying, this is how I print myself when we're doing a formatted string print, for example, inside a diagnostic. And so it sort of isolates it in one place. And yeah, this is rather wordy because my variable names are rather long and I've got namespaces. But here's an example of this is a note inside the C front end where you have a type mismatch where you're complaining about I've got a function call and a particular parameter is of a type that conflicts with the argument at the call site, say argument 2 is wrong for parameter 2 of the declaration of the function being called. And so we make our location, and you'll see that at the particular location we're complaining about, which is the location of the parameter itself in the declaration. And you'll see I've added a highlight colors expected, saying that I want to highlight, when I quote the source, I want to highlight highlight that using that color scheme. And then I'm going to, if you look at the bottom, there's an inform expected %e, but argument is of type %e, and I'm passing in a pair of element stars, which I construct in the lines above. And the nice thing here is these are C++ objects, so it's type safe in the sense that a element expected type is constructed with a tree that has to be a type. And all that the nasty, not particularly type-safe format string consumption code has is, well, it just has to be a pp element star, and it'll call the virtual function. So that's all kind of covered, and you have a quite nice way of just any time you want to add a new formatable thing that has to interact with the formatting subsystem, you can just do it this way, and it makes it very easy to inject. We'll print this as a type, but we'll colorize one of them using the expected colorization, and the other one is the actual colorization. And so in terms of what this looks like, this was the GCC 14 version of this. And yeah, the thing that it's the note as part of this, the expected const char star, but argument is of type int. And it's highlighting the param of the decal of the thing being called. And in GCC 15, you'll see that, yeah, it's highlighting things. One interesting thing about this example is you'll see that the colorization can be done at the level of the group of messages. So you'll see that in the quoted source and part of the error, the type of the argument at the call site is colored in dark blue and highlighted int. Whereas the param there is highlighted in green to mark the expected. But you'll see those of type int, that's in blue, so that matches visually the the quoted source from the error. So within any particular group of messages, you can establish a consistent colorization to sort of visually group the related concepts. So I went through the C and C++ front ends for basically things like type mismatches, bad binary operations, and things like that. And I gone and implemented this for GCC 15 for the C and C++. If you are the maintainer of a GCC front end and would like to implement this sort of thing in your warnings, talk to me if you like, or please implement this and I can help. So that's the colorization improvements. Next, I've been making some improvements to how you wanted ASCII art, you're going to get ASCII art. Okay. Well, actually, box drawing characters, which are Unicode. Since GCC 10, any diagnostic can have a diagnostic path associated with it, which is a list of events describing an execution path through the code, possibly interprocedural. And here's an example of a warning from the analyzer. It's warning about a double free, a very, very trivial one, and how we would print it in GCC 14. And you'll notice there's this kind of weird blue line, or cyan line, on the left-hand side, a border. What that is to try and show the interprocedural calls and returns, like what is the stack depth? We're calling into this frame and we're returning from it. But it's completely redundant here because this is purely intraprocedural. And so for GCC 15, for purely intraprocedural paths, I eliminate them. So it makes the warning that much tighter. You'll notice on the event 2 in the path, you'll notice it's gained a little warning emoji, and before you all scream, yes, it's disableable, and if you're in ASCII only, you can turn off emojis. And that highlights, but basically there's a flag on events to say if they're flagged as danger, they will get a warning emoji, and that makes it through into the machine-readable output. There's a property in Serif you can add nouns and verbs to events, and the analyzer happens to set that typically on the final event in an execution path. Here's one of those interprocedural things I mentioned before with calls and returns, and there's can you spot the difference between GCC 14 and 15? Is it better with or without? And basically the difference is if you look at the bottom, maybe at the bottom here, this is pure ASCII, and now it uses box drawing characters. And of course, you can turn that off and go back to just using ASCII. There's options for all of this.
How do you turn these things off? Is it only on command line?
There is a command. Okay, the question, how do you turn off these things and control these things? There is a -f diagnostics text art charset equals that can be ASCII, Unicode, or emoji, which is basically, this I added in GCC 14, and I think it defaults to emoji. ASCII is pure ASCII, Unicode is use ASCII plus some box drawing characters, and emoji is add the warning emoji. I'm not adding all the full,
Shouldn't this come from the environment?
Yes, and the default is affected by the environment as well. I refer you to the source file, gcc-, I think it's in diagnosticcolors.cc, because it's similar to how we scrape the capabilities of the terminal if we're connected to a terminal for whether we should enable colorization for control codes. So more ASCII art here. So GCC 14 gained analyzer infinite loop warning for detecting some kinds of infinite loop. And this shows, and it might, basically you have to look at the numbers and figure out what the control flow is. So you get event 1, then event 2, then event 3 down there, then event 4, then event 5. And this can be increasingly difficult when you have more and more complicated execution paths. So for GCC 15, I've added the ability to show control flow edges in the paths. I'm not convinced that on this example it's an improvement in usability, but here you see event 1, and that's actually got the emoji because that seemed the best place to put the warning thing. Infinite loop, when you go here and we follow this control flow into the loop, and essentially I try and consolidate events into sanely printable runs of source code that we can show edges between. And what we have here is a looping back, so you can sort of see it from the line numbers go back. So I'm not convinced this is the best example I should have chosen for this, but it at least shows the capabilities that I've added for visualizing control flow edges in the ASCII art. Well, it will be ASCII. In this case, it happens to be box drawing characters because that's what Compiler Explorer supports. Okay, in GCC 14, well, there's been a recent development to terminal control codes where it allows you to, as well as colorization, express URLs and provide links in the terminal. And we added that for the warning when it says -w whatever, that becomes a clickable hyperlink to the documentation. And that's been in GCC for a number of releases now. In GCC 14, I extended that so that anytime you mention a command line option in quotes, using like, for example, the %QS format string inside one of those, error at or warning at, there's basically a hook, a URLifier, that looks at these and says, do I know about this thing? If so, I'll make a URL for it and just automatically inject it. So for GCC 14, almost any, because sometimes there isn't a good URL to use, but anytime you mention a command line option or anytime a command line option is mentioned in a GCC diagnostic, it will give you a hyperlink to in the terminal to the documentation of that warning. Now, internally, we have to basically scrape. There's a Python script that scrapes the result of building the HTML documentation, and then generates lots of .top.url files, if I remember right, and I didn't want to put a dependency on make HTML really, really early in the build for something that only is needed for the rare times when you're adding a new option or documenting an option that you should have documented. And so there's a manual step, make regenerate opt-URLs, and there's continuous integration that will complain if you, thanks Mark, that will complain if you forget to do this. But it will send you the patch as well. Well, it's fairly trivial to fix, but it might be annoying, I don't know. So for GCC 15, I've got a patch that basically, which is proposed, which sort of does the same, but it extends it as well as command line options, it's compiler attributes. So here we have a warning about attribute access, read, write, 2, 3, blah, 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 blah. And you'll see that now not only is the well, it's probably not very legible, it's the -w attributes URLified to a link to that warning. It's not a particularly necessarily useful warning, because what you really want is the documentation about attribute access, which is now, as a URL to the docs about that attribute, or at least if we apply this patch, which I think is a nice usability win, because that's what you kind of really want to know about when you're in this situation. So I've got a patch. It adds another manual step that anytime you add a new attribute, you have to regenerate this data file that has, here are the URLs, or the relative URLs within our generated documentation. And so that would be another step for GCC maintainers who are adding new attributes to do. And it would be also, they're not unique. For example, there are I think the record is 19. There are 19 different URLs in our documentation for attribute interrupt, because there's lots and lots of different target-specific versions of the documentation for interrupt, because I think there may be, Jason.
And also attributes that apply to types and functions and variables.
That as well. I totally forgot about that. So you have, I don't have a plan for how to fix that. What I was going to suggest is I can add a new target hook where you can query the target, and the target will say, this is my documentation versus, you know, AArch64's versus x86, whatever's. But yeah, I need that I need to think about. So that's sort of discussed the sort of the user-facing sort of the textual output improvements that are mostly, apart from that last one, already in trunk for GCC 15. For as of GCC 13 onwards, we've also gained the ability to emit diagnostics in a machine-readable format called SARIF, which is the Static Analysis Results Interchange format that is an industry standard. It's JSON-based format designed for the output from static analyzers and to be able to capture fairly rich data about, for example, things like what the execution path that's predicted is, potentially even multi-threaded execution paths are expressible, and yeah, you can do all kinds of fun things like say, in this self-extracting exe file, there is a zip file, and inside that zip file, there's this file, and inside here, there's an ELF file, and inside this ELF section is a virus, and report things like that. So it's got some pretty rich vocabulary for describing things you might want to talk about in a static analyzer. But also, in fact, just in general, for SARIF 3, I was going to say, actually, we hope to, I'm on the SARIF Standard Committee, although I haven't only been there for about a year. The plan is to change it from being the static analysis results in interchange format to the, we had a total bike shed discussion on, it'll be the system analysis result interchange format, because so that we can handle things like dynamic testing, fuzz testing, and so on. So potentially, say the output from Valgrind could be, you could use SARIF, but there are some issues we need to resolve with that. Because we've already got a pretty rich vocabulary for expressing things about source code and things about binary artifacts and all of that. So yeah, I added support to GCC 13 for outputting diagnostics in SARIF form, and I've been making various improvements since. For GCC 15, I've done a lot of work on the SARIF output code. There's lots of new metadata. So, for example, it captures the command line argument when the invocation of CC1 started and finished with timestamps, what's your working directory. There are things like those sort of labeled ranges of source code that you would have seen on the slides before. That's now captured in the diagnostics in the SARIF output. GCC will emit things like in file foo.h included from here in file bar.h. There's a problem, and you'll see that in the textual output. That's now captured in the SARIF output as well, the sorts of chains of includes that lead to a particular point in the source code. I've added support for URLs in messages, similar to what you saw on the terminal text-based output. And internally, lots of improvements. I added basically to make, I've added, the tests now check that the output is valid according to the SARIF schema, which I wasn't doing before. And to do that, I actually added a class hierarchy rather than just having a big blob of JSON values. And I'm using unique pointer now to avoid memory leaks, because there were, so lots of internal improvements. I got most I have a partly written patches for, I mentioned capturing chains of include paths associated with the diagnostic to get to a location. GCC can do things in macro foo, and it has macro, these sort of chains of macro expansions, and potentially, as I say, I have a work in progress patch that covers that, and that may or may not land for GCC 15. And similarly, GCC can capture for warnings that are coming from the middle end that this is this function, when it was inlined into this function, when it was inlined into that function, I can detect that there's a buffer overflow problem there, and we could capture that as well. But that's not done, but is hopefully close to doable. Talking about internal improvements to GCC. So this is much more just for GCC developers and for authors of GCC plugins. In my talk at Cauldron last year, I talked about this new subsystem I added called the text art, which is how basically all about doing those ASCII art diagrams or box drawing diagrams. And for GCC 15, I've added a new tree widget class that makes it very, very easy to add to visualize hierarchical structures in a dump. Basically, if you have a type that has a make dump widget member function of suitable signature, there's a text art dump template or a family of templates for dumping to standard error, dumping to a pretty printer, and dumping to a file star. And so for example, inside the analyzer, here's one of the visualizations I've added. This is visualizing a region model, which is the analyzer's, here's a state that the analyzer has along a particular execution path. And it has a lot of it's built up from a lot of sort of objects. There's the store, which is its simulation of what the contents of memory is, and there's constraints. There's a constraint manager which captures here, and we know that, for example, this doesn't equal that on this path. And so it's basically the tree widget thing is a very easy way of just, give me a colorized visualization of showing that hierarchical structure. And of course, for free, it'll also do ASCII and non-colorized and all the combinations of those, depending upon whether, what the status of standard error is and the command line options we mentioned before. The other visualization I added to the analyzer, that was sort of showing the state of the simulation along a path. And we have, for example, that in frame 51, variable _6 is that symbolic value, initial value star in it. And here's a visualization showing how that symbolic value is built up. It's the initial value of a region, which is the initial value of that pointer valued variable within this frame on the stack. And again, so that's I find this very useful because, you've got these complicated tree-like structures that you want to see where the problem is. And again, with the colorized box drawing and those. So, I'm sorry, Siddhesh.
Does this work on tree as well?
Send patches. So Siddhesh's question was, does this work on tree as well, which is the sort of very important data type inside GCC. And I have not implemented that, but it would be a very useful patch, no doubt. So if someone wants to, I can help with that. Continuing to talk about GCC internals, I've been looking at the insides of the pretty printing formatting routine. So I showed you one of these already. There was like that inform, like expected %QS, but got, or %QE, but got blah, blah, blah. So these are used throughout how we implement warnings and and errors. And you can just directly call PP format. So here's an example. We'll send an int, a string, and a string in quotes with these parameters and try and print this to a pretty printer. Previously, this was done just diving a bit into the implementation. We had various text buffers, and it would basically say, oh, you've got foo : space, and then you've got %i, so there's that run of text. Then we've got an I for %i, it's going to consume that parameter, and so on. So it would chop up the format string into sort of data and control, as it were, sections. And that's sort of phase one of the formatting. And then in phase two, it would take, say, the %i and the vararg and sort of consume the vararg and make a string for it. And for example, for the %QS, the quoted string, it would take the string and then add quotes, but potentially also SGR control codes saying color this in bold on the terminal. Okay, turn bold off at the end. And potentially inject the URL that I was showing you on those earlier slides, and there's control codes for that. So previously, all of this logic was just all working in terms of char stars and text buffers, and I was running into problems with that because you have these text buffers, and all they are text. And there are some control codes that are awkward. So the C++ front end, for example, has %h and %i for contrasting two different types. And so that we can, for example, if they are templates that are almost but not quite the same, we can highlight the differences between those template types. And to print those, you have to sort of defer printing them until you've seen both of them. Which is awkward. We have the ability to dump optimization records in JSON form to say recording like decisions about inlining or decisions made by the vectorizer. And it has its own, I think, %C for a call graph node, %G for a statement in the Gimple representation. And then I have this logic to automatically inject URLs, and that was getting really, really messy. And finally, yeah, we have these terminal colorization and URL codes, but that's sort of all we have. And so supporting Serif has some fairly rich things you can do in terms of marking up the text. And there are other formats. We could docbook support anyone? I'm not sure. And basically, you can't really support if all you've got is text and control codes. So for GCC 15, this is in Shrunk. I've added, there's a new header, pretty print format impl.h. There's a new mini internal representation, pretty printer tokens and pretty printer token lists. So what we do here in phase one, rather than having just text buffers, we now have token lists. And it looks very similar, this slide, to what we had before. We have a list containing one text token, basically in each phase. Where it gets interesting is in phase two, where we substitute, because now we have all these token lists containing text tokens. But the final one, we've captured that there's a begin quote, then the text, then the end quote. So we've sort of captured the meaning of what we're doing at a sort of a slightly higher level. And the advantage of this is, and then we can do all this, okay, we've got all these, we now put them all into one token list, and then we can do things like merging the consecutive tokens, and all that sort of logic can be done in one set of shared utility functions. And then what this achieves is a sort of a separation of concerns, because we have all the different front ends and also the dump subsystem have their own sort of little mini language of what are the format codes. I mean, there's the shared ones like strings and ints, but the front ends add things like types and expressions, and the dump subsystem adds things like call graph nodes and statements. So you have these sort of client-specific format codes. And so the front end sort of has this sort of format decoder. And what we have, by having these tokens, the idea is that the front end's format decoder is responsible for understanding its format DSL, domain-specific language. It's a little version of the format language. And generating these tokens. We have some shared logic for example, if you spot begin quote, text, end quote, the auto-URLifying logic got a lot simpler because I can just do that in one place rather than, there used to be lots of really awkward cases of, look at this, capture this char star, and then capture this char star, and if they're in the same buffer, compare the, so that became, and then finally, there are multiple different output formats. You could be doing pure text, or you could be doing text to a terminal that understands these control codes, or you could be doing to a machine-readable format like Serif, which has its own how you express these different concepts. And so, here's a double free warning, or the implementation of the analyzer's double free, where it has a describe final event virtual function implementation. And if you know what the first free was, you can say, oh, the second free, or whatever function, the quote function here was here, is here. The first free was at, and %at is references another event in the execution path. Hopefully that's fairly obvious, like it takes in 2 function names and an event ID. And after so we do the formatting and we have the second quoted free, begin quote, free, end quote, is here. The first one is there. You'll see that was at, and we actually got a special token type for event IDs. So we've captured at a higher level that we're talking about an event. Rather than having to sort of figure out, well, what does the text look like? And and so we then can get them all into one list, and you've got that. And then, so if we're outputting the text, we can, and here's text with formatting codes, and it will output it this way. But, and here's the fancy thing, if you're outputting to Serif, you'll see message, text, second free here, first free was at, and there's this long thing, because Serif has a way of embedding URLs, whatever, into, and so this is you'll see that the second free was that the text of it is 2, and the URL is serif:/ blah, 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 blah. That's a JSON pointer to within the Serif file itself. Saying, so you can actually reference, within this event's message is referencing another node within the Serif tree. So, so a consumer of this can say, so it's this location, this free is here, that free is there, and they can refer to each other. So the consumer of the Serif, for example, if you're generating HTML, you could put an anchor in each one and then have a link from one to the other and sort of keep track of what the things are. So this allows this sort of very rich integration between the messages that we're emitting and the output we're generating. Similarly, with the optimization records, there's, that's not very legible, it says inlining %C to %C with frequency blah, saying we're trying to inline this call site into that that call graph node into that call graph node with frequency there. And so inside the formatting subsystem, there's a custom token which, where you can add new types of token. And so I use that to say, well, this is a record from the dump file optimization record subsystem. So inlining this call graph node to that cold graph node with frequency and then that. So when that comes through into the JSON optimization record, you'll see it's inlining, and rather than just having the text get CPU ID max, blah, 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 it's also capturing that it's a symbol table node and it's at that source location. And for example, for Gimple statements, it will capture things like what's the profile, what's the profile information of this statement, so that you can query based on the hotness of a particular, you're probably most interested in the code that's being called a lot. All of this has existed for quite a few releases, by the way, but having this sort of unified rewrite of PP format has basically allowed me to consolidate and remove an awful lot of hackish stuff and into one new internal representation. So the current status is, this is in Shrunk, and it has allowed me to simplify the formatting code, and it allows for much nicer machine-readable output. One issue is that this is currently only applying to the formatted text printing. If you're just doing, just sending strings and other things to a pretty printer, that part of it is still just accumulating text into a buffer. And it's probably very doable to have that be a token list so we can capture things in a rich way as well. So there's a bit of an annoying inconsistency between the two right now, well, maybe I'll fix that, I'm sure. The other thing is maybe we could have other kinds of token, like a begin span, end span, for sort of arbitrary semantic markup. So you can say in %QT that this is a type, this isn't just a string, this is a type. And then if you're doing, for example, perhaps we could do HTML output, and you can have a div or span class equals, and then have CSS to colorize things appropriately, based, and which I think would be pretty easy to do. It would be, it would basically leverage all the %Q stuff we've already got. And do nice output. This is, of course, assuming that we want to, if we want to do HTML output. Moving on, libdiagnostics. There's a wiki page on our wiki talking about this. So we've got all this existing code for printing diagnostics and working with diagnostics and emitting sort of either as text or as serif. And so what I've done is I've sort of wrapped that up behind a simple C API into a new shared library. And it's kind of similar to what I did with libgcc-jit way back when, which was sort of taking GCC's code generation code and hiding it behind a C API, a pretty opaque one, I should say, to avoid sort of tying us down implementation-wise. And so there's a new, you have to opt in when you build or configure GCC with a -- enable libdiagnostics. And build it. And this basically exposes all of this code that we've got as a shared library with a header. And I say, yes, you could just use fprintf to standard error, which you probably are already if you're working on a tool that emits diagnostics. But if you use this, then you will get things like quoting of the relevant source code, underlying of ranges, the sort of the labeling of ranges of source code, if you like, the control flow, you can do execution paths with the control flow edges and all of that. Fix-it hints, generating a patch from the fix-it hints, logical locations versus physical locations, like rather than saying at line blah of foo.c, it's within function foo, or within namespace class function, and finally the serif output. So in terms of, how am I doing for time here? Okay, I've got 15 minutes till the top of the hour. So example of how we'd use this, you would make a new diagnostic manager, and this is basically the sort of the context to the library, the thing that your context for talking to the library. You tell it what your name is, if you want to do serif output, because serif has a required attribute, which is what is the generator of these diagnostics. And then you make, for example, a source file, diagnostic file star saying, well, this file name, this source language, we can make a text sync. We'll go output to standard error, colorized if standard error is directly connected to a TTY, but not otherwise, or we can do always and never. And well, let's open a text file star and send Serif 2.1 to it. That's actually the only version supported there. That's just there for future expansion. And then, yeah, let's make a location, that file, a particular line, and in fact, a range of columns. And then you make a diagnostic. It's an error, and you should populate the diagnostic with data. And finally, so here's where it is, physical location. We'll add a fix-it hint, and then you finish it by sending a formatted string and the var args, which sort of has to be last because you can't, I don't know if there's any way of preserving var args. You sort of have to use them there and then, ultimately. So there's the unknown field color. Did you mean color? And so here I made compile that to a.out. Yeah, this is me running it on my laptop last night, so it's not installed. It's just, oh my God. And you'll see, yeah, it's emitting, it's doing the formatted printing. It's sort of it's put stuff in bold, for example. It's finding the source code for you, quoting it, doing the underlining, showing the fix-it hint. And here I did the generate patch API thing, which generates a patch from all the fix-it hints on the manager and emits that as you exit, for example. And also here it will do Serif output. So here is the Serif result saying, yeah, unknown field, blah, 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 with all of the data in machine readable form, including the fix-it hint, fixes, artifact changes, a replacement of that with that. The other thing I've added is, well, we have all this, now that we've got a library, or I hope that there'll be a library, to work with GCC's diagnostic subsystem without bringing in all of GCC. I've created a command line tool, Serif Replay, and this is sort of, yes, we can serialize our diagnostics to a file, and this is the opposite, saying, oh, can we load a diagnostics from a file and turn them back into text? So this is a command line tool that uses libdiagnostics and basically reads the JSON and basically calls into the API and then says, give me Serif output. Well, you could have other output, then use it as a converter. And so here we are, Serif replay of a saved Serif file from the analyzer, and it's replaying and it's showing a reasonably faithful reproduction of what would have appeared on standard error with colorization, events, quoting, and so on. There's some issues about can you find the source code and in order to be able to quote it. So that's, I'm at version 3 of the patch kit, which I last posted about a month ago. It doesn't have documentation yet, so we would need that, which I'll work on. It has bit-rotted somewhat, because I've been making a bunch of other changes to the diagnostic subsystem. As I say, yeah, I have a patch for the GNU assembler that uses this, and potentially you could do one for the linker as well, so we would get, like, quoting the source code if you have, like, you're calling this function but I can't find a definition of it anywhere. But as it turned out, that's one of the things that is bit rotted and I need to fix as I was writing these slides. There are probably bugs. But yeah, I would like to get this into GCC 15 because I think it's a useful feature. And I work with the analyzer, I'm generating like tens of thousands of Serif files when I do the integration test, so it's useful for me to have a way of just looking at a Serif file. So basically this cycle I focus, normally at this point I talk lots about the static analyzer. I added a new warning, which is, you're subtracting 2 pointers that are the address of two global variables to compare them, and that's undefined. That's basically the only thing I've done to the analyzer for GCC 15, but as you see, I've been sort of focusing on the diagnostic subsystem in general. And so most of what I've talked about already is already in Shrunk for GCC 15, and I've sort of said some things which are more experimental. Here's the more out there and experimental stuff. C++ template errors. Cy Brand of Microsoft has posted this very nice proposal for extending Serif to capture sort of hierarchical structured diagnostics. And the idea is for C++ templates, traditionally you get these screenfuls and upon screenfuls of screed about saying I can't resolve this template because of reasons. And the fix probably is, rather than try to capture either everything or, to be concise, is to catch everything but in a hierarchical way and give the user like a sort of expand collapse widgets where they can drill down into the part of the diagnostic they care about. And so Cy posted this proposal to the C++ standards thing, and also to the Serif body that uses Serif to capture the templates. I have a prototype implementation of this for G++, I suppose, the C++ front end, and it's currently really ugly. Basically, so rather than having a flat, I tried this and it didn't work, I tried that, it didn't work, it actually this is obviously debugging code. It captures the hierarchy of what it tried and why it was rejected. And in like this concept isn't satisfied, or this I couldn't satisfy this conversion doesn't exist, like, so it sort of goes through all the candidates, but it captures that in the hierarchy of that. Now, some questions. What should that look like? I don't know how to make it compliant with the GNU standards for diagnostics, for example, or how to make it work nicely in the Emacs compile buffer, which is sort of what I use. How do we represent that at the Serif level? Like Cy's proposal had one way of doing it. It kind of works. I have some concerns it might, but anyway, that's going too into the weeds. And then what IDEs would support it. Microsoft have an implementation of this in their compiler and in VS Code, but currently the proposal in terms of how the two talk to each other uses a very Windows-specific RPC mechanism. And so obviously we would want to generalize that to not just work on Windows. I'm also looking at, so currently we have a global diagnostic context inside GCC, which has a single pretty printer, and we have a single output format, either text or serif. And so you can do, basically, you can only do one thing in one output format at a time. But it would be really nice if we could both, say, for example, write colorized text to standard error, and also emit serif somewhere. And so sort of been looking at, can we have multiple output sinks for diagnostics, as it were? Yeah, you can in libdiagnostics because we don't have this global variable, and there are reasons. So I've got an experimental patch that sort of converts it to a vector of dynamic output formats, so multiple sinks, and then the global diagnostic context pretty printer, we instead have a pretty printer per output sink. But unfortunately, there are lots and lots of places inside GCC. Yeah, sorry, I'm running out of time. Yeah, oh, yeah. So that HTML output, I've got a patch that adds that as an output format, but I kind of dare not commit it, because then I'll get bug reports, because everyone will want HTML a different way, so I don't know. I've also got a patch that will send diagnostics via RPC, similar to the one Microsoft had, but I'm not quite sure how that should work, but it's kind of fun. You run GCC in one window, and the diagnostics appear in another. Potentially could be sent to an IDE. Again, it's sending the serif that way. So yeah, I'm running out of time, so that's my talk. Questions? Siddhesh? Yeah, we've got 3 minutes till the top of the hour, and so sorry I didn't really leave any time for...
So this is probably more of an internals question. So you've got pretty printers, the pretty printing class, which you're basically transforming from making it a simple text buffer to like giving meaning to the diagnostics.
Yes,
right?
yeah.
And at the very end, you have Serif as a format, which already has given meaning to diagnostics, or attempts to do that. So have you thought about using the Serif object model, not necessarily the output, but object model in the beginning, so that way you have this one kind of descriptive object model, which you can then transform to whatever you want.
Yeah, the question is, basically, can we capture things in the Serif object model earlier? The issue is that with that is that Serif doesn't seem right now to have as much support for inline markup as I would like. There is a way it supports Markdown, but only a somewhat limited subset of Markdown, as far as I understand it.
That's something that you can drive in the...
That's what I hope to do. I mean, I wish they did restructured text instead, but they pick Markdown, and I will stop ranting. Any other questions? Jakob.
So you talked about an option to select between Unicode and ASCII. Is that meant just for the ASCII art, or there are things where you emit parts of diagnostics directly from the source code, like hash error, hash warning, static assert, and so on. And so the question is if we should re-encode, because we know the source code is probably in Unicode, UTF-8, and if we shouldn't recode the parts of the user parts of diagnostics, so that user can see it.
Sorry?
C++ could have Unicode.
Yes, so you raised some very interesting questions, and I'm not quite sure the correct answer in terms of, full Unicode support in the source language itself. I believe ultimately we're turning things into UTF-8 internally. I hope, and the Serif, for example, we convert. One of the bugs I fixed is if there's a bad encoding in the Serif file, how do we report this is not encodable as UTF-8, or this is not validly encoded, and encode that diagnostic in a validly encoded Serif file? And we do handle that case, at least, I know. All right, I think are we out of time?
We are running out of time. That's my job. So I would like to thank for a very nice talk and good work.
All right.
So yeah.
Thanks.
And we start immediately as things are ready.
Thank you.
Yeah, it's yours. So please repeat questions which are not replied. Hear them on the things.
The idea was we need to go first anyway, but why up first? Everything works? Yeah. You start first.
Yeah, we go 3 minutes.
Yeah, you could try here. I don't know.
So you will be switching computers during...
Well, we want to get one which shows the result which used to work, but currently
Do you have HDMI cable connected?
I have this cable connected. I don't know whether that's the right one.
Yeah. Asi nahoře, no. Asi tam je.
We show my other screen.
Ne, sorry, to asi funguje.
It's still showing the other screen. You don't need to see my Jira. I don't know what's wrong with yours.
So which one of you want
What's my battery doing?
So can use this one.
Okay,
Sorry guys, which one of you want this?
you can have that because you're doing the most. I'll use the other one to start.
Yeah.
Well, I don't know who starts, but
Can you some...
yeah, but well. Well, we all use the mic.
Right.
Well,
Do you know
well, in the
it's unmuted.
case, welcome. We quickly go through these three different topics, each speaking a bit, and also kind of starting why we started a bit slowly with some turmoil internally, and well, give some results of us and others. And Andrews starts.
Hello, everybody. Can you hear me? Okay. Okay, can you hear me? Okay, good. Okay, yes. So, hello. We do this talk every year. This is the last year you were seen as wearing Siemens colours. So this year it's Bay Libre, but we're doing the same stuff. Yes, as to be said, we had a little bit of internal drama when we all got laid off last year, but still working on it. There's a bunch of us doing this. So a little bit start about who Bay Libre are, because we're advertising, obviously, and then moving on to the project stuff. We got the HPC stuff and the internals update, and then at the end we'll talk about the Summer of Code projects that were happening. But we're a few minutes late, so let's get on. So, Bay Libre, you probably may or may not have heard of them. Been around a few years now, but doing kernel stuff mostly. The compiler stuff is new. So Bay Libre have been around since 2013, but we've now incorporated what's left of the Code Sorcery team, which has been going considerably longer. And obviously we've been here for years, so you all know us. But yes, the history is sort of is up there. Obviously our drama last year was Siemens decided they wanted out of all software. Basically, they didn't want that. I mean, that's fine. That's up to them. But we were rather upset about it. So about half the team have joined Bay Libre. The other half gone and done other things. So we have some openings. We are hiring. If anybody wants to do HPC work or other random embedded tool chains, please let me know. We have senior and junior positions open. There's the possibility of a ski trip as well in France, because HQ is in the south of France. It's a good place, small company. Let us know. Right then, you want to do this one.
I can do this one, yeah. Okay, I'm Thomas Schwinge. I guess most of you have seen me before here. That's just a quick status slide of the OpenMP, OpenACC offloading support in GCC. We have this slide every year, I guess, or similar incarnations. And not too much is changing on that slide, because then, of course, behind each of these items are a ton of details. So OpenMP 5.2 means, I don't know, 600 pages of text or something like that. Yeah, so OpenACC support is still at 2.6 level, which was released 5 years ago or so, or even more by now. Work in progress is on 2.7 items that we're currently implementing. Some of them are already in GCC mainline. OpenMP 4.5 is fully supported, I think, or maybe some small exceptions, as everywhere, and the later revisions are also in progress. 6.0 is the hot new thing, and I guess work on that will be beginning at some point. There's a nice page where all the individual items are laid out and their implementation status. OpenACC, OpenMP offloading share a lot of middle-end lowering code and runtime library code. Yeah. Then, right, for OpenMP, there's of course the traditional kind of OpenMP shared memory CPU parallelization stuff that is not yet available for OpenACC. Could do that, but somebody needs to send the patch, basically. Okay, then we have code offloading AMD GPUs, which compiles to a specific instruction set. And there are several variants that we have listed here. One has recently been removed from GCC because that's out of support by AMD for a time already. The Fiji GFX 803. The other ones on that line were supported before and new for GCC 15, or some of them are already in GCC 14. Yeah, are a few consumer level cards and other items. Andrew will go into a bit more detail later on. Then for NVIDIA GPUs, we compile to generic PTX, which then can basically run on any NVIDIA GPU via just-in-time compilation to the proprietary NVIDIA backend language. Right, and the important thing for GCC is that C, C++, and Fortran support for OpenACC, OpenMP is mostly developed in lockstep. That's different from the LLVM, Clang, Flang world, where Flang is way behind still. They are greatly catching up, but that's the good thing about GCC, that you have most of the features available in all three languages. And that's just a quick recap of offloading in GCC. Does that work? So you begin with your source code, whatever language you have or whatever mixture of languages you have, run that through the front end, get a .o file out of that. Just as in your normal host code compilation, the .o file contains embedded representation of the code regions that are to be offloaded to a GPU or other device, which just sit in this object file. And then when you run GCC for linking your object files into an executable, the linker sees that there is offloading code IR in the O files and runs the offloading code generation backends. Can be several, so you can have fat executables that contain PTX and AMD GPU code. And right, that's running here, and then that's again transformed into a host object file, which then just normally is linked into the final executable here. And then at runtime, libgomp, well, there are constructor functions generated for registering the host code at runtime. And that, when you invoke your executable, tells libgomp that there is offloading code for these and these functions available, and then it can probe which GPUs do I have in this system, and then when you get to the corresponding OpenMP, OpenACC constructs, launch the code offloading to the actual GPU. That's just a high-level overview in case you have not seen that before. Okay, then quickly some generic infrastructure changes that went into GCC trunk in the last year. Always miscellaneous cleanup and bug fixing. We have some improvements for scanning, offloading tree dumps, which is useful during development, obviously. I'm for a year already working on making C++ better supported in GPU offloading settings, so have some initial parts in GCC trunk to make that more useful. Some probing stuff does not matter too much. And some, again, internal stuff where we were basically generating wrong code. And ever since we added the offloading support 10 years ago, and now by chance I noticed that because when I run the test suite in .h mode, so to use a lot of CPU cores, and it turned out that when some test was running, there were still so I don't know if you know that the make uses some token system to distribute tokens which correspond to the .h number, and then either you run that many compilations or basically the LTO system also can claim tokens to run LTO compilation in parallel and offloading builds on top of LTO. And so it happened that there were slots available, and then we got some mismatch because variables were compiled or used several times in these streams. So kind of an unusual setting, but was fixed. And another bug fix to a bug fix, which also depends on a GNU Tools update, actually. Right, then Tobias will go into more detail regarding the OpenMP changes, which is most of what we're doing recently.
Yeah, and I try to get also some bit more feature size, so not having shown only these, tables, what done, not done. So I list some GCC 14 items, attributes are now the thing. So that's actually one of the few new features, which is an OpenMP 6 partially in there. A few other things which can be useful as well. And, on the GCC 15 side, a lot of older patches are in there. And especially for Unroll and Tile, I want to show this can actually be used also if you don't use OpenMP, essentially. Or you have to use the syntax, but if you use the OMP SIMD, then there are a couple of commands which don't need the runtime library, so you can use it in principle in any code where you dare to add this flag. There, of course, like the name SIMD indicates, there are other things which are actually enabled with this flag, but none of them requires runtime support, and we otherwise go slowly through the list of new features. And I want to switch to some things which are in the works, partially already there, but need to be included. It's mostly meta directive, which is an older feature. In principle, it's being revised and being reviewed. I'll give an example a bit later. Bit related to that is something which is really work in progress. That's something which is called variant functions, which in principle are old, but there's a new feature in there. We talked about last year in the BOF bit, how to handle things. I come to the example in a moment, and dispatch. So there's some related features I just want to present in terms of the language and in getting support. So we have meta directives, which take, one can decide an OMP Teams loop or OMP parallel loop as directive, and then decide what to use based on some condition. For instance, that the device is an NVPTX offloading device. And there are a lot of features, some of them, which is also an OpenP 5.1 feature, and with target device, which then asks for what you have as a runtime device. The same pattern, that's currently a bit under review, and finally we try to get in to the new version, is declare variant, which exists in other syntax. I will show in a second here, but there's now the possibility that one says declare begin, end, and Sandra is currently working on getting the mangling done, and of course the mangling depends. So with declare variant, you just call the function, and then it looks at the place where you call it, which of them it should use. Can be also used elsewhere, and I think the variant of SIMD in a way it's also used for vectorization, so one can have some match, and then one somehow needs to encode this match in the mangled code and to make sure that it works. So that's one part. The other part, which I wrote there, was code illusion, which we now currently implement in a simple way. If you put the whole thing through the preprocessor, but then if you pass and you see this one can never be true, for instance you disable this function, then the code is supposed to ignore everything until the action declare variant. So that's currently implemented. Of course, in a way, as we saw before when Thomas showed the slide, so if we enable AMD and NVPTX, then all of this gets enabled because we pass only once, but at least the other things get excluded. And in any case, if multiple things can match at compile time, then the user needs to make sure that all declaration and so on, that they don't collide and are anyway available. I mean, since it has to go to the preprocessor, this file has to be available in any cases. Well, that's one feature being worked on with mangling and this one, and the last one, which is a bit smaller and currently in, here's kind of the normal declare variant syntax, where you declare the variant to the function coming directly behind it, and you need to make sure of the names. New is that under certain condition dispatch, one can say, I don't want to have the context, so OpenMP-wise it has the context that's in the dispatch construct, or I don't want to have variant resolution, and it also supports saying, please convert these arguments, or to be precise, these arguments to the device version. Yeah, you have to map them first and then set a default device to that one, so that's kind of some features in flight. I just want to mention some other nice OpenMP features. So people like to combine code. They have the OpenMP code and then they want to call some runtime, let's say CUDA or HIP or whatever function directly, and there they need to get the device number out. So they might not match or some handle, and there's now a new feature interop, which is currently also being worked on, where one essentially says, please give me an interop object for the current device. In this case, if there's no device number, say, I'd like to have a CUDA object, then if I'm lucky, I get it. Check that I get it, and then I can get, for instance, a stream object, which does hand it in dependency, so such features are in and currently implemented. And well, now to the more or less status list. I start with compliance feature, so really that's supported. I mean, there are some other features. OpenMP 4.5, as mentioned, is essentially done. Recently there was also someone complaining about some missing feature. The rest is also mostly done with the newer ones, but we have a larger backlog of patch review and revision. And of course, a bunch of smaller features and two bigger features which are not in the core but a bit later. That's tracing and debugging. Especially tracing is useful for performance and very widely used, so big omission. Debugging is seemingly not so wide used, and actually it goes on with the newer ones. So 5.1 essentially complete. We need some few things, so that was on the first slide, work in progress. There's another patch posted and being worked on for some other things. So a lot of things done, but still, especially in these final stages, getting it in is things missing. And for 6.5, it's a small release, so a lot of things is in there already. Mostly missing is the other features or the features we depend on, smaller things. And the next big thing in the room is the OpenMP 6 standards, which had some technical previews before in, well, 1.5 years ago, half a year ago, and very recently, and were released for supercomputing. And that's, of course, a huge one. We have some minor things, like the attributes in there, but more to do. To make it really useful, there's this more implementation quality features, so like unified chip memory, you don't have to support except syntax-wise, but everyone expects it. So there's something in GC 15, we have also allocator supports improvements, but there's some, again, patch missing for some cleanup and or improving unified chip memory, pin memory, and also some cleanup work. And well, there's of course more things one could do in the future. I think near term is reducing the backlog, finishing work in progress items, small features, and then next, but of course depends on time, funding, and so on. Performance offloading, I think it's a big thing. Finishing 5.2, tracing would be good, lowering features, and that's more or less what's in flight. And Thomas wants to speak about OpenACC update.
Right, so OpenACC support in GCC, as I said earlier, not too much development going on because the customer, our main customer, is more interested in OpenMP these days. But as I mentioned, always again, miscellaneous cleanup and bug fixing, and a number of OpenACC 2.7 features got in already. I guess, yeah, I can introduce them quickly. The self clause is useful to, if you nest compute constructs into each other, the self clause means to run this OpenACC compute construct not on the GPU, but on yourself, basically, so on the host where you're starting. And in theory can be used to parallelize at the host level using multiple threads, which is not currently implemented in GCC, so it's not useful per se, but still we need to parse it and handle it correctly, even if we then don't apply the host-side parallelism. And the read-only modifier means that data transfer to the GPU is only read there and not modified, so that means the compiler can do some optimizations around the data transfer and or use different GPU memory spaces for constant memory, things like that. Front-end support is in the actual interesting part to use that, not yet. Right, and then OpenACC has structured and dynamic reference counting, which is different from OpenMP. So structured means when you enter a region, like a block with curly braces, and there is a OpenACC construct attached to that block. That's static reference counting because you enter at some point and leave at a defined end of block. And these can be nested, of course. And then you also have dynamic reference counting, which is when you have pragma ACC enter data, for example, then that's a dynamic region because when that statement is executed, you do these memory transfers, for example, or other things. Right, and that patch cleared up some, well, the patch, but the OpenACC 2.7 revision cleared up some mix-ups there, or made that, yeah, unconfused some things. Further OpenACC patches are in development and will be coming, hopefully, still in GCC 15. Then I will continue with the NVIDIA GPU support. And first highlight that this us working on that mostly, not NVIDIA, even if there's an NVIDIA logo there, that's just to highlight the GPU. And recently NVIDIA actually started contributing to that, so that's great. We'll highlight that in a later slide. Right, and it's not only us working on that, but also other GCC contributors who find the NVPTX backend useful. So, and again, miscellaneous cleanups and bug fixing. Then as I said, I'm working on the C++ support. One thing was to use the usual weak declaration thing that the C++ front end kind of would like to behave correctly. That's not yet useful for offloading code, but what I need to do as part of the C++ work is run the NVPTX code generation as a NVPTX target in GCC. So like when you have an embedded target and compile to your, I don't know, MIPS chip, for example, if anyone still remembers MIPS. And then you use some loader to get that on your bare metal target, run the GCC test case and get back some good or bad test result. And we use that obviously to test the compiler for correct code generation and all these things. And now if I work on C++ support, I would want to be confident that the C++ front end, middle end, lowering, whatever comes is behaving correctly. And for that run the usual GCC C++ test suite. Because if I only test the offloading setting, I have to basically replicate all the C++ constructs that we would like to support in offloading. And when I, on the other hand, as I just said, use the standard C++ GCC test suite for NVPTX target, then I basically get the checking of the code generation for free. Just that it takes a lot of time to go through the test results, and if we in the NVPTX backend do non-standard things, we have a ton of fails or need to adjust the test cases for that case. So it's easier to actually make NVPTX behave the same as other targets, and that's one piece here. And then Roger did a lot of smaller kind of fixes and some bigger ones to review still, and more in the pipeline to basically improve PTX code generation on a high level. So that's another thing I worked on, just to basically clean up the C++ test results. PTX in the implementation that we have does not support global constructors and destructors. So in C++, obviously, when you have global objects and need something constructed before entering the main function, you need that support, or when you use the attribute constructor things. So that was missing. I had some first implementation using the old collect2 executable from the 90s in GCC. Yeah, that turned out not to be the optimal way, so I re-implemented that and have now have the linker figure out the global constructors and destructors to call and inject the appropriate things. And that greatly clears up C++ test results, as you can guess. And then also use that for offloading, where that is useful to switch libg Fortran out of the minimal mode that we had been using before, which did not support any I/O, and the customer was requesting that they would like to have the ability to use printf or corresponding Fortran thing for debugging in offloaded code regions, which did not work for PTX because we could not compile some libg Fortran source files for the I/O stuff, because they did depend on global constructors to set up the libg Fortran state. So one thing required the next thing, and that kept me busy for a year, I guess. But that's now all working. Right, and next thing is to make symbol alias support work with NVPTX. I put in recently a bug fix for one thing, and then, so PTX is a kind of a high-level assembly kind of language. It does support some symbol alias support, but it's very limited. It can only alias functions, not other variables. And you cannot have an alias to an alias, for example, which easily happens internally to GCC even. And yeah, a lot of other things. So looked into that, and other people also made that comment before, maybe we should not actually use this alias PTX support, but instead change the NVPTX linker to resolve at link time the symbol alias information, because then we have a global view of the program that we're generating and then can rewrite the symbols so that we resolve to the proper aliases. This also turned out to be more complex than anticipated, so that's what I'm currently working on. And that's maybe also common to make the NVPTX support in GCC does not use GNU Tools like you would normally do for assembler and linker, but there's a separate package called NVPTX Tools, which our team wrote when we started the GCC offloading support 10 years ago. Right. That's that. And then actually now Prathamesh of NVIDIA, is he here, by the way? I don't think I've met him before. Ah, hi. He has recently been working, or recently a few months, I guess, on enabling the NVPTX offloading case for ARC64 hosts. Which had a number of issues, so there was an analysis email of what's all going wrong, and then out of that fell these several patches listed here. Because the ARC64 host has some properties that are different from the x86 64 and PowerPC LE 64 that we used or supported for offloading before. So there were some changes to do. So that's now, I guess there is one patch missing in review, but otherwise that is now working, and that means you can use the latest flagship NVIDIA Grace Hopper system for GCC offloading, I guess. That's what you have been targeting with your enablement, I guess. Yeah, so that's great to see NVIDIA actually contributing to the GCC NVIDIA GPU offloading support. Okay, and that's all I had here. Then Andrew will cover the AMD GPU support.
Thank you, Thomas. So yes, more GPUs. Sorry, there are only two. There are only two, I promise. So there hasn't been a whole lot of AMD activity, really, like proper engineering in the back end, mostly because of the corporate drama that we already mentioned. I lost about 4 months worth of access to the devices that we had, so that would make that, and also obviously AMD changed their focus a little bit on toolchains, and we, yeah, anyway, so I haven't come back with a whole list of things that I want fixed this year like we did last year, like the vectorizer doesn't work, but on the plus side, while we had no access to our compute devices, we did manage to acquire some consumer devices to play with, which we'd been putting off for years. And so now, finally, we do support some consumer devices. So if you have any of those four, then you're in luck. That's the 90C support was actually added by Frederick Harworth. So thank you for that, Frederick, wherever you are. Yes, thank you to Richie for testing the RDNA 2 devices, and we had some the RDNA 3 devices in house. The 1100 is a proper GPU. The 1103 is literally this laptop. It does work, although you do have to start it in no graphics mode to run the test suite. Otherwise, your computer crashes hard. But, you know, you can do it. There is one removal. Yeah, the really old GCN3 device that we started with all those years ago, like 2017, is now discontinued. There's no more hardware. There's no more hardware support in the drivers. And it was deprecated for GCC 14, and I've just, a couple of weeks ago, removed it from GCC 15. And also all of the back-end support for that ISA completely. So nobody tell me they want a GCN3 device now, please. This is the list of patches that have gone in. I'm not going to list them all, but Yeah, oh, the VGPR stuff went in about this time last year, so that supports the extra registers that the really high-end devices have. XNAC mode is for the memory management stuff. It allows loads to be interruptible, which turns out to be an important thing when you have page tables. And the consumer device stuff. The preferred vectorization factor, because consumer devices have half-size vectors compared to the compute devices. We do run them in compatibility mode, but you don't always get perfect performance that way. Yes, so we did get, when I've been adding these things, I did get a number of emails. Why don't you just support all the devices? And the short answer is it's non-zero effort to add it, and I can't test it. I don't want to add it. The way that the drivers work is they refuse to work if it isn't compiled specifically for that exact device, unlike the NVIDIA, which is kind of, it's got a finalizer in the driver. But if now that we've crossed the hurdle of adding support for the RDNA devices, if there is a device that you would like to test it on, patch is welcome, or just willing to test it, then let me know, and I can see about adding the magic numbers and whatever into the toolchain and fiddling with the metadata and all the stuff that you need to do to get a new target. As long as it's not too much effort. It's not kind of primary role, but it would be really nice to build out the support now that we can do RDNA stuff. So that's mostly the consumer stuff, laptops, games machines, whatever, should work now if we just add the magic numbers into the toolchain, add the multi-lib, whatever. And back to Tobias for the next topic. Oh, it's Thomas. Is this on? Yeah, didn't turn it on.
Okay, so for the first time, actually, we got some Google Summer of Code students working on projects related to the code offloading support, roughly, or other things, as you will see. Two of them. The third item here is outside of GSOC, but a project from GSOC. So the first one, Georgi, is working on setting up infrastructure to be able to test the offloading flow through the compiler and runtime library in particular. Runtime library, if you do not have a GPU available, so standard laptop without GPU, if such a thing still exists today. Well, without a GPU supported by GCC, then this can be useful for testing data movement across host and device and kernel launches and all these kind of things that depend on having a GPU or emulation kind of a GPU. So this currently works by forking. When you launch you compile your OpenMP, OpenACC code, just like you always do, and then run it, and then libgomp has several plugins which it probes. Do I have an AMD GPU that I support? Yes, no, I don't. Do I have an NVIDIA GPU that I support? No. And then I have another plugin called host process, I think. And that is always supported, obviously, because it does not depend on anything special. And then this forks the process, and then you have a communication between host and your device, which is then the forked process, and that way can test the libgomp offloading support. There are a lot of details there again, but a good part of the libgomp test suite passes. The other part is more difficult to make work. So I think that won't happen as part of this Google Summer of Code project anymore. But it's still a very, very good first step to making that work. Because what happens occasionally is that somebody commits something in GCC and accidentally breaks something in the offloading support. For whatever reason, not intentionally, of course, and then has no way to, well, maybe has a way to fix it, but has no way to test what that person is doing. And this can enable such a thing without a lot of overhead. Right, that's this project. Then Tobias can maybe cover the next one quickly.
Please start by dealing with the mic. Well, the first part is really a Fortran thing, so do concurrent. That's essentially only a compiler that the code could be in principle run concurrently, and what was not yet implemented of Fortran 8, 2018 and 23 features were to tell information to the compiler what to do if one really wants to run it concurrently. So let's say fractalization or whatever means. So they added localize, as they call it, like local variable, but initialized, shared variable, default none, so that one really has to specify things, and the newest thing was reduction, and that was not yet implemented in G-Fortran, so and we started out with adding parsing support and handling all of this. It's mostly done on the parser side, diagnostic and so on, but well, so patch is nearly ready, waiting for a few additions to the test suite. But then we have a mostly working Fortran part. The goal, which won't be done during this summer of code, unfortunately, is to go to real parallelization. So for instance, to turn that one into OpenMP parallelization or OpenACC, potentially even with offloading, either by using a flag, or the alternative would be the OpenMP 6 version where they support OMP loop onto concurrent, but at least the basic steps of the base language will be there. And well, that's part of the project. And now let's go to merging the previous talk and the OpenACC topic in a way to static analyzer.
Right, yeah. So that was something we had proposed as a possible Google Summer of Code project, to take the GCC static analyzer and add checks for OpenACC constructs or directives or OpenACC runtime library calls. So you can basically call ACC malloc to get device memory and ACC free to free that. And of course, you should not mix up your host and device pointers, and you should not free after free, even your device memory, even there that doesn't work, and other such things, which is already supported in the static analyzer for host code, so for standard malloc and free and all these things. And the idea was to extend that for OpenACC or for device memory generally. This might likewise apply to OpenMP then, to teach the analyzer that there is a difference between memory you get from malloc and memory you get from ACC malloc. And then all the checks that follow after that. So that's, Vedant approached me outside of Google Summer of Code. We had proposed this as Google Summer of Code project, but he did not get a slot for Google Summer of Code project. But he would like to do this for his university project or thesis, something. So I said, yes, why not? You don't get money for it, but still happy to do the work, of course. Yeah, and that's, well, if anybody knows of any students who would like to do such smaller projects, we now have a small list of them, so happy to do some mentoring. Of course, I also have to do my regular work, or all of us do, but I like to introduce new people to GCC development, and that's one way of doing that. Right, and that's the end of our presentation. There are some BOFs which also relate to these topics. Obviously, the BOF on the very same topic, the first one listed here, that's after lunch today, and then Vectorizer later today, Vectorizer BOF, and the LTO and so on BOF also happens to talk about offloading topics every once in a while, because, as mentioned earlier, the offloading code generation builds on top of the LTO infrastructure in GCC. Then, thank you for your attention, and happy to answer any questions.
Thank you. Barış Akdemir from Intel. What level of debug information do you generate?
For which target?
For any, I mean for AMD and I mean for GPU in general.
So for AMD, we have very basic support for debug. In theory, as long as you use the no omit frame pointer, then you should get frames and you should get basic variable support. The optimization will break things for you. The vectors and stuff, it doesn't understand when they're masked and stuff like that. But in theory, you should be able to start it in ROC GDB, the one that comes with the drivers from AMD, and it should do the right thing. So if you say disassemble in main, it'll give you x86 code. You say disassemble inside your kernel, it'll give you AMD code. It's, they've done good work, and Pedro's in charge of putting it in the dwarf standard. And we have not done extensive projects to enable every little corner of that, but the basics are there. It does work.
And there was a presentation 2 years ago, I think, for...
There is a recording with a demo from the Cauldron that was on the Plumbers thing a few years ago, which you can find on YouTube. And I'm sorry, it's my video editing skills, it's not great.
But it was great to see you step in GDB or ROC GDB through host code and then hit some OpenMP, OpenACC offloading construct, step into that, and then just continue stepping through your device code.
It's funny when you say info threads and there's like 1,000 threads. That's great, that is.
And so that's AMD GPUs, and for NVIDIA GPUs we have some very limited support of emitting dwarf directives as supported by PTX, so that's, I think, basically just location information, but nothing else really. And I admit I have not really used that so far, but in theory you should be able to compile your code with -G to generate debug information and then use CUDA GDB to step through the things.
Do you have any performance numbers you could share on how well the offloading works compared to the proprietary solutions?
These numbers do not yet look too great for most cases. There are benchmark codes where GCC is up to par to proprietary vendor compilers. Yeah, there is work to do there, definitely. And hopefully we will have some projects upcoming to work on that. We have ideas what to improve, where the problems are, or how to find them. Yeah, so if there are people, customers, whatever, who would like to fund such work, we are very happy to do that. Maybe one additional comment, so that's not an inherent, well, it is kind of an inherent problem that this is difficult to generate performant offloading code because a GPU is a very different target than an embedded or standard x86 whatever chip. But also what happened is that the customer priorities so far have mostly been to get the functionality working, so to implement the OpenMP and OpenACC standards. And if that already takes up most of our time, then there's not much time left for performance tuning.
And it's also a bit intrinsic, so one has a lot of levels of prioritization, so one needs to use them very well. And if, I mean, it's Amdahl's law, if there's one serial part that dominates, then a lot, so one kind of fix one part to get really parallel, and it's factor of 40 faster, but then of course all other parts dominate, so one needs to fix kind of all parts to get it, and also the tuning how to distribute the data over these different levels of parallelization seems to be a rather tricky part. in the automatic. And one sees also the other vendors are a bit struggling with that, so some have a lot of experience and have it then working well. Then comes a new construct and might find in a corner case and there it completely fails. So for maybe good tuning, one needs to tune it manually, but otherwise one can try to make the different parts faster. Maybe if we're stuck on this one, I found interesting that LVM project, they have on the offloading part now performance guided optimization tried. And seemingly because of all the cost factors which are not really tuned for GPUs, the code got slower. So they now need to do a lot of studying about the cost to get the performance guiding optimization working. We currently don't have on the offload side performance guiding optimization, but could be also interesting to look into. Any more questions from Max? Suggestions? Otherwise, after lunch, one can discuss a bit more in the BOF style. One floor up.
Okay.
Okay.
Then thank you, Ken.
Yeah. Thanks for your interest and the comments and questions.
within 2 hours.
Do you have some belt we could put it behind, or maybe on your pocket, maybe? Yeah. We'll somehow manage. You can possibly use this, as a backup, And I'm sorry, I'm not good at untangling this. Okay, so.
Yeah. Yeah. Oh. Is it on? Oh, okay. Is that good?
Can you say something?
Hello? Testing?
Yeah,
Okay.
It seems to be working now. So
Maybe.
this is like I'm gonna handle like questions, but this is like kind of muted, right?
Yeah.
You press it, you unmute it, and you press it again, you mute it.
I'll need to do part of the presentation.
So you can use this because we have only one of these. Okay.
Show me again the mute.
Now it's already mute. You press it once, you mute it, you unmute it. At the end, with the question, I can help you around the room.
Yeah, thanks.
Okay. So let me know.
Is there a clock or anything? I can use my phone.
5 minutes.
Okay.
So I'm your clock. Wait. Well, you also
Okay.
And I snapped a few pictures of you. I hope you
Yeah.
don't mind.
Okay. Sure.
changing slides.
Just arrow keys.
Still 5 minutes.
Yes.
We have still time. We can adjust anything, you know.
Is there a mute? No. Does that? Okay.
I'm not sure how to.
There's a mute button. Does that?
Yeah, that's mute button. Yeah, it's a mute. Okay.
Yep. Okay, I guess we can go ahead and get started. So hi everyone, my name is David Faust. I've been working on the BPF support in GCC and in GNU Tools for a few years now. There will be portions of this talk that are given by Cupertino and Jose. They'll join me, but I guess I'm getting started and I have the fancy headpiece thing. So this is not the first time we've given a talk on BPF support. You might have seen it's been an ongoing project for years now. So this is sort of the 2024 update. Little bit of an outline here. But I think the big thing that's happened in the last year or so is that we've kind of finished the port to the point where it's ready for production use and is in fact being used, but in various distributions. And so the big thing there is compiling all of the Linux kernel self-tests. And as people probably know, BPF is very much a Linux kernel technology. And so the self-tests that they've got there are very, very thorough and kind of push it to its limits in terms of exhaustive test cases, all of the bleeding edge stuff. So for a long time, we've been struggling to implement everything that was required, in fact, to even compile some of those tests. And now those are all in place, and most of them pass. The ones that are not functioning as tests for now are still basically blocked by verifier issues where the code generated by GCC doesn't exactly match the code that's generated by Clang, and some of the patterns that are emitted, the BPF verifier in the kernel doesn't actually understand. So the code is correct, but the verifier in the kernel can't know that it's correct, and so it rejects the tests. But with that point, now that it's a usable thing, people are starting to use it, so it's been shipped in Oracle Linux for a while just because, I'm from Oracle. And it's been picked up and shipped now in the GCC BPF crosses in Debian and in Gentoo and in Fedora, and people are starting to build things with it. So at least in Gentoo, they're starting to build the systemd, the BPF portions of systemd with GCC instead of with Clang. And so that's exciting, not only for us as the GCC people, but also from the perspective of people that don't want to have to carry around a big LLVM install all the time. So moving into what's sort of actually happened, this is, just keeping up with the latest developments in BPF. So in GNU Tools side, that means supporting all of the newest instructions that they've got. So things like unconditional byte swapping. Previously, the only byte swapping instructions were endian dependent, so you couldn't unconditionally swap bytes for things that you wanted to. There's longer displacement jumps. That was something that they found they needed, rather unsurprisingly. There's signed memory loads and register moves. And finally, there is signed division and signed modulus, which is something that we told them they would need years ago.
They said no. Why?
Yeah, they said no. Why would you ever need signed division? Well, turns out it's useful. So in addition to that, there's things you can do now with some of the newer jump instructions that we've got. So basically relaxation, being able to, if you have jumps that were too far before, now we can relax them. We turned it on by default in the assembler, so it makes sense. Another big thing that happened in the assembler is there was an awkward difference in terms of how overflows were handled between the original LLVM implementation and what we did. So we've worked with them to sort of consolidate it in terms of if you have any immediate field, any written number whose 2's complement fits in that will be accepted, and then leave it up to the instruction to figure out what to do with that. And that resolves some of the disparities that there were between LLVM compiled stuff and GCC compiled stuff. And also, with the new relaxation from the previous slide, just realizing, hey, let's not try to relax immediates if we're leaving them up to the instruction, and we'll only do that if there's an expression. Another useful thing has been the addition of taking some of the machine-dependent bits in the elf header flags and saying, okay, let's encode the actual version of BPF that we're compiling here, because over time they've added more and more instructions to the BPF instruction set. And so if you take something that's compiled with a newer compiler, with say compiled to version 4 of the ISA, and you try to load it on some kernel that only has version 3 implemented, then the kernel's going to say, no, I don't know what to do with this. These aren't real instructions. And so the header flags just are a convenient way of encoding that, and then the disassembler honors them unless the user specifies them explicitly and stuff. So that's just pretty useful. The bulk of what's been going on, though, is in GCC, probably unsurprisingly. The first thing, people in this audience might not be familiar with this, but at LPC, I think this is exciting. We had to ship for a while a workaround for the BPF headers, or for the BPF helpers. That's something that's shipped in the kernel, but for GCC for a long time, we had to have this workaround file, and it was a pain in the butt for everybody involved. So we've managed to implement everything we need to use the real kernel version and not our own, and that way it's not a headache anymore. Another thing that we were lacking on was the BPF core, which is compile once, run everywhere. Is basically building your BPF programs on one kernel and then running them on a different kernel version. And so that's finally been completed in GCC. Another couple of things are sort of changes in the defaults to match what users actually expect. So for one, the BTF, which is the BPF type format, sort of the type information for BPF programs, that's now the default when you're generating, when you say -G for the BPF target, because that's sort of what people expect by default. And then if you want, you can also generate dwarf with just gdwarf. And the assembly syntax, from the beginning, we've had sort of two syntaxes, because in LLVM, they use this very pseudo-C style thing on the left with the R0 equals. Turns out it's a pain in the butt for any program that expects something that looks like an assembly language, and anybody who expects to read assembly language. So we sort of adopted the more typical assembly syntax from the user space BPF project. The problem with that is that there's a lot of inline assembly in the kernel BPF headers, and those are all written with the pseudo-C syntax. So in practice, it becomes necessary to sort of do this by default so that we can compile things that are using those. Also, one thing that comes up a lot with BPF is that you can't have any library calls. And so you can't fall back on things if your instruction patterns don't implement, you can't fall back to lib calls if your machine doesn't implement some instruction patterns. So one thing that we've done recently is to make sure that the built-in memmove and memcopy, that family of things, is always expanded inline in a way that the verifier can understand. And that avoids issues with falling back to lib calls and then finding out that you don't have anything actually implementing that lib call, so you can't use the program. Another related facet with the different versions of the instructions is that there's all these flags that are used, and there's feature macros that are used by existing BPF programs and people who have been using BPF for years now to check whether these different kinds of instructions are available. And so as we implemented them in GCC, we added the flags, so you can have finer grain control than just a bulk CPU version. And that turns out to be useful because a lot of people are using custom forks where they've backported certain instructions from later versions, so they might support only CPU version 3, but then they also have, say, the longer jump instructions. And so there's feature switches that let you turn them on and off, and now we're also emitting the same feature macros so that people can have the same checks between compiling with GCC and LLVM, whatever. Oh, there's a question there. Yeah. Mm-hmm. Mm-hmm.
But those are combinations that won't happen for any same user. And we will not have tests for those combinations. Because are we going to make exponential number of tests?
Yeah.
Idiotic tests.
Yeah.
And do we want to support this at all? So, well, you now have only 6. So
Yeah, I mean, that is definitely a concern, especially because they keep adding stuff to the BPF instruction set, so.
What's your point, that they are not really instruction set designers? That's correct.
Yeah.
Well, you say they have to do stuff in new instruction set, but then you have to go with the previous generation stuff as well, if you have that new instruction.
Yeah.
And you do not have a random combination.
Yeah, so usually these flags aren't very useful. I mean, what people typically do is they will use whatever is the latest version in the kernel that they have, right? But in very rare cases, they will have an older version, and then they've backported some set of patches for the kernel to turn on one of the new instructions, but not all of them. And so that's, for now it's manageable. It doesn't necessarily mean it will always be. So, yeah.
Well, in this case, at least you have only 6.
Yeah, yeah. Let's hope it stays that way. Yeah, so the next thing that's been going on is completing the core implementation, and I think Cupertino is going to talk about that. So,
can you hear me? Yeah. Okay, so last year I presented core, but it was more focused on the how to implement it within GCC, taking as example the initial implementation from Clang. This year I'll focus more on show the end result after it's done, and a little bit of a glimpse of how I did it. Okay, so what is core? Core, like David says, is compile once, run everywhere, and basically the intent is to multiple kernels to be able to run the same binary produced for BPF. It relies on these type relocations in order to patch the code at load time, such that it would fix the offsets to access the specific fields of structures or enumerations. And that's basically that. I have a diagram on the next slide that shows a little bit what I meant. So, for example, I don't know if, yeah, it works. So we have 2 kernel versions in this, not kernel versions, 2 structures representing structures within the kernel, for example, right? And one might compile an application, a BPF application that's using this struct as a reference that would be in the binary. So on the other side, you have another kernel version that has a different structure that was compiled and run Pahot and generated BTF information for that version. So the core infrastructure actually generates the code in the best as possible, meaning that with fewer instructions as possible to represent a load or a store of something that you don't know yet where it is in the structure. So, for example, you have the load, and the load would be associated with a relocation that would be patched at load time based on the BTF information to fix up the offsets that would be within the load to be the right patch for the new kernel version. The loader itself verifies that both BTFs are compatible, and if in case some field doesn't exist or stop existing in the new kernel version, it would abort with an error. So the BPF core infrastructure actually is implemented using built-ins. So as you can see, this, for example, the first built-in has 2 operands. One is the field access, which would be, I'll show in an example after. But then they kind of collapse like what would be multiple built-ins in single built-ins. And then the second operand would be what the built-in would actually be doing. For example, let's take a smaller example. This enum value, you would have the enum type and the enum name, and then you would specify if you want to know if it exists or what is the enum value in this specific kernel version where this BPF application is running. So, so as you can imagine, this could be quite tricky to get, and indeed we needed to hack a little bit the front end in order to obtain this information. to sum up, so all these four built-ins are actually more of like collecting BTF information. None of them has any effect within the code itself. However, this part down below actually is the one that allows to access data, either loading or storing. And it's based on this built-in preserve access index. And this would actually, so if you have such an access, it would generate the code that would be setting the relocation such that it would correct the offsets on the loads and the stores in order to obtain the data from the load. So in the next slide, I have an example. And this is the most simplistic example of this preserve access index, right? And as you can see, you have a store of 42 to this P-B, and because you actually attributed the struct, then this would kind of like annotate this PB with the built-in preserve access index, although it's not the same thing. That's not what's happening, that's what I mean. And so just to say that both of these lines would be kind of the same thing and produce the same result, except that one is loading and the other is storing. And so the assembly result of this actually is a store and a load. And the thing to notice is that the relocation itself is not a regular relocation that is. Do you want to?
I'm just wondering if the attribute on the structure is enough to decorate the store, why isn't it enough to decorate the load as well? Why do you need to explicitly call built-in preserve access index on the return? Why can't you just say return P into B?
Yeah, it would have worked. It's just an example, and just to show that there are two ways of actually doing it, nothing else. So they are semantically the same thing, because this thing is attributed. Imagine this was not attributed, this would not be generated as a core access. So, like I was saying, the thing to note is the core relocation. And this core relocation is actually not a traditional relocation. It's set in a specific section for BTF extensions that are specific to BPF applications. No other target has this support, generates this section. And then from this section, you actually access or contain references to BTF information that would allow you to understand what the type actually is. So just to give a glimpse of the internal part on how we are actually doing the transformation and collecting this data. So, so we now actually go through, we have a specific pass. This thing is an error. This was intended to be 009 BPF core lower, okay? And what happens is that on that pass, I actually traverse the Gimple tree looking for things that are attributed with preserve access index. And then I identify if I can compute at compile time the offset. And if I can, and this thing is a preserve access index, then I know that I can convert this thing into a pointer plus offset access. And so I construct these entries in the Gimple with this built-in core reloc. And one, in this particular case, is actually an index within a table which I copy both the type information associated with that and the expression itself. And I kept it all through compilation until I'm on the last stage, just to be able to actually generate the relocation referring to the original type and the original expression that was associated with it. I do this thing because otherwise the other passes in GCC can play with it, and then I'll lose the information. Okay. So in the next example is a little bit more complex, but is a little bit more of the same, and just with different types of expressions down here. You can, just for conclusion, you have the structures, but then you see that this, except from the first one, that is actually as you can compute the offset of X from P, and then always you also know the size of QS at compile time, you know the index. So you can assume that you can actually get the full access in one instruction. So that's what you get. You have a store in which you have a single offset 42, which would be the offset for all these expression. No, sorry, 48. 42 is the equal sign. So 48 is the offset. And this 48 is what is patched by this relocation here, okay? And this information is what I kept on that original built-in. So the same goes with these two expressions, except that you have two indirections. And so for that reason you cannot compute the immediate offset because you have another pointer. So you compute the offset for this one and this part, and they are both expressed in two instructions, okay? So and that's it. And this is more of the same, but with the array indexes. So very minimalistic. So the other thing, and this is an example that actually doesn't work in Clang or LLVM, and in which is when you have like an unknown index in an array access, right? In the particular case, and because we are not so centric on the built-in transformations, but rather in walking the Gimple tree and identifying what are the expressions that we need to convert, then we figured out that it would be relatively easy to support this kind of representation. So for this example, and this is not in upstream code, but you can see that I can generate a relocation which collects the size of the struct Q, which would be, for this particular structure, 8, but for the running kernel it will be something else. And then we can actually create a core relocation to collect the size of the struct, and then having the arithmetics to actually compute the position in the next pointer to actually get the access. And that's exactly what's happening here. The thing to notice is that in this particular example, we actually are lucky to have a Gimple format of this type. We don't have what comes next in the next one, which is sort of the same, but instead of using QP, and QP being, in the previous one, I was missing there. So QP being a pointer to the struct Q, right? So instead of using QS, which would be, we have QP, which is a pointer. And for that reason, the parser or the front end actually doesn't generate this array ref, but instead generates pointer arithmetics, which then will be harder to unveil and discover that the particular 8 that is here is not the size of the struct. So it would be extremely interesting to actually be able to annotate these 8 in the Gimple format in order to say, okay, you know, this is an 8, but it actually comes from the size of the struct. And in that particular case, we could also support this kind of code. Yeah.
Yeah, but this is exactly what you're doing, right? In the example before, you annotate the 8, the size of Q. Well, yeah, right, I know. So you do that in the example before, and you are not doing it here, so I don't see the principal difficulty.
I did not annotate the 8. Oh, sorry. So,
yes.
So this is the default format, right?
Yeah.
One example, if I have this QS, if I have this type of, sorry. Yeah, so in the Gimple, and this is really in the Gimplification step, right? So in the Gimple, we actually have an expression like this, which is, this would be an array ref. On the next one, you don't. On the next one, you have the pointer arithmetics. It was expanded. So
Of course, you have to. You need to change the expander that actually calculates the expression and substitutes the 8 in this multiplication by extra instruction which you can annotate. Of course. I just wanted to say that there are no principal difficulties in that. It's just you need to change the expression expander.
Nothing special, I guess. Yeah. It's nothing special. It's just that we didn't do it yet because it's not actually a pattern that Clang supports. So our target is really to support whatever they have, and then just showing it as the next step. So I'm just finishing. So just to finish, like we stopped having a kind of built-in-centric idea of how to implement this thing, and it goes to a Gimple traversal format. We use this get inner reference as the way to figure out, to extract the information of what is computable at compile time and what is not, in order to do a recursive transformation. And yeah, so we are running self-test. We did run the self-test. We actually found many bugs with it in core. And yeah, upstream we are just compiling BPF or the self-test, but in the house we are actually running. So we look forward for it to be running soon.
Thanks. Okay, so the next thing, there's BTF, which obviously the core stuff relies on, but also in general is pretty centric to BPF. So I just want to clear up in case anyone's unfamiliar, just quickly. BTF is the BPF type format. It's not exactly a debug format in that it's meant to represent just type information so that the programs can be loaded by the kernel. So it's different from Dwarf. You can kind of think of it, it does have shared ancestry with CTF. So it's sort of a ugly domain-specific cousin of CTF. And as Cooper showed with the core relocations, you need also BTF for the kernel itself. So you've got sort of, there's really, even though it's domain-specific in terms of you generally need BTF for BPF programs to be able to load the program, in order to load the program correctly, you also need BTF for the kernel that you're loading it on. And so in GCC, you can generate this for any target. It's the default for the BPF backend, but if you wanted to generate it for other targets as well, you could just pass GBTF. The only constraint here is that we're only dealing with C. So if you are running the compiler and you're running it as a C++ compiler, don't do GBTF, because you either get something incorrect or I think it'll just say, it might ice or say sorry. It just says no. Oh, it just says no. Good. That's what it just should do. It should just say no. So in terms of what BTF actually looks like, it looks like this. It's a lot like CTF in terms of you've got some source on the left and you've got the BTF for it. You've got different, you've got your integers, you've got structs, you've got pointers. There's forwards for the forward declaration of A there, and functions, function prototypes, and they just say, here's the function, here's the return type, here's the argument types, and then they refer to each other. Yeah, yeah. So the big thing, most recently, I guess, I refactored a lot of the BTF implementation in GCC just because it was getting, BTF has grown a lot over time, similar to BPF, and so it kind of became a pile of hacks of adding things into the implementation that weren't there in the first place, and it got very ugly, so I rewrote a lot of it to make it less complicated and easier for myself to maintain and to extend as they keep adding things to BTF. And there were a couple of nice bug fixes in the process. So there was an issue where BTF has these datasec records, which are sort of like they record for different sections what variables are in those sections and how big they are so that it can pass that information to the kernel BPF loader or whatever other BPF loader to correctly allocate space for the variables in each section. And in the old implementation, there was actually a bug where if you had things that were variables that were completely optimized away, so you have some variable that you declare in the program and it gets, I don't know, constant folded or whatever, and it doesn't exist at all in the resulting object, the intent of BTF is to represent what's in the resulting object, not what was there at source level. And so we had erroneous datasec entries for variables that were at the source level but had been totally optimized away, and then there were still entries in the BTF claiming, hey, you've got this variable x in BSS that you need to allocate space for, but actually x has been completely removed and constant folded. Another thing here is that there's a better cut between what's going on in the early passes and what's going on in the late passes, and that's something that we're going to be dealing with in the future because right now you can't generate BTF with LTO or you'll have problems. So that's great. Make it less complicated, make it easier to maintain, make it easier to extend. And then we can immediately throw that all out the window by complicating things again. So this is gprune BTF, which is an option that was added earlier this year. And the motivation for it is basically, this is an example of a self-test from the kernel. And this compiled, compiling with GCC, compiling with Clang, generating the BTF, and then comparing them. And so GCC on the left, you can see for this one self-test, and this is an extreme example, I'll admit, but it was generating more than 8,700 types in the BTF. And so the BTF section was absolutely huge. And the kernel people are saying, what's going on? Why are you wasting all this space? Whereas Clang is only generating 56 types for the same program. And the reason, really, is these includes. And so as a general thing, if you're a BPF program that you're loading into the kernel, the BPF program is going to interact with some kernel data structures. So you need definitions of those kernel data structures. But typically, your BPF program is only interacting with 1 or 2 structures at most, and maybe it has to read a field and write one other field. But by pulling in these headers, you end up including thousands of types. And because internally in GCC, we have the internal dwarf die tree as the canonical debug representation, all of that was being translated into BTF. And so you end up getting all of the types from all of the headers that you've included for your BPF program, even though you need to access just one structure. And so it became pretty common that with just the kernel self-tests, we're getting a magnitude of 10, or an order of 10 size increase in compiling with GCC versus compiling with Clang. And digging into that a little bit, I began to realize that really we have 2 modes of BTF generation. On one hand, there's generating BTF for a BPF program, which is you want as little as you possibly can have for that program to be loaded correctly by the kernel. But on the other hand, you need all of the BTF information for the kernel. And so you've got these 2 different modes where, on one hand, you want minimal BTF so that you can have a small portable thing that loads quickly and is verified quickly. And on the other hand, you need everything. And since we are supporting BTF not just for BPF programs, but for anything, the hope is that eventually, when you go to generate the BTF for the kernel, you can just do that directly with the compiler. Right now, you can't do that because the linker doesn't understand what to do with BTF. But currently, what they're doing is you need BTF for the kernel, you generate dwarf for the whole kernel, and then you translate it into BTF using PA-hole or some other tool. That's kind of an annoying process for everybody involved, and it takes some time. So enter this new option, gprune BTF. Basic idea is just to try to find out what that minimal set of type information that you actually need is, and then only generate that. And the catch here is that Clang does this unconditionally. And so we need to be, ideally we would be compatible with what they're doing so that people aren't getting unexpected differences in the type information. So a special thanks to Yang-Hong Song, who developed this on the LLVM side to help make sure we were compatible and doing the same thing in terms of this pruning. And it turns out that they really wanted this to be on by default, so we did it for them. You can turn it off if you want. But in terms of what it actually looks like, it looks something like this. So if you've got some struct that you're pulling in from a header, and then the BPF program, the only thing it ever does is it reads through a pointer, it reads that that my pointer, arrow X, right? And so inside of struct C, you've got a pointer to struct B, and B could be some massive common data structure in the kernel. But if in this program you never actually use anything in struct B, you're only pulling in the type because it's part of some other type that you want to use. Well, you can, instead of generating all of the BTF information for structs for B fully, we just replace it with a forward that says, you've got the struct C that you're using, you have a pointer to struct B, but you don't actually care about the contents of struct B. And so this is basically the idea with the pruning, is to say, starting from what you actually use, what do you need, and anything else that you can get rid of, you get rid of. And so that resolves the big size difference. Gotta quickly check the time here. Okay. Yeah. Well, I'll need it. So the other big thing that is missing in BTF at the moment is type tags and declaration tags. And these are fairly kernel specific. The The issue here is that there's a lot of semantic information associated with types that isn't actually encoded in the type system in terms of things in the kernel. And so the reason that you want this is so that you can pass that information to the verifier. So if you've got some pointer that comes from user space, and you've got a BPF program that is interacting with a data structure or something that has a pointer like that in it, you need to check in the verifier that the BPF program is not doing inappropriate things with that pointer. Yeah. I can, oh.
So just a few comments about the verifier.
Yeah.
There's no specification for it, right?
No. No. It's implementation defined.
Okay, so two questions. One, I was wondering, Cupertino may be better for this. How big is a typical core program? Because all these, are they ever generated programs or what? Because verifying the relocations. Yeah,
so typically BPF programs are quite small. You load them for like some specific hook that you care about,
okay.
Right?
Okay, and the second one is, how much does the verifier do with BTF anyway? Or is it unspecified and it may do more at some point? Because you sort of answered it.
It's pretty much, it's unspecified and they may do more at some point. So one of the recent things that came up actually is they want the ability to say that a pointer type may be nullable, like the value of this pointer at the entry to the function may be null or it can never be null. And that was something that they wanted to have that information in the verifier to correctly analyze the BPF program.
Brilliant, thanks.
But there wasn't any way of representing that until type tags. So the mechanism that they've devised for this is to basically have this way of associating arbitrary user strings with types or with declarations in the program. And then those strings are recorded in the debug information for use by post-compilation analysis tools, most particularly the kernel verifier. The thing is, though, that this isn't just BTF specific. You also need it in dwarf because you need, to get the BTF for the kernel, you need to go through dwarf. And that means you need to represent all of this in dwarf. So how do you do it? Well, there's a clear ideal way, which is that you treat a type tag, a type annotation, whatever that may be, the arbitrary user-specific thing, well, you just treat it like a const or a volatile, right? And that's the natural way of representing it in terms of these dwarf dies, for example, that you just treat it like it's a const or a volatile. The problem is, of course, that any implementation, anything that's doing anything with dwarf, if they don't know what this annotation die is, then it breaks, because you can't follow this type chain. So what is happening today is this format where they've got the annotation dies emitted as the child of a declaration, or for decal tags, it's just the child of a declaration, and that's simple enough. But for type tags, what they've done is said, hey, we only care about this right now for pointers, so let's make it the child of a pointer with the semantics that it applies to the pointee. And that doesn't break dwarf, but then there are cases where you have some type that's not pointed to by anything and you have no way of representing that. So we discussed this and we brought it up and we said, hey, what if we kept a similar thing, but instead of the semantics that it applies to the pointee, we'll say, just make it a child of whatever type it applies to. And that's great, because now you can represent the annotations on any type. So you've got some simple pointer to an int, and you've got a tag which applies, in this case, to the pointer itself. But you could just as easily move the tag and apply it to the integer base.
Just to get this clear, the annotation here is acting like a sort of paint that applies to the pointer, and so anything which points to that pointer is assumed to have that annotation. Where normally you would assume you would expect to represent this by putting the annotation in between the variable and the pointer. You've done it by sort of attaching the annotation to the pointer and painting the pointer with that annotation.
Yeah, to not break dwarf.
Oh yes, but this certainly makes it interesting to parse the resulting BTF.
Yeah, because ideally you would have something like this where it's just like a const, right? But that breaks dwarf. So this is an improvement because we can now, we can represent these annotations on any type. But then, what happens if we do something like this, where we've got two integers, they have similar tags, but now because we've attached them as children of the type, if you have the same type with different kinds of annotations, well, you have to duplicate it, and then you have to share, you have to duplicate the base type, and then have a bunch of different annotations, a lot of which are exactly the same information. So in this case, we've got the BTF type tag, tag1, in two different places, and it's not shared. And So it breaks, you know, it doesn't break dwarf, but it's not great. It's wasteful. And so this is sort of the agreed upon thing that we're going for next. But it's not actually been, there's a patch series for it in LLVM. I have a patch series in it for GCC, which when I sent, there was the very clear complaint that, hey, this is wasteful, maybe we can do better. Since it's not into the mainline LLVM and not into GCC yet, well, there's time to improve. And so recently, this is including some of the feedback that we got on the original version of the patch series. This might actually end up being basically the same proposal that was come up by someone at Cauldron last year. I couldn't attend, but I heard from Cupertino. But the basic idea is, what if we add, in addition to a new dwarf tag, we also add a new attribute? And that attribute just holds a reference to a die, if there is any, and then we can chain them together by using the attribute for the annotation that points to the dies that hold the actual information. And then if you've got a whole bunch of things that are shared, well, we can share them. So the basic thing is, it looks something like this, where rather than being a child of the pointer type here, you've added this AT annotation that points to the die, and that die holds the information. And consumers which don't know about the annotation can safely skip it, because there's a whole set of rules for extensions to the dwarf attributes that as long as you obey these things, then it can, you know, you're safe. In this case, because it's just a die reference, consumers can safely skip it if they don't know what it means. And now, going back to some of the waste, right? We can actually reuse these things where we've got, rather than having the base types that both independently have the same tag1 annotation, we just have one tag1 annotation, and then we have a tag2 where it's needed, and then we chain them together. And so for the X declaration, it's an int, and then it has an annotation of tag2, and then it has an annotation of tag1. And for Y, it's just got the annotation of tag1. And so that's great, because now we're sharing and reusing, and it turns out that a lot of the time you've got a whole bunch of different types in your program that all have exactly the same set of annotations. And so with this format, you only need those annotation dies once, and then you can share them. Yeah, Nick.
There is another problem with the previous implementation, which is if you've got two translation units, one of which has has both of the same type, and in one of them it's annotated, it's tagged, and in the other one it isn't. You can't deduplicate those together because the types have the same name but different annotations. And you can't, with this representation, you can just have the annotation hanging off it, and some variables use the annotated version, some use the unannotated one. With the previous implementation, that's impossible. You have to conflict them all. Space wastage, and generally a nightmare.
Is there a question up in the back, or is that just pointing? Okay. No. Oh, there is. Okay, thanks.
What would happen if you had a third line that would say int __ tag2?
In that case, yeah. So in that case, there are some cases where it's unavoidable to have duplication. So if we had a third declaration here that was an int z, say, that was only tag2, then you would need a separate tag2 that doesn't have an annotation chain. But there's at some point, there's a level where you can't really avoid some amount of deduplication. And so this works with ints, which is great, but of course it works with any other type also. So this is the same thing, but instead of another int, you've got some struct pointer, and it could have a whole set of other annotations or other types before it. It could be, you know, a pointer to a pointer to a pointer to a struct. But right at the end of the day, you're just using these same two annotation dies. And so you can have, you know, n different types that sharing the same annotation chain or the subchain. Now, another interesting aspect of this is that the ordering is actually preserved. So in this case, we've got the ordering of the two tags, tag1 and tag2 here, is actually important. Because if you switch the ordering, then you would have the chain of annotation dies be the other way around. So that's something that it's not clear whether that's useful or not. If you decided that you didn't care about ordering, then we could do some additional deduplication, because you wouldn't need a chain of dies that is, you know, tag2 points to tag1 and tag1 points to tag2. You could just say they're the same. But that's something that it's not clear yet whether we want that or not. So that's sort of where I'm at. I wanted to finish a proper, proposal of this. The problem right now is that the implementation with the child dies, that's been implemented in LLVM, but in GCC there's been pushback saying, the dwarf format is bad, let's change it. And so this is sort of an alternative approach that I think addresses those concerns, and hopefully, if this makes sense to people, then we can go ahead and do this and then bring it to LPC, bring it to the LLVM people and say, hey, here's a better dwarf format, let's move forward with this. So that's what I'm hoping to do if I don't, get it. Yeah, change it again. And they'll be mad because they'll have to change it again, but.
It's like CV quals, which is obviously wrong.
Yeah, it's like CV quals in a way. And I've already written the dwarf part of this. I have a patch that implements it. I haven't done the translation step to BTF yet, but just from writing the dwarf portion of this, it's very natural in terms of the code to actually get this done. And to me, it just kind of, it smells more right than the previous approach in terms of the previous approach is ugly to implement. So that's usually a good sign that it's a bad idea.
So something that probably is this ordering preservation thing, which with qualifiers it doesn't happen, right? It's more like a set that.
Right.
I think that if we decide that we want to have it as a set, I think we should make GCC to actually swap, even randomly, to make sure that nobody relies.
Yeah, we could take a page out of that.
Serious proposal, yeah.
Okay.
Yeah.
Yeah.
Right, to avoid that.
I think from what I've seen, I think there is some interest in keeping the ordering preservation for some of the kernel attributes that they want to use, but we'll see. I think it's kind of neat that it preserves the ordering, but it's not something you should necessarily rely on, because at the source level, these are just two attributes that apply to the same type, and you're not guaranteed which one comes, first. Logically, they just apply to the same thing. So that's sort of it for the tags. That's where we are at the moment. Hopefully patch series for this coming, and then we can move forward and say, hey, this is a better format. Let's implement this also in LLVM, and then we have an agreement, and we're good to go. So, isn't there supposed to be? Oh, whatever. So turning the page a little bit, that's kind of everything that's been done until now. That's where we are today. And I don't know why my section transition slide didn't appear, but up at the top you can see this is moving over to open items and future work. So the next thing that we'd like to do really is to have proper BTF support in GNU Tools like we have for CTF. And that's something that likely we will need to do anyway if we want to support LTO and BTF, which we do, then we're going to need to have a linker that understands what to do with BTF. And because of the relation between BTF and CTF and the commonalities between them, well, a great idea is, hey, let's just use the libctf support that we've got that already knows what to do with CTF, and BTF is very similar. So let's go ahead with that, which I think Nick is going to talk about. Is it tomorrow? Yeah, so see Nick Alcock's talk tomorrow, and there'll be more information, I think.
Yeah, the dumping is also something that will fall out.
Yeah, the dumping, as Nick just mentioned, the dumping is also something that will fall out of that.
I'll add the BTF dump format as well, because at the moment it's got a quite different dumping format for CTF, and arrange to be able to use either with either of them.
Okay, just going to quickly go through the last couple of things, because I think Jose's got a little bit to talk about, and I want to leave some time for questions. But there's also the issue of that, in general, for BPF, we're compiling for something that we're compiling for this verifier. We're not really compiling for an architecture. And so the problem is that we can emit code, we'll generate code that is valid and does the right thing, and the verifier doesn't understand it. And then it rejects it, and it rejects valid programs. And it becomes a big annoyance because the code generation depends on what happens in a lot of the middle end passes, and at any time there could be some new optimization or even just a bug fix that causes GCC to emit a different set of instructions, and now it's one that the verifier doesn't understand, and what used to work gets rejected. Sam, yeah.
How modular is the verifier implementation? I mean, could we? Yeah,
Modular?
I know, right?
It's one function.
Because it would be interesting if we could have an optional checking pass where we ran the
Right, so ideally we have some formal set of, these are the things that the verifier verifies, you know, these are the rules that it checks, and then we can sort of have some sort of pass in the compiler that does that, but that is kind of, that's a huge can of worms. And
that's the other thing I was going to ask.
They're never going to do that, and they're never going to stop improving the verifier, or, you know, improving. But so there's been prior talks on this. You can see, I think Jose talked last year about the challenge of compiling for verified targets. We haven't really, you know, made much headway in that realm, but it's sort of a future problem. And there's some other things on the horizon. Jose, do you want to talk about this? Or?
Well, just very quickly. So BPF has a memory model. Is Paul here? No, he's coming for the kernel buff. So BPF has a memory model. So basically you have a C compiler, like GCC compiles your C. It compiles it into BPF bytecodes, which can be seen as like an abstract architecture. And what is new now is that this abstract architecture, it has a memory model, which is basically is based on the kernel memory model. You know that the Linux kernel, they don't use the C memory model as such, but they changed it, and they are using their own memory model, LKMM, I think it's called. So since this year we got a memory model in the BPF architecture, then we had to adapt the compiler in order to actually do the right thing with it. And part of that was basically to generate something sensible from the different built-ins, atomic built-ins, like fetch and add and fetch, you know, like or, and so on. So we got it wrong initially, but in LLVM they got it wrong too, so okay, that's fine. So basically this is what is now in the slide is the latest version of it, that it's been right now being discussed in a pull request in Clang. That's the BPF LLVM hackers are working on that. And we have a patch for this that we will put in GCC as soon as the other part gets applied. And then there is a little add-in there, which is that now we need in BTF support different qualifiers for the types, like const, volatile, and so on. And now we will need a way, like Dorf has, like this atomic qualifier for types, we need to add them to BTF, and we will coordinate with the BPF people, with the kernel people in Plumbers.
No, I was
Oh, okay, so that's it.
Okay, yeah, I mean, that's pretty much it for slides, so there's some time for questions if people have them. I think there's, you know.
Okay.
It's blank for a reason.
Okay, this will be very fast because so there are more time for questions. Okay, so the maintenance model. Okay, first I got some notes here. The pseudo-C assembly syntax. It's a horror. It's a huge mistake, but it's there. So, but we will still fight. We will continue the fight. So BPF can still have, you know, maybe in the future some say in assembly syntax for doing assembly things, right? In assembly ways. Okay. Also, the ISA evolution on BPF and everything, those are not like, so to say, like Porphyrian categories. I mean, they have not been like that forever. Like I'm mentioning because Seger, you know, he made those comments. I mean, those different instruction categories and everything, they have originated like organically through time. So it's not something, it's not a design from scratch of an instruction set. So on that way, you know, it has to be understood. For example, core. Now we have core, but there was a BPF pre-core era. And in that era, the BPF programs will include kernel internal headers, but not compiled to BPF, but compiled to those headers were the headers for x86 or for MIPS or for ARM or whatever. So you can imagine what world that was, right? So now it's much better with core, even if core is ugly, whatever. Yeah, okay. Yeah, so the maintenance model. Now we have a little problem. Right now, in practice, the people who are using Clang and LLVM to build BPF programs, particularly the people who has like big BPF programs on the wild and working ones, at the end of the day, they feel they get forced to fork some particular version of Clang that happens to emit verifiable code for their particular BPF programs. So this is a problem. This is a big problem that of BPF in general and of the Clang BPF support in particular. So we are trying to think slowly and, on the GCC side, how to do it better, how to make it better, and also, if we manage to do it better in Clang, they can start doing it better too. So part of that is the maintenance. So for example, now Faust mentioned that many distributions are actually packaging GCC BPF and GNU Tools BPF. As far as I know, Debian, for example, Doku will correct me if I'm wrong, but the Debian GCC BPF package is pulling from GCC mainline, right? For 14, but you also have some patches, right? It's not GCC 15? Are you sure? No? Okay. Okay, well. In Gento, it's also 14 or 15? It's 14. Okay. Okay, so as people start using the compiler, we can expect, I guess, that they are going to hit the same kind of problems that they are hitting with Clang in that sense. So we will be talking with the other GCC maintainers about this, but we are wondering what maintenance model could actually work best for BPF in particular. Like if it's always pulling for master and keeping branches, or I don't know. But, I mean, this is something that we can discuss.
But yeah, otherwise, that's it. Thanks.
Last 2 minutes.
Yeah. Oh, there's at the back. Up in the back, yeah.
You had a slide that were talking about GNU BTF for the duplication, and 2 points. You were BPF programs, we can get rid of the duplication. Oh yeah, that's the one. And then point number 2, you say PAHO-like. So, correct, without the GCC support, if you wanted to add the BTF section to kernel, when you were building the image, there was a phase that PAHO was running, processing some dwarf information, and transferring it back. So with this support of number 2, there is no need for PAHO anymore?
There still is need. So first, there's the aspect of linking, where the kernel is built out of many objects and they're linked together. And right now, the linker doesn't understand. But even supposing that we get that completed, there's PAHO or PAHO, I still don't know, is doing a little bit more in terms of there are some things that it adds into the BTF section for the kernel specifically that it knows about that in the compiler we can't do correctly. And so even, and I think the PAHO people would be happy to do this because it also has a BTF reader. So in that future where we just generate BTF for the kernel directly, then PAHO will still have a place in terms of we output BTF and then it modifies some and adds whatever is needed. And so it reads in the compiler emitted BTF, appends a little bit or adds it or whatever it does, and outputs BTF star, modified BTF.
The linker deduplicated BTF.
Yeah, the linker, yeah. So, otherwise I think we're out of time. Yeah, thanks.
now it's on.
Can you hear me? Okay, sorry. Sorry.
May I start recording? May I start recording?
Record now? Okay, it's fine, yeah. Okay, so let's start. My name is Qin. Yeah, so I think this is my third talk in Cauldron. So I work on the GCC security feature improvement for the Linux kernel for several years. Yeah, this talk basically is an update for the last year's plan, which we described in the last year's Cauldron slide. So some of the concept I didn't list here. So if you have any question on some of the concept, just let me know. Yeah. Okay. So, how to page down? David. So I cannot use the arrow. Sorry. Oh, okay. Thank you. Yeah. So the outline today is first status update for last year, then give some more detail on several interesting items work on for this year, and then to-do list for the next year. Yeah. So in this table, there are several new security features I added or will added very soon for the Linux kernel into GCC. So most of them relate to the flexible array member, to the array outer bound issue for flexible array member. So most of them already finished and under review. The last one is some improvement for the diagnostic. So I have some slides in the later for more details. So so if you want to get more information, of these items can go to the last year's Cauldron slides, at least in the bottom. So so let's start the status update. The first item is flexible array member-related features. So from last year, we have 3 items, and I think we finished all of them. Yeah. So the first one is to accept a structure with flexible array nested into another structure. We accept it as a GCC extension in GCC 14. So the second one is accepted the flexible array member in union. Previously, we didn't accept it as in union, but the Linux kernel has a strong request here, try to accept it in union. So we improve the GCC to accept this extension in GCC 14. And then the next big item is add a new attribute for flexible array member. Because flexible array member has issued this in the IR, in the language you don't have any information on how many number of the element of that array. So it's very difficult to catch the outer bound error by the tools. So one important improvement is add the size of the array into the IR. So as we discussed, we decide first add a new attribute counted by to the flexible array member. So we already finished it and added this new attribute into GCC 15. And this attribute also is already used by Linux kernel in mailing, in their source code. So you can see the the reference in the bottom, yeah, there are a lot of usage in the Linux kernel right now, and they catch real bug already, yeah. So, yeah, during the adoption of the counted by into Linux kernel, they have a new request to request GCC and clone to add a new built-in counted by reference to ease their adoption of this new counted by. So I will talk a little bit in more detail in the later slides for this new item. There are 2 old items we are trying to work on, but due to the lower priority, so I haven't started yet because Linux kernel currently don't need them. Yeah. So yeah, so for the flexible array member task, we finish I think almost all the issues. Yeah. So the next item, yeah, from last year is try to reduce false positive for array bound warning. Yeah, there's one bug filed by Linux kernel which inhibit them from turn on the array bound warning by default. So we have a long discussing with Linux kernel folks, and finally I convinced them that's not a GCC bug. Actually, it's a real array out-of-bound warning in Linux kernel source code. So they try to fix them in the Linux kernel, but looks like it's not an easy task, even in this kernel, to fix this real bug. So, but during the discussing on this issue, we noticed that GCC has some general improvement is needed in this area to improve the GCC's diagnostic message to provide the user more information on why this kind of warning happened. And yeah, so we have some improvement in this area, and I have an implementation ready, yeah, under review. So the third item is try to improve the integer overflow detection. Yeah, last year, after discussing, we identified these 3 items. The first one is try to add a new option, unsigned integer overflow sanitizer. Yeah, and the second item is try to make the signed integer overflow working with wraparound behavior. Yeah, and the third item is try to add a new attribute for specific function to control the granularity of the, yeah. So there are some requests from the Linux kernel, but within this year we don't have any progress in GCC because the KSPP project decides to waiting for the experiment between the clone and the Linux kernel because there has some special requirement from the Linux kernel. I will explain a little bit later in a later slide. So, so we think maybe it's better to do the experiment first in the clone, and then if it's successful, then GCC will catch up, yeah, in this area. Yeah, so this is a slide to describe clone actually made very good progress in the integer overflow detection area. They provide both sanitizer for signed integer overflow and unsigned integer overflow. It's already available. I believe it's in clone 18 or 19. And the second, they support the signed integer overflow combined with wraparound. So that's in clone 19 already. And the wrap attribute I just mentioned, that one is under review right now. It's not checked in. Actually during the their study, the kernel guys study, they need some idiom exclusion in the compiler, try to help the adoption. Linux kernel has I think Linux kernel, they have some source code try to do the integer overflow detection by themselves in the source code or around the source code. So they call them idioms. So if the compiler integer overflow detection combined with their source code integer overflow detection together, that will have a lot of issue. So Linux kernel don't want to eliminate their available idioms for the overflow detection code. So then I think this part is very tricky. So that's a part I really don't know whether compiler should add them or not. So currently, Clang, in Clang, they already finished this 3 idiom exclusion. And already put back into Clang. So I will see how these 4 items combined together, whether they can eliminate the integer overflow detection, integer overflow bugs class completely. If they can, maybe, even it's tricky, maybe GCC still need to consider this. Otherwise, so any questions so far?
Just one question. So I remember it was a few months ago, there was this interaction on the mailing list with the kernel people. And Linus was very much against tagging various functions as requiring these semantics. What's happening with that now? Because the whole thing, this is so kernel specific, right? Because we already have sometimes people file these bugs with these non-default sanitizer options. And I'm worried that people might end up, writing these things and then complaining that their specific idiom isn't supported. And I don't know, it just feels like there's going to be a bit...
Actually, I think this is a common issue. Not only for the integer overflow, I think for the array outer bound, they also have the same issue. They have the Linux kernel have the source code catch the array outer bound themselves because they know the source code better than compiler, so they add those kind of checking in the source code. Then later, if they try to use the GCC or Clang's tool catch the integer overflow or array outer bound overflow, then there are some mismatch confliction because they have the source code handling, but GCC and the compiler can catch it. So so this part I communicated with the kernel people a lot, but looks like convince kernel people to change their code is very, very difficult. I know Linux, so the Linux, the Linux kernel founder, he pushed back this kind of elimination, very strongly. So so I don't know. I don't know. I try to convince them. That's your source code need to be changed, but it looks like it's not an easy task. It's not an easy task. So that's I just watch, whether the Clang experiment in Linux kernel can be successful or not. If it can be successful, then give us some motivation to do it. Same thing in GCC, So so that's an update for the last year. So I'll give some more detail on several interesting items. The first item is counted by attribute for the flexible array implementation in the GCC 15. The second one is a new request from Linux kernel. It's called a new built-in counted by reference. So the last one is, some detail on the diagnostic improvement to provide more hints about the compiler's duplication on the compiler warning message. So the first item is counted by attribute. So let's go over the current design of the counted by attribute. So for this structure with the flexible array as the last field, the buffer, we add a new attribute counted by. No. So the number of the, previously the buffer plus flexible array buffer don't know its size, but with this new attribute, we know its size will be specified by another field in the same structure. That's a size field. So this size field, must have an integer type, and if it's a negative value, then treat it as 0. In the beginning, we only accept the positive value, but later Linux kernel request, we handle the negative value because sometimes they use the negative value as error code. So, but 0 and the positive value will be treated as a size. So they can reflect in their code to eliminate this requirement, but handling it in GCC is not hard, so I handle it to treat it as a negative value as a 0. And then we have two requirements. So that's a requirements for the pair of the two objects. So with the new attribute, so there are two objects for one structure object. So the first object is a flexible array object, and the other object is a size object. So these two objects must meet two requirements. The first requirement is the size object must be initialized before the first reference to the flexible array object. And the second one is the flexible array object must have at least the number of the size object number available all the time. So these two requirements is a requirement to try to make the behavior defined for the users of the size object. If this one of the requirement cannot be met, then the behavior of the consumers of the counted by. There are several consumers of the counted by attribute. For example, the bound sanitizer or the dynamic object size. Their behavior will be undefined. So this is a summary of the counted by attribute. And this is an important feature of the counted by attribute. So this feature is also requested by the Linux kernel. So the reference to the flexible array member field use the latest value assigned to the counted by field. So in this example, there are two references, reference 1 and reference 2. So the size is assigned before the reference to it. So every reference just use the latest size assigned to it. So this feature is used by the Linux kernel has a pattern try to dynamically extend their array, flexible array. So this is for that purpose. So,
Could this counted by attribute be eventually applied to function arguments? Let's say a function receives a length and a pointer to actually array elements.
That's the next step. I will talk about a little bit. So during the implementation, we have.
So I just wanted to make a comment. For function arguments, you already have attribute access, which pretty much does what you want.
Yeah, I also explain it in the slides later about the relationship between the counted by and the access and a local size attribute. Yeah. So yeah, we have we observe an issue. Yeah, so the current IR in GCC cannot express the implicit reading of the size information in the consumer. Yeah. In the line 9, you can see the built-in dynamic object size. Actually, when compute the object size for the object buffer, that reference, it will try to read the object size information. But that reading, implicit reading, didn't represented in the IR. So if it cannot be represented in the IR, the compiler optimization might apply different optimization, reorder them or hoist them. So then the wrong transformation might happen. So this is a major issue during the implementation. So in order to resolve that problem, we have a lot of discussion and finally decide to introduce a new internal function to carry the size information in the IR to the flexible array object. Then with this internal function, the size information is explicitly represented in the IR. So the data dependence is preserved in the IR, then no wrong transformation can happen. So so this is some detail about the new internal function. The second argument is the size, reference to the size. And the first one is a reference to the original object. And the last 4 parameter is other information needed for the size reference. Yeah, so I will not explain in more detail.
This is presumably in Gimple, not in RTL or any other later stage?
Not RTL, this is Jimbo level.
Right.
Jimbo level, yeah. So this internal function actually is a pew, and it's a leaf, and a non-throw. Yeah, so that's a feature. And it returns the first argument, the reference to the object, same as the first argument. Yeah, so this is an internal function. We try to add it to resolve that issue. So then this explain how this internal function resolves the missing reading issue. Yeah, so for every reference to the flexible array object, in C frontend, we will replace every reference to the flexible array member with a call to this new internal function. And in this new internal function, the size information will be encoded over there. So the explicit data dependence is encoded in the IR. Yeah, so then in every consumer of the size information, for example, the bond sanitizer or the dynamic object size, they will query the size of the buffer from the arguments of the internal function. The second, I think it's the second argument is the size, yeah. And after the size information is useless anymore, that's most situation is in after the Gimple state, after the middle end, in the expand phase, we will replace every call to this internal function back to the original reference to the object. Yeah, so that's the basic design of this new counted by attribute. So the status is we already committed into GCC 15 on this May. And the remaining task is, there's 2 remaining tasks. In last year, we plan to use this information to improve the dynamic object size to calculate the whole object size for structure with flexible array member. And the second item is issue warnings. If the requirement, we mentioned previously, the requirement is broken in the user source code. We try to implement these 2 items, but due to the other things, so these 2 giving lower priority, so I haven't started them yet. So the item have higher priority as this one. Actually, this is a new requirement from the Linux kernel to add a new built-in for their purpose, because during the adoption of the new attribute, they made this problem. So this slide explain what kind of problem the Linux kernel have during the adoption. So from the structure A, the structure with the counted by the left side, so before the counted by attribute is added, the Linux kernel has a macro allocator, object allocator, as I explained on the right side, without the size information for the flexible array. It just alloc the size and then assign to the pointer. So that's the current allocator in Linux kernel. So when they try to add the counted by attribute in the source code, then the major issue is after each allocation, when they call, every time they call the macro, they have to add open-coded initialization after the allocation. So that seems only 1 or 2 is okay, but there are a lot of places in the Linux kernel call this macro. So add them every place seems not, it's too tedious and error-prone work. So they request this new built-in to help their adoption. So the built-in is very simple. Just giving a flexible array, please return the corresponding counter field for me. So giving, if this built-in available, then they can just change the macro, the allocator macro in one place, and then, so I think the motivation is very clear here, so I think it's very reasonable to support this request. So, so after a lot of discussing, we finally decide this interface. So for this built-in, we will try to return a pointer to the corresponding size object if this flexible array have a size object associated with it through the counted by attribute. If there are no such size object existing, then returns a void pointer, non-pointer. So the type of the void is also decided after a lot of discussing. In the beginning, I tried to use the size T pointer, but later, after discussing, we decided on the void pointer, void pointer, non-pointer, to help them you try to use the generic. So with this new built-in counted by new built-in, the previous object allocator can be adapted with 2 more lines. Yeah, so we can use the generic to choose the what are the type returned by the built-in counted by. If it's returned void pointer, then do nothing. If it's returned other size of the other pointer, then we will assign the counted by field. So by this simple 2 lines, we can resolve the issue for the Linux kernel adoption. Yeah.
Just being an idiot here, I guess the advantage of that over just having a conditional is that that's completely compile time. I guess the advantage of that over just having a conditional is that this is completely compile time.
In the compile time, yeah, in the front end.
There's no conditionals at all at runtime, it just knows automatically how to assign the count. That's very nice.
Yeah, it's completely evaluated during the front end. Yeah. Any more questions?
Do you have an assignment to null?
Generic.
Okay, I will believe you that that works. I'm worried that there's an assignment to null, but
actually, this code is provided to me by Martin Euchre. Yeah, she is very familiar with this coding. So, personally, I have to, admit.
There's no assignment to null in that. You read that as if this is a void star, then assign to this to the address of this literal 0, which is just allocated there. It's not a null. So it assigns it to a temporary and throws the temporary away.
Thank you. Yeah, it's compiled well. Yeah, it's compiled well. I know it. Yeah.
If you just used if built-in counted by ref equals is non-zero, then assign it. Then it would be illegal code because you would still assign if zero code to the void point.
Yeah, I think the programming, the source level programming model, actually we discussed for quite some long time. Even till now, I think myself cannot fully understand this coding here. It's, Martin Euchre provided this coding to me, So I think, in my testing case, it's working very well. So I think this is the right approach to do it. So the status of this built-in, actually, I already submit several versions of the patch. So I think the first patch, after first patch we have a lot of discussing. So I think all the issue we already resolved. So I just sent out the 5th version before the conference, and I'm waiting for the approval. So hopefully it can be approved very soon.
When does built-in counted by ref get lowered to or converted into? Because it'll be converted into something.
It's in front end. In C front end, it's just the C parser just saw this built-in, and then it will decide. It will check whether it has counted by. If it has counted by, then just return that field, the counted by field, to replace this built-in. If there's no counted by, just return a non-pointer.
Very early in the front.
Very early. Just as handled in the C parser.
Right now, it's a keyword in the front end.
Keyword.
It's not a normal built-in. It could actually be an overloaded built-in, like we have atomics and various others. But the thing is, it can be normal built-in because its return type depends on, and in this case, not even on the arguments, but on the actual counted by attribute.
Yeah. Yeah. Okay, let's move on. So, yeah, we are done with flexible array. So now we are, this item is we try to improve the diagnostic to provide more hints on the compiler code duplication. So it's, hopefully I can explain this a little bit clear with this simple example. So this example, you just notice, there's two cosine assign in the second routine. So that two cosine will be inlined, and then some optimization will be applied. Then the optimization called jump threading. So that jump threading will duplicate code. That duplication, introduce the warning. Actually, if we compile this small example, with the latest GCC, you can see a strange warning for the line 13. Line 13. So the user will be very confused. Where is the warning come from? Actually, after we study, this is a real bug. This is a real bug. It's to catch the source code has an issue, because when the line 5, when the line 5, this one, is evaluated, then the index will be larger than 4, and then it will 1. But if it 1 and exit, then there's no issue. But it is only 1, but still continue the execution. So if the index already bigger than 4, you want it, but you still continue reference the array, then that's out of bound, right? So the compiler catch the real bug for the out of bound, but it's very confusing to the end user. And this, sorry. So hopefully, this slide will try to explain a little bit why this compiler do this duplication and how this warning introduced. So on the left side, you can note, please focus on basic block 4. Basic block 4, you can see from basic block 2, there are two go-to. The first is an index bigger than 3. The else is index smaller than 3. So both of the branch, they go to basic block 4. So on basic block 4, the index could be smaller than 3 or bigger than 3, so it's not known. Then the reference to the array will be, because compiler don't know, so it cannot issue any warning there. But on the right side, after the compiler optimization, the duplication, the code duplication will be applied, and then the basic block 3, you can see the index will be larger than 3. So on the basic block 3, the index will larger than 3, and the basic block 4, the index will be smaller than 3. So the reference, the red one, I emphasize the red one, that reference inside the basic block 3, the index will be larger than 3. So the compiler, actually can issue the warning, definite warning, is out of bound. So that's a real warning, but currently we didn't provide more information to help the user understand why this warning come from. So in order to provide more information to the user, we try to add a new option, diagnostic explain header, for this purpose, to provide more information in a warning message to report where such index value come from. So this is report, the warning message with my current patch. And from this warning message, you can see very clearly the compiler report under what kind of situation. Under the event 1, when the condition evaluated to 2, then this array out of bound will happen. So then the user will come back to look at their code to see the line 5, has this, then it will help them to identify where their source code have issue. So here, thanks a lot for David help. So the patch. The implementation is actually simple. We just add a new data structure, copy history in the middle end. And this data structure tries to record the condition and transformation for the code duplication. Whenever code is duplicated due to different transformation, we'll record them into this data structure. And during the array out of bound checking or other warning checking, the warning checker will query this data structure and use it to form a sequence of diagnostic events to report the path of the warning message. So I think this should be a very nice improvement in general to the GCC, and not only in the jump threading, I think other loop transformation, those duplication transformation can also all be extended to add this one. But this is under approval. So Richard is not here. Richard, no. Richard Burney.
So I was going to ask, why is this feature hidden behind the flag? Is it just because it's experimental, or
what's your question?
The diagnostic try harder? It seems like as a user I won't know that flag, so I won't benefit from it. So why is it not just enabled by default? Better diagnostics.
You think it's better to be on by default?
It's a question.
Yeah, I hope so. But the first step, we will try to keep the default behavior first. Then later, if it's really helpful, we'll turn on it by default. Jack.
I'd like to point out that the warning is actually correct or not false positive or false positive really depends on what the code is doing. The thing is, that's basically the main design issue with the Midland warning is that they run very late, and therefore they do want to be dependent on the optimizations, but the optimizations are actually not done to make warnings better.
Actually I agree.
And so they run into problems with the optimizations, and often the better the optimizations are, the worse the false positives are.
Yes, that's true.
In this case, even the extra diagnostics, whether it's useful to the user or not, depends on if actually the user wrote it that way in the source. And that might not be the case. You have different situations. Either the user, for instance, knows that the index can be higher than that and put the if conditional in there and expects that the index above that will be higher, and in that case the warning is good. But it could be just that you use some inline function written by someone else, and that someone else is just trying to be extra cautious and tries to protect something against some problem, and just uses some conditional somewhere, and it doesn't relate to the caller at all. And in that case, the jump threading will work again and will do the same thing. And in that case, it will just confuse the user because it points out something that really isn't in the source. And it's the thing about the middle-end warning is that they often use the VRP information range. In this case, it's not there. There is just jump threading, which turns this code is conditional under.
So jump threading is much earlier.
But generally, how the middle-end warnings and the late warnings use the VRP is, if you don't know anything about some value, it's varying, then you don't warn because you would warn all the time. And if you know that the value is not a single even value, so you have somewhere some check that checks it's not 42, then you suddenly assume that it's possible that all the other values will appear there, and that might not be true. And in that case, you warn, and often that's false positives. So the question is whether to do anything about this at all, because it's hard to find out if the check which the jump threading is done on is coming actually from the source or from some optimizations found out.
If it's come from the source, we also can mark whether it's, if the duplicate, then we can mark which one is originally, which one is copied, right? So the copied one will have, we can check later, this is copied, then it might be a false positive or those kind of things.
Yeah.
We can mark it.
Two questions or observations. Firstly, am I right in thinking the explain harder flag is a way of avoiding paying the costs of building this data structure and storing it in terms of compile time and compile memory? It's an sounds like it's an optimization.
Yeah, that's right.
And I don't know if you've measured the cost and if it's true.
No, not yet. Not yet.
The other thing, one, and in terms of the discoverability of the feature, if it's turned off, but if it had been on, we could have done it. We could issue a note saying, note, recompile with -f explain harder to get more information, and that would let the user easily discover the feature.
Okay,
The second,
I think maybe, it's time, if you, because I still have a lot of slides, so if more questions relate to this item, can we postpone to after the meeting? I still have some slides, after the slides, sorry. So so this is the implementation for this one. It's very simple, I think. So current status is, so maybe more discussing on this. So this is a to-do list for the next year. So also 3 items. The first one is, just ask, whether, we will extend counted by to general pointers. That's the first item. Then we'll try to re-implement the attribute, the available attribute access a local size with the new internal function. That's one of our goals. And also the arithmetic overflow detection improvement. And the last item is the KCFI. So for the motivation of, we will, all the array, we can classify into 2, fixed size and dynamic size. So dynamic size has variable length array, flexible array member, and a pointer, general pointer. And you can see fixed size, variable length array, the bounds, all in their type. For flexible array member, we just add the attribute counted by. So the size in the attribute. But pointer, there are quite some pointer arrays. Right now, there are no way to specify the size. So our next item is try to extend counted by to general pointer. So there are two major cases. The first one is a pointer inside the structure. As in that small example. So we can add a similar attribute, same as the flexible array member. The second case is pointer passed as function arguments. So the example shows it. And as Sid just mentioned, it's the same. Currently this feature can be covered by GCC current attribute access. So the access attribute did the same thing, just with a different name. So because it's already available, so our next focus will on the first case, the inside structure, pointer inside structure. For pointer passed as argument, we'll not do it right now. So the next item will be re-implement attribute access and local size. If you want to get more information, see the documentation for these two attributes. So these two attributes will try to carry size information for the pointer as argument or a pointer as a returned value. So the access is attribute try to represent the size information for the pointer argument, and the alloc size attribute is try to carry the size information for the returned value from a function. So currently, they already available in GCC, but they have some problem. You can see all this this PR. This attribute information lost after IPA optimization, after the inlining. So during the discussing of the counted by, we all agreed the new internal function access with size actually can be used to re-implement the access and local size attribute. To carry the information in the IR and survive the inlining.
Does access with size have a location saying where this came from and use the source? Like why? Do these access with size calls to the internal function carry with them where this came from? As in, did it come from a counted by? Some particular line
not
number,
counted,
or an access.
So that's you asking whether the diagnostic later will. I think this is if in the implementation we replace that one with access. The access with size internal function, we might need to carry the location information during the replacement.
So the user knows why the compiler is complaining about this access rather than just this access is bad.
I believe in the real implementation to use the access with size, re-implement access and local size, there will be some more detail we will figure out at that moment. But right now we think the access with size should cover the major issue, but there will be some minor issue.
In the current internal function, you can put the source code location on the function call. That's easy, and you can. There is the -1012 argument that can be extended as bit mask or something. But I would say there is a problem with replacing the access attribute with the access with size, because the thing is, access with size is used on all the references to the flexible array member. And the problem is that access attribute doesn't work like that. It's only about the
parameter.
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 So it's not about all the uses of the parameter, but only about the value of the parameter which was passed to the function. So, and another thing is that
but it's still an association with
the pointer might not be addressable.
Yeah,
so
I still think
you need a different internal function, perhaps similar, but which actually takes an SSA name rather than a pointer to it, and you need to associate just the originally default SSA name in the function. So only the value it was passed to the function, because you can do anything. The function arguments are like any other variables. You can change their values. You can assign them anything else to them, and the access attribute doesn't apply at that point anymore. It's only on the function boundary. So if you want to put it on through the inline functions, then you need some internal function which will hold the association that this SSA name, which originally was the default one, the parents D one, is associated with this SSA name, which is the value of the argument. But otherwise,
yeah, maybe we can discuss after the meeting.
We have 3 minutes left.
Yeah. Okay. Yeah. So the the overflow detection will watch the clown's experiment. Yeah, the case if I don't think I have enough time to explain the several slides, so maybe just jump. So the control flow integrated, it's a security mechanism that I think most people might know. If it disallows the changes to the original control flow graph, for binary. So the CFI technology, currently we have two different CFI. One is forward, one is backward. Forward means the forward jumping. Backward means the backward jumping, that's a return. The forward including all the other jump, branch, call, indirect call. So there are references for more detail. And so there are concept of the precision of the CFI. There's a coarse grain and the fine grain. So coarse grain means all the function in the compiled program are allowed, and also all the address taken are allowed. That's a coarse grain. The fine grain, will be finer. So with the same prototype, you can, the C, D, E, F, just finer. The C is all with the same prototype. D with the same prototype and address taken. E, even finer, only the derived class, that's for the C++, or if the compiler analysis more accurate, the point to the class hierarchy, we can point to the exactly set, that's more accurate. So this is the precision. Then, I don't think I have time for this. So the current support in GCC and the clown, the hardware support all the coarse grain part. So GCC clown provide the x86 and the ARM64 support for the hardware instruction already. That's for all the address taken function are allowed. And the software support, the fine grain, and this one actually requested by Linux kernel for several years already. Clown already supported, provide two tools. One is satellite CFI, and that has some issue. So later the other KCFI, that's specifically for kernel purpose. So they request the KCFI implement in GCC for at least 3 years already. But till now, nothing provided in GCC. So So I raised this in GCC community, yeah. So a patch previously by Li Dan proposed on last year March, but that one had some discussing, but later gets dropped because Dan left. Yeah. So then there's no progress on that project. But we need this project going on to provide the KCFI for Linux kernel from GCC side. So yeah, I'm not sure whether help can be get from the GCC community on this project. Yeah. So that's it. That's it. Any question? Yeah. Do I have time? No. No.
There's half an hour break. So now there is half an hour break, so you can like discuss, but
yeah.
It's a break.
Yeah, it's a break.
didn't see it, but during your talk, I thought, this might be really easy because you've done all the hard work.
All the information already there.
Yeah.
I think it should be integrated.
The other thing I wanted to say was I'm very happy to see the time.
Explain how.
For the diagnostic bus. You are the first person who has used that. Having said that, Andrew McLeod, I know, has been playing around with it as well for Rangers. And he is trying to store information about what Rangers decisions or the diagrams of the activity parts together. And I think we should talk to each other. But I suspect what it is no, I don't think so. I don't think it's here. I think we should reach it, your thought. Maybe more something. We can find Richie.
I need to find
your patching, and then actually use your work as a basis for, and then have Rangers support. Maybe. I don't know, I'm just, rather
Now? Hello? Oh, I can hear myself now. Okay. Hey.
We can hear you as well.
Okay, cool. So, it's time to start. I suppose Jeff Rowe and Jeremy should be there, but anyway, I can start first.
I'm pretty sure there will be 20 more people coming in over the next 10 minutes.
Okay. Okay. Anyway, welcome to the RISC-V booth. We don't have too much concrete agenda today, but yeah, only few things I have put in the slide. I mean, I will spend a few time to show you what's new in the trunk compared to the latest GCC release for the RISC-V. For what we have now on trunk is we have better constant synthesis, which is mostly contributed by Jeff Rowe. He has a lot of interesting magic around the constant stuff. And also, we have more mature backlighter support. Also has support early exit loop. Of course, we only port in the backend stuffs only. I mean, I remember the backlighter part is done by Fox. I forgot the name. But anyway. Okay. But anyway, we bridge we added the missing part in the backend, so it's work for RISC-V as well. Yeah. And also, we have Intel friends to add in bunch of saturation operation support, who is Li Pan. He is working on adding bunch of middle-end stuff and also the back-end support. So in case if you are not working for RISC-V, but you can still benefit from that by adding some more pattern in your back-end. Yeah. And also, this year we have trying to add in more security stuff in the RISC-V backend. One most important thing already in the trunk is the stack crash protection support, which is contributed by the Bentana folks. And another thing is bfloater 16 support. Yeah. Basically we are trying to learn from x86. Yeah. And a lot of improvement for utilize the DBS extension. Okay, so what's the plan? I mean, what's the thing we plan to do to include it in the GC14, 15, but not included it? The first one is hardware CFI support. I have a talk for this in tomorrow's afternoon, so in case you are interested for that, welcome to join my talk. Yeah, and another one important bit for the RISC-V is function multi-version. In the last year, we have the taggy attribute. It's kind of fundamental thing for the function multi-version, but yeah, we didn't did anything around the real multi-version yet. Now we are working from the taggy clone and the taggy version, which is should be same behavior in the definition in the ARG64. I mean, I remember they have support both as well. And RISC-V, we will support both. Yeah. And also another interesting bit is the fixed length vector coin convention. In last year, we have a scalable vector coin convention already there. And this year, we will fill in the gap for the fixed length vector since we realize one thing, fixed length vector still kind of popular in this world. So we must have some coin convention to improve the efficiency of the passing the argument for the fixed length vector. And that's what we're supposed to implement in the next GCC release. And of course, there are a bunch of the Cauldron improvements for vector plan ongoing, which will based on the banana pie. Let's borrow kind of most easier access in the world, I believe. you can just buy from the network and get one. It has support the full vector one, although it's sci-fi and it's not sci-fi CPU, but I still will recommend you to get one if you would like to play something with the RISC-V vector. Yeah. And also, there are some sub-items around. Here is some extra saturation handling and the zero stride loss store and the segment tracing mode and some misaligned vector handling stuff. Yeah. And the next one is kind of new stuff, which is pop up recently. The shortcut setting, short circuit setting. I mean, I forgot why we set into false before, but anyway, we will evaluate that soon. I assume, Jeff, you will do that, right? Yeah.
I'm having a hard time understanding the echo in here.
Yeah, okay. The short circuit setting.
So where are we? Short circuit. Sure, no, this is actually Palmer's patch. I got to do that, actually run that on design. I feel you have to take a microphone.
Yeah, okay.
Yeah, so that's actually your patch, Palmer. I've got it to do to actually run that on design. The thinking is, when I looked at this class of problems about a year and a half ago, the general conclusion we come to was we don't want to be crazy aggressive on the front end going into Gimple, but we want to be very aggressive on the back end if conversion. What your patch does is defaults back to the standard way we evaluate the short circuiting stuff. And I think conceptually it's the right thing to do. We just need to test it on design.
Yeah, I agree.
So I'm sure we'll get that sorted out in the next week, 2 weeks, whenever.
Yeah, I mean, it's a one-liner.
Yeah, it's a one-liner. It's the testing that takes time.
Yeah.
Hey, do you want me to talk about any of the other ones?
Sorry.
Since I...
Yeah. If only.
Yeah, and Jeff, I assume the next one is also aided by you.
Yeah, I think I put most of this in here. So on the code gen improvements, probably the biggest takeaway from that is now that there's some hardware out there, and now that within Ventana we're running a lot of this vector code on design, we are finding a lot of quirks, both in our design and in these initial boards that are out there. So we know that, for example, VXRM is, in a simple implementation, will be a pipeline flush, which you can assume will be very expensive. Mm-hmm. And that shows up anytime you want to use those half-word averages. So like a pixel average in X264. Zero stride load versus a vector splat, that shows up in MC weights. Is that right, Robin? Segmenting addressing tunable, that was one that you were looking at. Shows up on the Banana Pi. I think it's just bad performance, if I'm right. Yeah. And then misaligned vector handling, and if I get it wrong, Robin, please correct me. But one of the things we're seeing with X264's SAD loop is to get enough elements handled per vector op, and to get only do one reducing sum, you actually have to expose unaligned vector handling to the vectorizer. That allows you to unroll both loops, and you get really nice performant code. So we've kind of figured out SAD. We have not figured out SATD yet. That's Rob and I are going to be living inside of that probably for the next couple of months. And the last one, this is one of Robin's patches, if conversion. I think it's kind of pending on a discussion between maybe you, Richie, Richard Sandiford, and Robin to get sorted out.
I actually have a question to the Banana Pi evaluation. As I'm working on using SLP for everything, I run into the situation that currently we decide to use I think it's called struct load and struct store on RISC-V, which is load lanes and store lanes on ARM, right? Yeah. It's just called different. That the ARM vectorization relies almost entirely on the struct load and struct store. But in theory, it can also use the vgather with the register gather, or also, I think for some interleaving you could use the compress thing. So did you see if like is that struct store of like 8 vectors fast? I mean, it must be pretty awkward to implement that in a fast way.
Yeah, it's not fast right now.
So is it faster to load continuous memory and do a lot of gathers?
We're still trying to figure all that out.
Okay. Yeah, so I think this is one of the, I guess Jeff was kind of putting this somewhere up here, but RISC-V vector extension has a lot of fancy things in it, and the hardware does not go fast for all the fancy things. So I think we're starting to find that now.
When I look at the specification, my takeaway is that it has a lot of fancy things, but it lacks very basic things, and you have to use the fancy things.
This is the problem is that, and this is really the core of the problem, is that the fancy things are there, and so they removed the simple things, and this is a common RISC-V idiom, is to remove the simple way of doing something and instead replace it with, you know, some sort of idiomatic code sequence of fancy things. And that's kind of just hard for everybody, if that makes sense, because, you know, you try to filter it down to the simple version of the thing, right? But the ISA sort of loses that information, right? And then the hardware guys have to recover it in slightly different ways. And we're seeing that across the board in vector land.
So how does it work when the hardware designer implements the vector gather? Does it at somewhere in the pipeline detect, oh, that's just an interleave, and go a different path than the very generic end-to-end mapping? Does it do that?
That's the kind of thing we're actually discussing with hardware guys.
I mean, you're doing hardware. Are you doing this kind of stuff, or you have just fast generic permute thing?
That's what we're testing right now, trying to figure out what is going to be performant. And
but the vectorizer needs to know what you're going to implement, and not the other way around.
yeah, and we have not done any of that kind of modeling yet. No. Okay. We're still very early days because we are just understanding how the vector designs perform in practice. Because we can look at code, it looks fantastically fast. But when you run it on design, you find out that there's a quirk. There's always a quirk.
Yeah. So like right now, if you run vectorized code, like you run vectorized code like run spec or whatever on the actual hardware, the vectorized code will probably be slower than the scalar code because there are just enough performance quirks in any design that haven't been worked around that it's just not going to be a win. It's a bit of a bummer, right?
Yeah.
On the VR gather stuff, we're starting to see some more common idioms get added as instructions, right? Like they've got zips and compress and stuff, just got fast tracked a couple days ago, I think.
Hopefully going to be a transpose coming soon.
Yeah, right. So I think what we're starting to see is this general pattern of like not putting any of the simple stuff in the ISA is just going to get worked around by adding a bunch more extensions, would be my guess. And then we'll have a generation or two of hardware where you shim those through the generic flavors of the things, right? Kind of like the splat, right? The zero index load splat idiom, right? Where basically you use a zero offset into your index load to splat something, right? Like that is an idiom that kind of is a little clunky for hardware folks because it's through memory and whatnot, right? So you start to see these like patterns that end up being a little more complicated if you rely on pattern matching the generic version of stuff, and they're just starting to go in as extensions. So my guess is that the first generation or two of hardware, we're going to have super quirky performance models for all these things. Not so much on the like pipeline model scheduling side of things, because scheduling really doesn't matter in these newer cores, right? For the in-order ones it might, but for the out-of-order ones it really doesn't anymore, right? But just on the cost of doing an instruction sort of thing, right? Is there a big latency because you've microcoded it or dropped down to some firmware mode?
What happens with an L-ball? What happens with a segmented loader?
That's the other stuff. Is that, yeah.
So to put this in perspective for you, Richie, ByteDance was looking at just like a transpose, a 2x2 transpose, and they've come up with, I think, 5 implementations, but yet they don't have any they've run on hardware yet, so they don't know how any of them perform. They're looking at instruction counts. And their first proposal to me was do it in memory. I said, no. Not only is it bad in memory, it was going to be partial vector stores and partial vector loads, so you're going to get store forward bypass problems. Do it all in register. There's a lot of quirks that we're finding, and that's just the nature of first-gen vector hardware.
Yeah. I think it's pretty clear on the vector side that like we're very early in terms of people actually implementing the ISA, and we're in the longer run going to see a different way of doing things.
Now that people are seeing codes, now that we can take a code fragment and say, this is what the idiom looks like in CodeGen, I can now give that to the hardware team and say, is this performant given your expectations of this particular microarchitecture? If they go back and say, oh yeah, this is dumb, we're doing something stupid, they go off and they fix it. Some of the things are like, yeah, this is not going to get fixed right now. That's just the nature of first-gen vector hardware.
I think more broadly speaking, RISC-V as an ISA really isn't, if you want to do a performant design, it's really not RISC like an ARM type RISC where you have one op at a time. RISC-V is really way more like a variable length CISC ISA that is described as a series of RISC-like fragments. And a lot of the ISA is designed around detecting common patterns of multi-instruction sequences and merging them together some way in the hardware that stuff goes faster. That makes sense. And if you look at like the vector stuff, a lot of it really is like a 64-bit instruction encoding that's been split in half with there's a configuration instruction and an op instruction. And the configuration instruction gets really complicated. Jeff mentioned LMOL, right? There's a LMOL flavor that will like cause you to read and write the entire state of the machine in every cycle, for example, right? So like you get super weird at a certain point, and a lot of people who are not RISC-V processor designers, people who came from ARM land, saw it and said, hey, this is RISC ISA, I'm just going to, one instruction at a time, implement them, right, without so many canonical sequences and whatnot. And that just leads to bad performance.
So as of the ISA, it's probably that we have to wait 1 or 2 hardware iterations before people think about doing LVV 2.0, or maybe it's then just another extension on top of.
If the RISC-V vector spec was ratified saying something like, this is not going to change until 2.0, so I think maybe they want that one from the start, but it's a particular sticking point.
So I wait. It's rules. I feel the rule is still kind of changing to the 1.0 is already not as intrinsic.
Have version numbers. Yeah. So it's a whole can of worms over there. But yeah, no, I think what's going to happen is that there's going to be the base vector stuff. And unfortunately, the base vector stuff has a ton of complicated stuff in it, which is frustrating for hardware people, because if you start to add the common patterns as instructions, then you still have the complicated patterns. When do you do, like, microcode them or something?
That's also complicated for software people, because they can't make use of these complicated
And this is the problem is, and this is what I was talking about, is like it's kind of hard for both sides, because like, you don't get a clean description of what's fast. Instead you have these canonical sequences of instructions that are fast, but the canonical sequence is a little different between everybody's hardware, right? What exact flavors of things do you detect? So it starts to get to be this really mushy kind of meta ISO where like, yeah, you got all these instructions, but you can't use them. You can only use these certain flavors of instructions and really like flavors of multi-instruction sequences. When you start to get something like the VR gather, the generalized VR gather, right? Yeah, if you don't implement the generalized VR gather fast, then you've got to have the hardware pattern matching certain like flavors of constants to go into the register, right? And then the constant generation sequences are super long because we can't index individual register bits, right? Because they don't want any VLA stuff in the ISA, right? So it starts to get super complicated of like what exactly is fast. Yeah, if that makes sense.
And it wasn't until very recently, that the software teams are giving the hardware teams code and saying, this is what needs to run fast. That has really started the last few months.
I think if you look at like, moan about the ISA.
Yeah, I mean, it feels like all the time when CPU people design something and not talk to the compiler guys before they design something, because I always believed they would have a vector interleave instruction, because I mean that's perfect for a variable length ISA, and they have it. It's just called GADA, right?
Yeah.
Yeah, and I've worked on ISAs that had these highly generic gathers, but what we found was building some specialized ones was really useful. Because we found that the complex stuff we didn't need very often. Really, zip, unzip, 2x2 transpose, you get the basics right, and the rest just doesn't matter.
And like everybody else has the same set of common ones. Yeah, everybody else has the same set of common ones for a reason, right? They're just kind of what workloads do and what software people expect to have. So I'm sure we'll end up with them too. It's just going to take a while. We're almost like, this first generation of hardware is almost really like a generation earlier than you would expect from most shops, like an Intel or ARM type shop, because like the compiler guys and the hardware guys were at completely different companies, and not only didn't they talk to each other, they couldn't even talk to each other, right? Hardware guys will never tell you what they're going to do, and they all think they're doing the fastest stuff, right? So like, I think this first generation is just going to be total chaos, and because it's only been, what, 6 months or something since we basically had spec, not icing all the time, right? Maybe 9 months, something like that, right? So at that point, like, we're still really early on the vector side of things, and the hardware you see coming out right now would have been designed before spec would even build. So it was just totally open loop design. And if it takes, 2 or 3 years for the hardware cycle to really close, because even if you're doing a chip every year, it's not like you have a full new design of your IP every year, right? So it's at least a year if you do stuff real fast, and it's a little change, and then more like 2 or 3 if you're doing bigger changes. And a lot of these, like, more generic, like, structural changes in the design are way bigger, right? So I think we're going to have a few years of just totally wacky performance models before stuff generally starts to converge. And a lot of that's going to be new instructions and whatnot.
And what that probably argues, go ahead and take it up there, I'll just check. What that probably argues is that the tuning and other stuff we put in now, we throw away in a few years because it's going to be hardware that money has.
And this is something that's like, should we even just have like a, tune 2024 or whatever year it is type thing in there, right? Because then, I don't know, it's the same argument we had with the MTune generic, why we ended up with generic 000, because we didn't want to change generic because it was still aimed at the things that don't support misaligned scalar accesses, right? So it's kind of like, are we stuck with the flavor of tuning that we have now? Even if all that hardware is just, that's the thing, right? Like, but then somebody says, no, I've still got my PDP or whatever, and you're stuck with it, right? So that's kind of, I don't know quite what to do there, right? But I think this first generation of hardware is just going to have a totally chaotic performance model, and it's just going to be, like, I'm not even sure if we're going to have reasonable code gen if we try to target stuff that's not slow on any system. That makes sense? Just because this is going to be so fragmented, I don't really know what we're going to do.
Well, if you stick with simple loads, simple stores, simple ops.
But the problem is that we don't have... and we don't have the simple ops, right? Because we only have the complex ops. So if like everybody has a slightly different flavor of the complex op that's fast, and there's no simple op to back it up, what do we do? Like literally only the whole register loads and stores and maskless ops? The code gen's going to be horrific, right? So, yeah.
Then you end up with PowerPC.
Right, just assume it's 128.
They only have one implementation, though. One existing real.
Yeah, and this is kind of the problem. Does this devolve into, like, basically just some ancient SIMD thing where we just end up with 128-bit code gen and no masks, and that's what we get for a little while. I don't know. It seems backwards, but it is what it is.
I have another question. Is what's the actual plan to implement the target clone? Since now RISC-V is leak of the target can inline point, we can't deal actually the inline function with the target clone to make sure that a caller is actually devised by a colleague. How do we deal with this?
I don't think people are going to be running generic vector binaries for a while. I just don't think there's going to be that level of compatibility, because vector is really a performance thing. And it's not like it's a factor of 100 or whatever, right? It's integer factors on these big designs. So I think you're just going to see the vector code gen that people use just built for whatever CPU they're trying to run. It's some embedded thing. And the distros maybe have, FFmpeg and OpenSSL have their hooks or something. But I don't think the generic stuff's going to go in there. That's me, though. So.
Yeah, okay.
I don't think I've got anything else to say there. Yeah, I would expect the distros are going to pick something, they're going to generate code for it, but they're not going to dive into the details of how it performs.
Yeah,
That's just reality. And if I was building a distro, I would try to figure out where the market is going as opposed to targeting what's out there today. Because again, what's out there today is just weird.
Yeah, I think we see that. It's kind of like any other time there's new hardware floating around, right? It's going to be a ton of people doing it. A couple of those designs are going to win somewhere and survive for a while, and that's what people are going to pay attention to, and everything else is just going to eventually be ignored. I think we're just still at the point right now in our Scribeland where it's getting bigger, and we just don't really know where it's going to end up.
So Richard, don't waste any time on the vectorizer for I will ignore all assembly test scan phase.
That's not a bad place to be. Well, no, because I would rather the work you're doing, I think, is critically important. And I wouldn't want like a RISC-V scan-ASM test to get in your way, because some of those are just poorly written.
Yeah.
Plain and simple. So if you're finding those, go ahead and go forward, bull forward, and we'll deal with the fallout.
Yeah, I think a vast majority of our scan-ASM tests that are sort of just trying to match, because if you look at them, they're pretty clunky, and they usually just match like big chunks of code that came out of the thing to make sure it's exactly the same. Like it's just not sane to expect those to last forever. We need to have written better tests. That makes sense.
There's a general problem with scan-ASM tests that they often don't state what they want to test. It would make a lot more sense if there was a comment that a particular optimization should be happening, and then the scan for that. And then when you see it fails, then you can check if something similar is being done or something better.
Yeah, and that's, I think, the right word in that. A lot of the tests...
I don't care. Is this for the television? Or?
A lot of the tests don't even tell you what they're trying to look for. It's just a big blob of code that somebody said, this is what it generated last year, without any thought as to how that code might change or what it really should be, or even testing things in the sequence that just don't matter. And that's something we're just going to have to keep cleaning up. I know that Pam Lee just did a number of cleanups in the saturation test for that, and I expect we'll have a lot of that kind of stuff happening over the coming months.
But that's just code hygiene in general. And being a small port that not a lot of people have worked on, we have a lot of clunky stuff. Not just in the tests, right? So get through it. All right.
Other questions?
Yeah, I have no plans.
Okay. And we have a few more items, but I guess it's by Jeff.
Yeah, and maybe you guys can actually answer this for me, because I added this. I had looked briefly at the way we do branch shortening, and it looks like we're dependent almost entirely on the assembler to deal with the compression.
Stop relying on the assembler to do anything smart, if that makes sense. Right? It just leads to weird code gen. We should add some just give me the instructions flag. We have some like that no aliases type things, right? But an don't mess with my code, just assemble the instruction I wrote type flag, and then do the benchmarking to make sure we don't drop anything, and handle compression, and because the assembler expands out instructions, like makes single instructions, 2 instructions all the time. Right, we should handle compression in the compiler and just stop it. Like all we're doing is just papering over cost model bugs, basically.
Yep.
Right.
That's what I found, and I was I'll say I was disappointed when I found it.
Yeah.
And what I thought I saw was the compiler GCC would always assume everything is a full-size instruction, and the branch limitations are such that we're generating long branches in the compiler much more often than we should.
But it's all over. It's not just this one problem. It is a general
class of problems
that we have.
Yes.
And we actually did this early on in the design to make it way easier to change the ISA, like do ISA design, when there were just 2 or 3 people working on this thing. The idea was that we would just build a compiler binary, because building GCC's too hard, right? So we build a compiler binary, and then no one would have to touch it, and we could, do our drag racing for, glibc code size or whatever based on just touching the assembler, which is convenient, but, we don't live in that world anymore.
The other thing we need to do here, we added long call sequences and long branch sequences 6 months ago, 9 months ago, whatever it was. For big enough functions, those sequences will trash your return address predictors. That needs to be fixed.
Okay.
It's not the top of my list, but it is something our hardware guys have said, yeah, we'd like to see that fixed. And I agree with them. It's the right thing to do. The good thing is we could do a register scavenger and fall back to these sequences that potentially trash your wrap.
Yeah.
But I would expect scavenging to work 90-something% of the time. And so if it does, that's sufficient in my book.
Yeah, I guess maybe we'll throw a missed optimization or whatever bug over the wall and just talk about it over there. But that kind of stuff, like, there's all sorts of things when you start to actually look at the code gen where it's bad. We have a bunch of the stuff that's hidden by whatever the implicit, explicit relux stuff that's similar, right? Where you don't get, shared registers behind your multi-instruction sequences and whatnot. So, yeah.
So that was all I had on those two. Go ahead and move forward. I'm not sure what else I put in there.
I haven't looked at them, so I don't know what's going on.
That's all I have for that slide.
Yeah, okay, next one. Yeah.
So, it's the microphone.
It's made by you, right? This is just this is almost actually an advert for my lightning talk in a couple of hours' time. I think just as part of the BOF, we throw in a few things. We've got MBench 2.0 in final release candidate, and now there will be a paper coming out later in the year with everyone who's been involved in this. And I thought I'd just put up a couple of slides here. One is to look and just understand that we can see the benefits of different extensions there. First of all, obviously putting a multiplier in helps things go faster. Compressed instructions don't particularly slow things down, and I've put a couple of the Core 5 extensions on there, and they also show the benefit of extensions. You want to go on to the other one? This is probably more interesting. I've just looked at the history. I've gone back to 2017, which is the first time RISC-V was properly upstream, and I've compared the performance of the different releases over time. On MBench, and of course this is aimed at the very smallest microcontrollers. This is tiny little 32-bit, maximum 64 kilobytes. The MBench 2.0's got one or two slightly bigger kernels in them before. There's a tiny AI kernel in there, for example. What we can see there that is over the last 7 years, RISC-V is slowly converging on AI, both in performance and code size, but it's not yet caught up with ARM. This is ARM Cortex-M4, no floating point unit. Okay, I forgot one more slide. I can't remember. Oh yeah, and just show we do big stuff as well. This sort of speaks to what Jeff was talking. Up until fairly recently, the only way we've been able to look at optimization for vector is do instruction counting, and this is just showing impact of vector code generation on Spec CPU 2017. What you find is that vectors mostly aren't making a big difference, at least to instruction counts. There might be some performance improvement when we get real hardware, except for one or two things. So X264, where you get half the number of instructions generated, the Xallen C benchmark, where you get a fairly chunky improvement. And actually, in terms of instruction count, vectors actually makes one or two instructions worth. I think that's all I've got there. Yeah, that's it. But I've got a lightning talk where I've got rather more detail on performance measurements we've done on other things.
Slide. So let's look at that X264 case. That's about half the instruction count, give or take a little bit. With naive CodeGen, that probably performs about twice as bad as the scalar version. So that gives you a sense of what we're dealing with here. We cut the instruction count in half, and it goes twice as slow.
On any hardware that exists.
Yeah, and in fact, on that little banana pie, the way I choose to think about it, based on experience, is the more we vectorize, the slower it gets. So it's a terrible microarchitecture, but.
So for X264, it's the experience. The wider vectors you have, the slower it gets.
Yeah,
so it's a very quirky benchmark for the vectorization.
Yeah.
And even so for variable length, I would guess.
It's a much harder variable. What you really just want is 128-bit wide SIMD. Yeah.
That's all we really need.
That's perfect.
Anyway, I just want to make that comment that while the ICAS look great, performance can be dreadful.
Yeah, it was an interim proxy until we got anything better, and quite honestly, most of the work was on getting things functionally correct. This is a month or two old, and you'll notice that though there are 20 benchmarks in that particular suite, I've only got 15 sets of figures because I couldn't get 5 of them to work on QEMU.
Okay. I don't have anything to say. I don't know why Jeremy gave me the microphone. What do you want from me?
All the political questions.
Yeah, and there's kind of big issue around the GCC and the GNU recently. I mean, RISC-V Foundation has proposed one thing called the profile, and we are intended to support that since the client has supported that, but recently Palmer has some interesting idea around maybe we can have maintained another GNU profile.
Yeah, so the problem with profiles is that the profile is a list of extensions, and it says you must support these extensions. But if hardware doesn't support the extensions, they can still just claim that they're compatible with the profile.
So wait, we are not talking about profiling, right?
No. No, it's different, yeah.
Yeah, sorry for the confusion.
It's the same as x86 v123. Except that if you claim x86 v3 or RISC-V v23 or whatever it is, right, you just don't actually have to implement that stuff, which is pointless. Yeah, but it's just RISC-V, right? Like it's chaos, right? So my argument was basically that my original argument was basically that we should remove the extensions that are not actually in the hardware from the profile. Yes, this is for RVA22, which doesn't support misaligned axes, and the profile says it does, right? Or it doesn't support it on all of the chips that exist, right? I forget if there's any other issues in there. That's just the one I happen to remember, right? But then I thought, okay, why? It's not really our problem in compiler land, right? If the user says, I'm running on this design that supports misaligned axes, then they'll get code that supports it, or whatever the extension is. They're saying, I want code that supports this set of extensions. Just generate the code. It'll crash, but that's not really our problem. We did what the user asked for, so whatever. And that's what the LLVM guys have done as well. That's what kind of changed my mind, is that they're basically saying, well, that's not our problem. If we generated the code you asked for, if the sticker on your chip says it supports that thing and it doesn't actually support the thing, the bug's in the sticker, it's not the software. So I'd say let's just go merge 22, flip on everything that's in there, and then break users. And the faster we break users, the faster they'll go complain, and then hopefully it'll get fixed. Where we are now, we've been forever just papering over all of these issues in the lack of any actual compliance, and then the folks at the RISC-V Foundation say, oh yeah, everything's fine, don't worry about it, right? Whereas we just kind of disable all these random instructions that don't actually exist in the design when ISA says they do. I think we're just digging ourselves a hole.
So, I'm a bit confused. So are you talking about defining profiles, or I think when reading through RISC-V stuff on the web, I found is something like profiles, right?
So they're defined by the RISC-V Foundation.
Okay.
Yeah.
Okay.
Now they defined 22, fully defined, ratified, and whatever. But then they said something like it's a minor release and software shouldn't use it. So we have kind of this gray area there. This happens a lot with the RISC-V Foundation, where they say something and then they kind of back off for it once they find bugs. Right? It's the same where they say nothing's ever been removed from the ISA, and then they're like, no, nothing was removed from the ISA since we moved to Switzerland. And it's like, sure, right? That kind of stuff, right? So it's the same with 22, where we ran into these issues, and they're like, okay, it's a minor release, don't use it, basically. Right? So that's why we kept it out, under the assumption that it was just going to cause chaos. But this is the post on the mailing list that blew up. It's like, I think RVA23 is going to be exactly the same. I don't think there's any actual change going on. I don't think there's actually any compliance getting enforced. So we might as well just break users today, rather than waiting for another release and then waiting for hardware to come out. And we'll just do the same thing in a year or two, or whatever it is.
Well, without compliance testing, this is going to repeat.
That's kind of my point.
That's the key issue.
There's no compliance testing. Vendors, they call it vendor self-certification, which basically means that the vendors decide whether or not they implement the stuff. which is, of course, the vendor always says, yeah,
so
we implement it.
So one guiding principle about that topic may be that the profiles, so to speak, for x86 64 were created by the distributors.
And
well, that's exactly where I think this needs to go.
Yeah, exactly. So if you have basically, I understand that the set of profile currently existing for RISC-V is basically a gremium that decided on those profiles and then backtrack for real-world reasons, right? So that's never going to work in the end.
And this is my argument, is that we should just come up with profiles and call them GNU 2024 or whatever. I don't really care what they're called. But we should just decide on something that says, here is what the, because these are only useful for binary compatible distros, you know, Red Hat and canonical type folks, right? So, you know, if you're not in that world, you don't care. SBCs and stuff don't really matter. So let's just say, here are all the chips you might care about running those sort of things on that got released in 2024, and here's the extensions they support. And you pass GNU 24 or whatever, and you get stuff that runs on those, as opposed to getting stuff that runs on kind of nothing, I guess. I don't know.
But it does feel like it's a distro, that this lands in the distro space.
I agree it's a distro problem. The profiles have always been a distro problem in a distro.
So at this very moment, how many designs are there out in the world that can run a Linux distro? So not the small embedded ones, but the
well, that's the problem.
Is it the correct time to start defining their baseline profile? I mean, we do have the RV64GC, right?
And that's just de facto the baseline for all the distros.
But isn't that enough?
The problem is that GC is pretty bad in terms of just performance. It's missing the bit manip and missing the vector. So I would propose, whatever we call it, just add bit manip and vector.
But vector sucks, and we only have a single implementation. So it's way too early to pull that into any...
We have more than one implementation of vector. Yeah, they're just all suck. But there's more than one.
I only know about the K...
Yeah, the K1. The T-head cores also have it, right? And they have T-head vector, but the new ones have vector. I think the C90...
Performs a lot like the K1,
but with a slightly different set of pathologies. Yeah. Some of their performance problems are the same, but I think the segmented loads are fast on one and the strided loads are fast on the other, or something like that. Yeah.
So on the vector topic, as a distributor, I would probably disable vector because it makes things slower, right?
Yeah.
So I wouldn't include it in the profile requirement because
which seems reasonable, right? And I think that's where if we decided to do a profile today, I think that's where we would end up. We would end up with bit manip because that's in stuff, but not vector because GCB, or if they've actually decided to define B again. Yeah. They used to call it B, then they called it other stuff, and now they're calling it B again. So whatever, it doesn't matter, right? Everybody calls it B, right? But yeah, and that's where I would end up, right? You know.
I mean, if we only have this single profile, do we need a profile? We can just make config GCC to default to that. If the configurer doesn't override it, then it's the default. Then you don't need a profile at this point.
Yeah. No, I think
defer to in 3 years when you have more designs.
So I think, you know, and this is where we get into kind of the weeds here. It's maybe done better on the mailing list, right? But I think there are some very simple vector routines which we can generate code that's reasonably fast for everybody, like just mem copies and stir copies and stuff, right? Stir copy is less. Stir copy is less true. Yeah.
I have concerns about the string routines.
Yeah, the string routines are a sticking point, right?
The string routines have to use
first first loads. Yeah.
And then some of them have a read of VL.
Yeah. So the string ones are a little clunkier, right? But even having mem copy will buy stuff. But anyway, we can argue about which things are in there on the list. But yeah, that's basically what I'd say is let's go post on the lists. Here's our set. And like I said, it really is a distro problem, right? It's not useful unless it's what distros are going to use.
Right, and so we need to get input from the distros. So the SUSEs, the Canonicals, the Red Hats, that's what I think really drives.
And regardless of what we call it, it doesn't really matter. We just pick a name, and that's something we all agree that's going to be the exciting target, and we're going to pay attention for cogen and performance, because there's so many options in RISC-V now that you can't really pay attention to all of them for performance and correctness reasons.
So for the profiles, we have the RV820, we have the RV822, RV823 is about to be ratified, or is it already? So there are already a couple of profiles, A and B. When we say that's a distro thing, yeah, the distros can pick that. But if we look at ARM, ARM has also their ARM A ISO definition with different versions. They have 8.1, 8.2, 8.3, 9.1, 9.2, 9.3. So I think that's reasonable that the profiles exist and that they are supported. If they are adopted by distributions, it's then up to the distributions, of course.
Yeah, sure. I mean, I think that's what we talked about is, for the profiles, let's just generate the code that targets what the profile says, and then let users report bugs and close them.
Well, that's the forcing function.
That's it, right? We can make a Bugzilla type for, closed, please go yell at somebody else. yeah, whatever you want to call it. I don't really care, as long as it's someone else's problem, right? Usually when these things break like this, we consider it our problem in software land, and then we stop generating that code, right? With other stuff that's gotten removed from the ISA, that's kind of what we've done, right?
And I'll tell you that the higher-ups in Ventana would certainly prefer to see if the hardware is misbehaving, the align stuff is the canonical example.
Yeah.
Who cares? In 5 years, these designs that we're running on today are not going to matter.
Yeah. So let's just go with it.
I'm not going to on my desk in 5 years.
No. If you do something that's gone horrifically wrong. Right?
If I had Banana Pie on my desk in 5 years, I'm probably not doing RISC-V anymore.
And if RBI wants to set the profiles as some sort of feature thing, and the compatibility issues will sort themselves out by market forces having people not buy ones that aren't actually compatible, cool, it'll just take a while to get sorted out.
Yeah, but this is a forcing function.
Yeah, that's it, right? At least now, we've got the stuff there, issues are visible, and we can just worry about it later, right? And then if distros want to pick some sub-target, there's nothing right now that stops the distros from picking any sub-target they want, right? They can write their ISO string down, and they can pass, there's a -- with default march or whatever to autoconf that says, just build this, and that's what you get, and that'll be your default multi-lib target, and everything just works. So that's all there right now. It's just a question of whether or not we write something in GCC to give it a name, or we don't. It doesn't mean anything, if that makes sense.
Yeah, so if people think the committee-designed profiles are useful, well then implement them, but don't add don't add.
Yeah, I mean implementing them is the easy.
Don't add any new profiles that you invent right now, because you don't have any designs that people want to use anyway.
Yeah, which is.
Well, that's why we've deferred it for so long.
Yeah, and maybe the answer is just wait longer.
Defer it another year.
Yeah,
I mean, I can live with that. I think the only reason this is being pushed right now is because LLVM has it now.
Yeah. But that's the profile side of things, which will just do the same thing LLVM does and tell users to report the bug somewhere else, which is, I'm totally fine with that. I mean, I would be happy to not have to paper over all these ISA problems in software. It's a pain, so just stop doing it.
Have we killed this one for today?
Yeah, hopefully.
So you'll make the change and evangelize it, right?
Yeah, sure. It got posted. I will close all of the bugs as go away, or whatever it is. We have a Bugzilla for.
You're taking the arrows.
I will either way, so it doesn't really matter who closes them.
We have any more slides, Keto?
One more.
One more?
Oh, wait. Just this one is kind of.
Okay.
Yeah. It's kind of update. It's not really related to the GCC development itself, but it's kind of another script build. It's a script for build a RISC-V GNU tool chain, which used in the RISC-V community for a while, and we are still supporting the latest GCC release. GCC 13, and we are trying to upgrade that. And we are very close to merge, and not sure if anyone has used it. Hopefully this will be useful to you, since this provide you some preview image and also a very easy script to build a RISC-V GNU tool chain. Since you may know, build and usable tool chain is very hard. I mean, yeah.
And doesn't this tool chain, it builds QEMU, it builds, it's the whole ball of wax. So if you're trying to get started, this is the easy way to get started.
Yeah. Mm-hmm. Okay, and some is topic, I'm not sure who edited.
Yeah, I think I wrote most of this. Yeah, I started dropping stuff in. It might have been when I was in Amsterdam. Yeah, so the hardware probe work is in glibc now. Within Ventana, we have wired up the vRule work that was done for us a while back into that hardware probe mechanism. We've also taken the work from engineers at Revos with the vectors implementation. We've got those in Archery. So we'll get those upstream in the fairly near future. It's not the top of my list, but it's on me, so blame me when it doesn't go in.
And it works.
Yeah.
Our LVM guys didn't figure out how to actually call the hardware probe function. But
yeah, I've actually run it on hardware.
And by the way, we have...
something out I didn't think we had.
And not only did it work, it found bugs. The nice thing is, so once you wire all this up in glibc, the glibc test suite will actually query itself for what implementations you have. And so say, oh, you have an unaligned mem copy, you have an RVV mem copy, you have a mem copy with unaligned loads and stores, and it'll just test them all. And it found real bugs. This is something I've added as well, vector register access to GDB. If you're using one of these Banana Pis, do not upgrade from the V1 software because the V2 software does not give you access to any of the vector registers in the debugger. It's a pain in the rear, and I don't know why. It looks like there's at least a GDB bug and at least a kernel bug in there. I'm not currently chasing it right now. As far as I know, there is no hardware watch point support in GDB yet, which would have been really nice to have about a week ago. But, oh well. And then...
Watch my stuff, I think, is blocked on getting something that makes them available to supervisor.
Yeah, I figured it's mostly going to be kernel side work. I mean, I've done this kind of stuff in the past.
In this case, we also need something below the kernel because the watch points start out in debug mode. And something needs to say that you can defer them to supervisor mode. And that's what we got stuff on last.
Yeah, I'm sure we'll figure it out. I mean, this is not...
Just curious, does here some developer for RISC-V are working on the GDB part?
I don't have anybody right now. Okay. I was going to have to do it myself until Robin pointed out that it worked on the V1 BPI. The reason mine runs V2 is because of the hardware probe stuff. I need a newer kernel.
But curious, why we won't work by V2 now work is all upstream one or their own release?
I think they have their own branch.
Oh, okay.
No, they have a bunch of their own stuff.
Because I was able to take the GDB from the BPI V1, try to run that GDB on the V2 software stack, which has a different kernel, and it says, I'm supposed to be able to get hardware registers, but I can't read them. So pieces of it are in there. It's a mess. And then Valgrind, I think, is still a significant gap. I don't think any work has happened in terms of getting that upstream.
Yeah, I assume PLC has some work.
Maybe somebody has it fixed.
Yeah, I know a guy from Intel. He is doing the very grand support for RISC-V port. His name is Hai Chen. So you can connect to Jeff Shell to get his work info about the very grand.
Yeah. Do you know if they've had any success getting review from Mark and the rest of the Valgrind team? Because that was really the whole, the key work is done, but we haven't been able to get the review side under control.
Yeah, I remember they started that work half a year ago. Yeah. Okay. So I think they do make some progress here. Yeah.
Yeah,
but I don't know the actually.
He's here somewhere.
Yeah, here. He's here somewhere.
Yeah, I was looking for Mark Williard because he is the guy and he's not in this room. So I assume he's downstairs right now.
Yeah, okay.
But it is still an issue.
I think we are downstairs.
I think we're downstairs, right?
Oh, are we downstairs next?
No, I think we're downstairs.
Sorry. Mark is upstairs. All right, I'm very little sleep here, guys.
I mean, maybe Mark is really downstairs.
That's true.
Okay, no more slides, so anything would like to raise? Okay, Jeremy.
So you went very fast through the previous slide, the RISC-V GNU toolchain. What's the status of Linux multi-willib support?
Okay, Linux multi-lib support is there. You may know it's there for support for configure, but it's unlike the bare metal multi-lib you can configure by yourself. It's in a fixed set.
You can have two each of 64 and 32-bit, so long as they've got different ABIs. What I can't have is a multi-lib of a non-vector and a vector library.
Yeah, that's something we need to add.
And that would really I'm not sure. Craig, I'm not sure. Craig, are you actually working on that?
No, I'm just doing the
Yeah, but I'm also curious how we extend that mechanism. I mean, we are selected that by the ABI before, so I was thinking we may need to extend in that to support such scenario. Otherwise, I know we stuck there for a while since that's block people to adding more multi-lib to testing or do some concrete work.
Yeah, I think we just need another folder for the target. The hardware caps stuff should do it.
Yeah.
Right?
I would think so.
Hardware caps is the way to go in GLC. I think GLC hardware caps is the way to do it.
If it's in a library, HW caps are a great way to do this.
Wait, one strange question from me. Who is really responsible for the recertified glibc review?
I'll review stuff or any of the other maintainers.
Okay.
I mean, it's no different than anything else. There's a bunch of us.
Yeah.
What? 4 minutes.
Okay.
Oh, wow. I did not think we were going to fill the whole thing. See. Yeah.
Okay.
If stuff's not getting reviewed, then I don't know.
It's any reviewed where?
GLC.
Yeah, and Keto. Yeah, I think you should have to post it, Palmer, myself.
It's the same as getting any other code reviewed, right?
I think I am a reviewer for GLC. Carlos, are you in here anywhere?
Let's assume you are.
We'll work with that assumption. I'll say with Carlos, but I think I can review code for GLC.
Okay, cool. Yeah.
Hello. So I have a question. We have many extensions in RISC-V now, and I can't keep track of all of them, and whether they're supported and how complete the support is. So I wonder, so the motivation for this is I often get asked by a customer, is X supported in GCC version whatever? So I end up looking through release notes and commit histories and things like this and looking in the source files. I wonder, is there somewhere better I should be looking, or do we want something like LLVM has? They've got a RISC-V usage document, and that lists all of the extensions and whether they have assembly support or code gen support.
Did we ever merge that table?
Yeah.
There is a dash print supported.
In the GCC, there is an arc equal help. It's a simple way.
So that will give you the list of extensions.
Yeah.
We did actually merge it though, right?
Yeah, already.
Yeah, we have that for the architecture, for the tuning, for the...
Yeah.
More,
Let's be the same interface.
So that will give you the list of extensions, but does it tell you whether it's a complete implementation, whether there's code gen for all the instructions, whether it's halfway there? I know that's not necessarily an easy thing to answer, but someone must know.
It's always improving.
Yeah.
I mean, if you turn it on, you should get some instructions out.
If you know how to tickle it just right.
That's it, right? Like how many you get out is kind of, I don't know.
So usually the question is that I get is along the lines of how good is it or how complete is it? So that's at the GNU Tools level. That's can I assemble all of it? But obviously the code gen.
If it's in there, it's complete unless there's some bug we don't know about.
Yeah,
right?
yeah.
Just list them all.
That's the easy one to answer.
Complete in GCC is kind of what does it even mean?
Well, that's the wrong question, but what is the status? There must be a way to answer that.
I would say if the extension is supported, it's supported right now. How many instructions actually get out depends, on it's much more complicated, right? When Zcon was initially added, we were only generating fewer Zcons, right? Like those instructions, but then over time that improved. But if the compiler says I'm supporting Zcon, it is supported, right, from a technical standpoint.
Yeah.
Not just from a technical standpoint. If you have a code fragment
Yeah, so I think that, yeah. So complete isn't necessarily the right question. It's how good do we think it is? Or should I expect code gen, and if I don't, is it a bug?
Well, yeah, that's where we get into this, what set do we do for distros type stuff. Because really the only thing that's going to be decent quality is the stuff that somebody cares about. And that means either some embedded vendor is shipping that thing and working on it, or distro people are shipping that thing and care. So right now, if it's not in GC, you know, it's a lower quality bar than everything else. That makes sense.
And, you know, a great example of that, you just talk about Z-Icon, CB set.
The whole thing, yeah. I would anticipate that any of that new stuff has a bunch of misoptimization bugs that just need to be filed and fixed. Right, we're talking about vector being total chaos, right? So.
Okay. And I think it ties up. Yeah, okay. Thank you, everyone.
Yeah, should you tell them to talk to Jeremy?
He's the man to talk to.
The answer is
pay no attention to the people up here in the front.
Like that? Hello, hello. Can you hear me? Great.
Yeah, but so we would like to start the next talk.
Come in, close the door. I have to switch rooms before the next talk, so. Today I'm going to talk about refactoring done to the vectorizer to so-called vectorize with SLP only, whatever that means. And so at first I want to just introduce what is SLP. So classically SLP is the superword level parallelism. For example, in the code above, let me see if that somehow, it's a point, yeah. Here you see 2 lines of code where there is an obvious possibility of executing the 2 statements in one statement using vectors, right? So that's why it's called super level word parallelism. These kind of opportunities, they can happen within loops or also without loops in straight line code. And when you do loop vectorization, you usually need to apply the unrolling that's done implicit by vectorization in addition to exploiting this kind of superword level parallelism. For example, for this case, if your vector has 4 elements, then you need to duplicate those 2 statements once to get all your lanes in a vector filled. And when you exploit this during vectorization, you're usually doing that to limit the amount of unrolling you need to do to fill the vector. Because, as I will show in the next example, here you have a quite simple loop. I made it awkward on purpose, so there's, of course, so there's a superword level parallelism by means of this struct having the members adjacent in memory, so you can, in principle, load the data as vectors and operate on that with the same operation, and in this case, even with the same scalar loop invariant variable. What is awkward in this example is that we have 3 of them. That's not power of 2. Power of 2 is always nice to compilers, not power of 3 is bad to compilers. So what do you want to do? In Gimple, it looks like this. I marked in red the important parts of the loop body, which is only shown. So there's a block with a jump down here, and above here there's a different basic block with the pre-header and stuff like that. But the important part is this, where you see the 3 loads of the RGB elements and the 3 stores of the RGB elements and 3 times multiplication. Then this depicts the SSA graph, or some SSA graph of the example, which shows that there are really 3 independent bits, namely those that we can later execute in parallel with a load, a multiplication, and a store to the separate elements. So now I will show, don't be confused. So I was very bad at doing slides. You see, I wrote them, did circles manually, and I didn't get to trying to make this with transitions and stuff like that. I tried to make AI generate my slides, but I didn't succeed.
You need a better model.
I tried to. They all tell me, oh, I can't visualize graphs yet. Too bad. So I now took the 3 loads here, 1, 2, 3. So this is basically the SSA graph from 2 slides before, and I have applied unrolling and duplicated the statements, and it's supposed to be n times, because without SLP we need as many elements to fill a vector, for example 4, right? So, and what we can then do without SLP is we can load of the first set of statements, the memory in one vector. Actually, we have to spill over to the next statement to fill the vector, but we are basically loading memory in this direction. But then we are forming vectors out of all the R elements, because we have basically vectorized the first statement separately, as if the others weren't there. Then we are doing the multiplication. That's just a regular vector statement. But when we are doing the store, we are now taking the vector result, which is basically a vector, a vertical vector, so-called. But now we are trying to store the elements again into the R elements, which are also have a representation that's in memory with a horizontal vector. So basically, for the classical vectorization, you need to transpose your vectors all the time if you run into this kind of situation where the memory locations you want to work on are not consecutive in memory. or you can use Gaza. GCN, Gaza. Everything is Gaza.
No, we just learned it's not.
Well, with GCN, everything is Gaza. Yeah, right. So there are architectures that can basically do this transposition as part of a complex load instruction, struct load for RISC-V or load lanes for ARM, for example. I think those are the only two that GCC has implementations for these kind of instructions. So x86 can't do this. The transposition as part of the load, basically. So when you do this on x86, you get this. So I had to explicitly disable SLP in the vectorizer to get that code, of course. So you get 3 nice vector loads, perfect. Then you get lots of shuffling, 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 that's the transposition. And somewhere there's the first multiplication, there's the second, and there's the third. And then you get, again, lots of shuffles and the stores. Of course, I cheated, I only enabled SSE2, which needs many more instructions for the shuffle than if you enable later ISAs, but I wanted to show bad code. So with SLP, you see, I got really creative when doing the slides. So now you have to turn your heads this way. So that's the very same thing. Basically, the statements are of the RGB. Now they are still horizontally for the RGB, but the statements of the different SSA work sets are now vertical, so that I could draw nice circles. Right? So we still load the memory in a linear fashion with a horizontal vector now. And what we now do is we basically combine the arithmetic also into a single vector. So we are not splitting the 3 statements into separate vectors, but treat it as a single vector. That of course only works because all are multiplications. If one of those would have been an add, then well, it breaks down. But we now have all nice horizontal vectors, and we get nice code generation. Right, it's shorter. Shorter is always better. We know that from RISC-V. So QEMU would agree with me. So now you know what SLP is in the classical sense, super word level parallelism. It's nice to exploit. So in GCC we can exploit this super word level parallelism both in loop context, but we also use the same mechanism to vectorize straight line code. That of course only works when there are enough statements to fill a vector, because we can't unroll the straight line code. We don't want to duplicate work. But in GCC, in the vectorizer, all these SLP handling is handled by different data structures. And for the non-SLP, we have one separate struct that has information per Gimple statement. And with SLP, we also have data structures that basically represent a collection of statements, right? The superword, basically. And there's another data structure that basically tells us where this kind of graph of a sequence of the superwords starts, basically the graph entries, or the representing data structure for the graph of these nodes. So here I'm showing an example of a SLP graph. So you can see for each SLP node we have the set of scalar statements that is covered by the superword. In this case, the loads, the multiplications, and the stores. For each of the statements we have this other kind of data structure, the statement vec info. And then we have a single SLP instance that points to the starting superword, which is always the sink on the GCC side. So you could build the graph from both sides, but we are building it from the sinks. And then we also have a SLP node for this invariant. So basically, the graph of the SLP nodes is something like the SSA graph. So for each vector, you have the defining SLP node, and also for the invariants, you have a defining SLP node, which in this case just has the SSA defs and not a statement, because, well, it's an invariant. It was a function parameter in the example. So now what's all the issue we had now with SLP and not SLP? The vectorizer can actually mix that in a single loop. So if you have superword level parallelism opportunities and regular accesses that are just single statements, it can just handle that fine. Usually the single statements determine the unroll factor you have to apply, or rather the statements that operate on the smallest data type in case you have an ISA that has a fixed vector size, because then you need the most lanes for the smallest data type. And so when you have a mix of both, then it can happen that a statement is part of both a superword level parallelism opportunity, but also feeds into, for example, a store that is on its own and it doesn't have any SLP thing. So the statement gets vectorized twice. Once as classical vector with the interleaving and swapping, and once with SLP. And that's called a hybrid SLP mode. There's a lot of complex code in the vectorizer that just deals with this speciality. And I think I've rewritten it 3 times and it's probably still wrong. And it would be nice to scrap that. Then I've told you that there are some targets that can do load and store lanes, or the struct store, struct load. But we couldn't do this with SLP. And if you wanted to use load or store lanes, you had to scrap all SLP opportunities and restart without doing SLP. So we do this kind of heuristically. We look at all the loads and stores and see, are there enough opportunities that it's worth to scrap everything or not? And yeah, I have to think about how to do that with RISC-V, given that we don't know if the struct stores or loads are fast or not. We'll see. Yeah, so that's kind of a little bit awkward. Then there are, so I've shown you SLP opportunity with a store as a sink, but there are also SLP opportunities when you have a chain of reductions. So basically you have a reduction in the loop, but you add 5 different things to it inside of the loop. Then you can eventually feed the computations of those things you add as part of a superword level parallelism. That's then called SLP reduction chain, because the SLP reduction is if you SLP 2 reductions. Well, but that's going to stay, so good to know. Right? And if any of that doesn't work, then we have to basically tear that apart to be able to vectorize it with the non-SLP vectorization. And what also happened still in GCC 14 is that when you think you have a SLP opportunity at the store sink, but it doesn't really work for all lines, then we split the store group. But at that point, we were losing all the analysis we've done for the data references, because we now had 2 independent groups. And if we then fail the SLP, that will confuse the classical vectorization. I don't remember seeing a bug really running into this, but it should be there. So I've now fixed that, so we are no longer tearing this apart. So this is what the talk is about in the end. The goal is to only do SLP. Well, now you say, well, but if there isn't any super word I can exploit, why do I want to do SLP? No, I only want to use the data structure because I want to use the same data structures for every kind of vectorization in the vectorizer. So basically, we'll have superwords of size 1. Why not? Why not? Yeah, right. So that's what the first line says. Yeah, unify the data structures because and we use the single group size. And what allows us to do is that we can remove duplicate code because it is indeed the case that when you have a SLP, the routines like, for example, vectorizing a reduction has a lot of code for the SLP case and exactly the same code for the non-SLP case. Of course, not exactly because they differ in features they can handle, which is kind of, yeah, bad. Right? So when we unify the data structures, it drives also feature parity between those two schemes. And we are running into the situation that for the classical vectorization where we only have the per Gimple statement metadata, that this limits us in ways we can, for example, generate code in more complex settings. For example, with the SLP approach, we have pattern matching that only works when you look at 2 lanes, right? For complex ops like swivel and rotate and stuff like that. Or the vectorizer does pattern matching on the scalar code before the vector analysis, basically when there is a multiplication by a constant and the ISA cannot do multiplication, then we can do this with shifts and adds. And what we are doing right now, we are creating Gimple statements that are not actually in the IL, and then because we need this meta info for the statement, and we need to know that we are vectorizing a shift and an add and not the multiplication. And then you find code in the vectorizer that tries to walk over all SSA operands twice, once with the SSA operand scanner and once with walk Gimple statement, because those don't have statement operands. Right? So if we were using SLP, we could just add another SLP node. And we don't actually need the per statement info in that case for the node, because there's also no real SSA name for the definition of the shift result in the scalar IL. So it's not really necessary to track a Gimple statement when the value of the vector lane is not in the scalar code. You need to track the operation you want to do and the operands, but you don't need to track a real Gimple statement. Oh, I have to.
And as you said, it allows you to disassociate vectorization from the underlying Gimple representation.
So I think I've been working on this for 6 years. Or basically, I've started first time 6 years ago, then 3 years ago, and now I have started again, and I hope that I can finish it this time. So I've added SLP support where it was missing, because as I said, we have 2 code paths, and lazy people implement one and don't implement the other, right? Why not? Because who will ever have SLP, so a true SLP opportunity for weird operation X? I mean, you can write a test case. But yeah. So, and of course, if you treat now every statement as a SLP opportunity with group size 1, well, you need to implement it. So I've implemented that over the previous attempts and the end of last year, a lot of those, mostly in condition vectorization, because nobody would ever have a true SLP opportunity there in real code. For OpenMP and more cases, basically, you disable the classical vectorization and see what test cases fail. And then you chase them down, all of them. You try. Right? So, and now in the last 2 months, I've put to trunk actual use of these single lane SLP vectorization. So before, we've never would recognized the supervert level parallelism opportunity for a single lane because it's not there, right? But now I'm trying to enforce it, so when it works, use it to iron out the bugs and stuff like that. So basically we are now doing the SLP discovery because you can, at the moment it's basically a greedy process. You have roots, like for example, a series of stores that you've analyzed are continuous or with some gaps. And then you start a greedy discovery. Do the lanes all have the same operation all the time? Because when they don't have the same operation, you can't SLP, right? So I've added, question?
You could SLP if you could insert a select.
Yeah, we are actually...
It's a static operation, so you can select between two possible values. There's a limit, obviously, but...
we are doing this for adds and subtracts, yeah. So yeah, so that's, but SLP discovery is a whole separate topic. So just take it as magic, which it is, kind of. So I've added a discovery from roots that we didn't previously consider. For example, a single store or a single live induction variable or stuff like that. So, and I think we've now covered all roots, and we do discovery, and we try to vectorize it that way. But of course, some SLP opportunities still fail, especially in the area of variable length vectors. And so sometimes even the discovery fails, but I think I also fixed most cases. And yeah. So in principle, the single lane SLP discovery is just rewriting the SSA graph to a SLP graph. But it still goes through the multi-lane discovery routines, which have various checks that are in theory not necessary for the single lane, because we later verify if we can actually vectorize it. But it's still done, because it was simple. So, but now we get to the loads and stores and to my initial example, right? So when you have just a single lane load and you have a non-continuous access, that's a case the classical vectorizer would have handled similar as to I showed in the example, like it would load continuous and then swizzle the lanes, or use the load lanes and throw away one or two of the vectors that it loaded. Or on RISC-V you could straight load and then compress away the elements you are not interested in. So I had to somehow make the SLP work for load lanes and store lanes, because some ISAs want that. And the original idea of the refactoring was to get exactly the same code in and out, because it's just data structures change, right? Well, yeah, wishful thinking, of course. So I tried to replicate most of the quirks we had with the interaction between SLP and non-SLP, because only then you can get exactly the same code back. And the first hurdle was to implement the load lane and store lane thing. There is now a representation for that. You can look it up in, I think, a series of attempts I made on the mailing list, how it exactly looks like. It looks a bit unnatural, but I wanted to change the code generation part as little as possible. So eventually we will make the representation nicer. Plus, the current way the interleaving support works in the classical vectorizer is that basically the first statement does all the loads and all the permutations, and the next statement, so the load of the B and the G, When that gets vectorized, it just looks up the correct statement in a magical on-the-side way, right? And that's now done explicitly. So you have a proper SLP node that does the continuous load, and then you have explicit swizzle operations that extract the elements as needed. The classical vectorizer supports power of 2 sizes of the groups and a size of 3, because this pre-outlined interleaving thing is basically hard-coded, right? Yeah. And so I try to implement that one-to-one, but I also try to implement it in a way that is not tied to a specific vector length, because we are at the moment doing this before the vector length is supposed to be determined. It's already determined, but it's not supposed to stay that way, right? So I have to take it from a more generic point, so we generate different code at the moment. And there are still some gaps that the previous SLP code would have handled magically, because the target can do weird permutations, and my generic variable vector length supporting scheme doesn't support all of the cases yet. So, but the main good changes are that those store groups are no longer split up. So we basically preserve the important information for vectorizing the store. We are loading all of those groups first as a whole and unpermuted. That also allows us to share that load between different swizzlings of the same loads, which we didn't before. And then they are permuted. When they are permuted without load lanes, you have the explicit swizzles. When you have load lanes, you have a flag on the node that says, I'm load lanes. And you get magic permutes after that, that are basically the look up the thing and take it, and the load lanes will make sure that it will generate load lanes and nothing else. So it's a fixed decision, but it was before. So it should be really a more dynamic decision, but yeah, we have to work on that as follow-up. Let me check. Good in time. So what are the remaining bits? So on x86, it's not too bad. There are a lot of early break vectorization fails, but I heard it's fixed, basically. Almost fixed, because, well, Tamar was also lazy and only added non-SLP for early break. And then there is quite a few test cases which have the GOMP simple lane in the IL. They are mostly, I think, only from some weird OpenMP scan pragma thing that I don't really understand what it's supposed to do. Yeah. Jakob implemented the non-SLP version, so I'm hoping he will find time to implement the SLP or explain to me what it's supposed to do. Either of both. Then there are SLP load permutations when they are not of power 2 size and not of size 3. Like, those are the cases. 6 is basically power of 2 times. Yeah, 6. 5. So yeah. So basically, when the vectorizer sees one of these swizzling nodes, it can generate code, but only if it has at most 2 inputs. But you can imagine there are permutations where you suddenly need 3. And then it says, well, I don't want to do this. And we've resisted so far fixing up that routine to then, well, make it work with more statements. And I'm trying to keep to that. So I have to kind of try to make those work even without fixing, knowing how many lanes I have. Because only when I know how many lanes I have, do I know whether I will run into that situation with the 3 vectors or not. Right? Or with the VLA, I'm lost anyway, kind of. Yeah. So I have some ideas, but yeah. well, so this is basically cases where we now do the explicit swizzling for cases that are actually SLP, which we handled before by magic, because it happened to not run into the situation and having used complex permute instructions. But now we're trying to support the permutation in a VLA agnostic way, even on the targets where it's not necessary, and shoot ourselves in the foot, basically, and no longer support that specific SLP case, like for the size of 6. 6 is really annoys me, 6, because 6 is almost power of 2.
Like 5.
Like? So what is also missing, it's sad, but it's the case. So currently when SLP discovery, so we do SLP discovery, and everything that we didn't discover SLP, we are using the classic vectorization, and then we determine the unroll factor and everything, and now we are analyzing the SLP instances, whether we can actually vectorize them with the chosen vector size and so on. And if that fails for any of the instances we discovered, we are basically saying, okay, try without SLP at all. Because we can't really, at that point, remove a single instance, because that changes data we computed already. It shouldn't be the case, but you know, it is there. So that's how it works right now. So then we are doing without SLP. And there are quite some test cases that just rely on that, because, yeah, they rely on it. So, and what I didn't yet implement is that when we run into this case, that we are then simply trying to vectorize everything with the single lane thing, because that would be the equivalent to the previous behavior. And I think that will fix some of the fails we are currently seeing. So I said I want to kind of do what we did before, not do too many changes at the same time, because of course we should handle that better. Only do this single instance with the single lane if the others work, right? But one thing at a time. So test suite status. So I
still stand by my statement. Even seeing that.
What did I do here? I created a patch that basically, when we, at the final step, do the analysis of whether we can vectorize, if we run into any statement that's not in SLP instance, we say, no, we can't. So we fail, we hard fail, basically, at that point. It's not exactly the same, because there will, well, it should be, hopefully. It's some number, right? Some number. And I throw it on the CI, because that gets me regressions. When I do testing with QEMU, I would have to compute a baseline, and I use the CI. So on ARM64, there are 594 additional fails. On ARM, there's 207. I think ARM has almost no scan assembler test cases.
Yes.
Out of 50,000?
Yes, tens of thousands.
Yeah, but I mean, it's a CI, it's supposed to be green, right? So ARM has almost no assembler scan test cases for vectorization, or it's all green, so there are no assembler test fails for ARM.
Well, they're not being vectorized before, so it's making it difficult.
Or maybe they are vectorized fine, like on x86. There are 718, you have to divide by 2, because I tested 2 multilibs in this case. I grabbed out the equality, but this is basically C, C++, so everything. And I think the CI doesn't test everything, every library, or I'm not sure. I don't think those numbers are really comparable. Likewise, probably the ARM and RISC-V ones are not comparable. For the RISC-V CI, I only looked at that multilib. It has a lot more. And yeah, and I just grabbed the fail lines in what I got from GitHub, the log thing. It looked kind of okay. I tried to reproduce some of the fails, and I can reproduce them. For RISC-V, most of the fails are assembly test scan fails. I've analyzed some of those. There are quite a bunch of test cases that fail because of this select VL thing. So basically how the vectorizer handles the vector length setting. So as far as I understand, either you tell the set VL, the configuration thing, I would like to use 267 lanes, and then it gets you back, no, 4.
You get 4.
You get 4. And then you have to work on 4. And basically that's your work set that you perform. And the other way is, well, tell me the vector length. And then compute out of that vector length and your constraints with minimum, maximum, or whatever, a vector length you are actually going to use. And that set VL thing, so basically let the hardware decide, it's currently disabled for SLP because I think it's probably necessary because the hardware is stupid. Because with SLP, you basically have some vectors where you have 2 lanes or 3 or 4 per iteration. But you have others where you only have 2. So basically you have different vector lengths, and your masks, you wouldn't need to like duplicate the masks. So, I think the code is not there, and I'm also not sure if you say set vector length 6, if it gets me always back a multiple of 3, or if it can get me 2, and then I'm lost with my 3 SLP lanes. It's not in the spec, at least I can't figure out what a hardware is allowed to do, so I guess it's allowed to do anything, like return 1. Correct? Probably.
Yeah, this is just going to be ugly.
Yeah. Or like with the ZVL, you also specify the data size.
Type, and you get back how many hardware.
Like, so it could be that also with a regular loop, when you have like ints and shorts, that you would get 2 different vector lengths, which of course can't work because you can't unroll differently. So yeah, it doesn't work.
Yeah.
So it's kind of very limited, but it seems to be, looking at the scan assembly thing, a useful optimization for a very narrow set of loops. And that's currently broken for SLP, but I know how to quirk it into doing the right thing, I think. And I hope that slashes 1,000 of those, maybe.
Okay, I stand by my statement. I would rather you pull forward and leave that 2,500 to the RISC-V guys, and we'll figure that out. And if there's anything of significance, we'll contact you.
Yeah, so I've opened bug for analyzed things, so I keep track of that. And yeah, so for x86-64, it also looks a lot. There are also assembly test scan fails. There is a bunch of generic test fails with regard to the 6 size, and there's a 10 and 8 and 12, something like that. Yeah. You can do struct load 10, I think, with RISC-V.
Yeah, you probably can. It'll probably be really slow.
How many vector registers do you have? How many vector registers?
Varies. Minimum 32, I think.
Okay. Yeah, so there's work to do. It's basically what it says. So I want to repeat. Do I have time to repeat? Yes. Very short time. To repeat the main benefits. So only one way to implement a feature. It sounds great. No more this strange hybrid thing, which probably still doesn't work in all cases. No more doing this iteration, so try again without SLP, and maybe we didn't yet get to the point to cost the different things against each other. Maybe also get a better heuristics when to use those load lanes and store lane instructions and be able to mix them with regular SLP and handle that kind of better. But not for the initial transform. I want to do the same thing. So there are only also opportunities for the future. One major bad aspect of the vectorizer currently is how costing is done and how the costing is interfacing with the targets. And when you have SLP nodes, you basically have a graph and you have most vector instructions represented by a SLP node, and you don't have to second guess how the vectorizer now implements this division that your hardware can't implement, right? So you could take into account data flow.
That's exactly what's useful.
That's exactly what's useful, that's true. But it's, at the moment, it's not really possible to do that in a good way. So the opportunity is to redefine the interface of the costing to the target. Then there's the opportunity, as we have data flow, we can co-generate directly from the SLP representation. So currently we are copying the scalar loop and then replacing each scalar statement with the vector statement. And then we copy it again for the epilogue, and we are doing that again. So we don't have to copy the scalar loop. We can, in principle, directly generate the vector code. But it's quite low-hanging thing in theory, but the benefit is also not too big in the end, I guess. But yeah, it's a nice thing that you can do that. And when you're doing SLP, you can in principle very easily generate code for not vectorized parts. So you have the single lane SLP, and you say, well, your vector size is 1. Yes, therefore it has 1 lane. So you just duplicated the scalar code n times when you can't vectorize any of the statements. So Jakob said it's useful for OpenMP because OpenMP has a special pragma that can tell you you are not allowed to vectorize this statement, but all the rest, please. And you can also do the opposite of vectorization. You can basically, people tend to write unrolled code because they think, well, it's fast. But in some cases, if the programmer unrolled 8 times, but your vectors have only 4 lanes, you can re-roll the loop and only use 4 lanes. Or when you're optimizing for size, you can re-roll it completely up to a single lane. So basically, it should be more easy to support fractional vectorization factors. So now comes the scary slide, I think. I chose a different color for the scary slide. Timeline. So I really plan to transition to the only SLP mode, which means putting the hard fail in the check at the end of this stage 1. At the end of stage 1, because then we still have stage 3 to fix things. And yeah, it will fail vectorization when there's a statement that's not using SLP. Right? So we are accepting at that point the scan assembly fails, maybe some more fails. And I hope too that we and also the target maintainers, bold, we can analyze the regressions, fix the test cases, see, it's not important, we defer, or fix it.
Yeah, I mean, if they're going to follow the buckets, we know that.
Yeah, but at least go through them and see if there's anything we don't yet know, because that's the interesting part. And I showed regressions for ARM, RISC-V, and x86. There's also PowerPC. No CI for PowerPC, sorry. Then there's, of course, System Z, which also has some very few vector instructions, probably not many test cases, so maybe nothing fails. But it has a fixed vector size, so those ISAs are usually not very problematic. Right, then there's Itanium has some vector test. Then now we are getting to the Sparks and stuff, yeah. Rainer already filed some bugs that test cases are failing. So I'm not going to care about those. I hope the target maintainers will at least file a bug with an analysis, what goes wrong, and then we can, of course, work on it. Yeah. Well, there will be no, so I won't file the bugs for the failing test cases. So I know you're posting PowerPC and System Z to results to GCC regression, right? But and some of you guys then file bugs for test cases that continue to fail. So I hope they will file the bugs, even if it's just many vectorizer test fails after revision XYZ, right? We can split that bug up then. And but so if it's in a bad state, we can at the moment still easily roll back. We just disable the single lane discovery and be done, and remove the hard check, right? And then we get what we got before. And only in next stage 1 we should do things to remove code that's then no longer necessary. So that's the plan. Basically hard force the thing through, because it didn't work the other 2 times I tried. And 3 times the charm, something like that.
Still awesome.
Of course. Yeah, I think there's very few things that needs to be fixing. At least I know only very few things. I didn't look at all the assembly things. I looked at the generic fails and a few assembly scan fails. But most of the time I can't make sense of the SVE assembly or the RISC-V assembly. So.
It's our architecture, we can't do that.
Given the magnitude of the RISC-V failures, the fact that the vast majority are
given the magnitude of RISC-V failures and the fact that the vast majority are assembly check failures, that to me really falls on the RISC-V maintainers. I don't think that should be falling on you for this work. So, and I think that applies to the other architectures as well.
So, questions? I think we still have even 8 minutes left. And there's the vectorizer buff for which we need to switch rooms, unfortunately, so it's downstairs.
We are downstairs.
Upstairs? No, but as... Is it S? Then it's supposed to be S10, right? No, it's S5. Okay.
The big one.
Yeah, the big one. Okay. So, and in case you didn't notice, I spoiled the end of stage 1.
no excuses.
I wrote it on the web. Yeah. I also wrote the end of stage 3. Yeah, it's 2 months from now. It's around the same time as all the years before.
Yeah, it's easy for us to forget that. That's only 2 months away.
Yeah. But usually we tell you only 3 weeks before.
Suppose code is no longer exercise because you broke something else. What if code is no longer exercised because you broke something else?
No, it's because it's no longer necessary, right? It's basically all the duplication and the features that are just there because there are 2 data structures, right? It's probably going to be a little bit disappointing, the amount of code we can actually remove. So the more interesting thing is to do then the follow-up cleanup of the code that results when you just remove the branches and blocks of code. But of course, so I would expect that this should be done in one step, so the cleanup of the surrounding code and the removal, and not somebody just folding all always false branches in the source, because that will result in code that probably is harder to understand than if both branches are still there. So it's probably going to take some time to do the code cleanup.
Yeah,
right.
And it's always the case that when we do these code cleanups, we find things 6 months later.
Yeah,
And
of course.
That to me is fine and normal.
So one extra data point, so we are tracking like spec performance on x86 and also on ARM, but on hardware without SVE. And I always looked when I did big changes, and there is at least nothing obvious happening there, which is probably a good sign. But
at least not related to your shape.
At least not, but it's probably a sign that real-world code is really simple and only exercises the very simple code paths, and the test cases are, of course, exercising all the weird stuff, and the weird stuff may eventually regress a bit. So I really don't expect Power or Z to regress. I know Power will regress because probably nobody implemented the unaligned, optimized load thing for SLP. Yeah, I think these optimized load things are from times where the hardware didn't support unaligned loads, like the original Power 4, whatever, Altivec stuff. Yeah, so maybe it's time to retire that code path instead of implementing it for SLP. But it's surely impossible to implement it. I mean, so of course the easy way out to implement something for SLP is just to implement the single lane SLP case, because that should be exactly the same but with a different data structure. Implementing the full SLP support is sometimes harder, because for VLA vectors you have to now synthesize constants with more than one lane, so it's not no longer a single series but two, so you have to generate two and interleave them and use gather or something else. Yeah.
Might the single lane SLP eventually replace x86 backend's STV, scalar to vector passes? Or are they very different things?
That's an interesting question, but the x86 STV pass basically implements operations that are operating on the general purpose register set, on the vector register set, but in scalar form. Originally motivated, of course, by the fact that there are way more vector registers on x86 than general purpose registers, which will be no longer true after the new Intel thing. But yeah, and so basically it tries to remove the transitions between GPR and vector. I don't think that's really topic of vectorization, because no, I mean, on Gimple it's still a float, it's still an integer operation, and I don't have a way to say it should live in the vector set. I mean, I could assign it a vector with size 1, but I think we have had more problems with vector 1 lane modes than not. So it's, yeah.
It's going to regress somewhere. Something's going to blow up.
Yeah. But in principle, it's possible. But costing is, of course, I mean, I know the STV pass does quite, it really tries to estimate on the instruction level if it's profitable to perform the operation on the vector side, even including the possible moves that result. And that's, of course, quite impossible on Gimple. So I think STV is great. Maybe we should make it more generic and other targets could also benefit. But the costing is, of course, very x86 specific. And yeah, we are out of time. So let's move up to the both. Thank you.
Now it should be on. Try speaking to it.
Hello, test.
Yes.
Good.
Okay. The button on the top mutes it if you want to.
Okay, thank you. There was a GDB buff upstairs, so some people might be still coming. Maybe we should start. I don't know. Okay. So hello, I'm Barış. I usually go with my middle name. I'm from Intel. I'm here on behalf of the application debugger team. So the topic today is debugging Intel GPUs with GDB. Let's begin with the big problem first. Modern compute workload is diverse. So there are engineers, developers, they write applications in a wide range of domains like AI, graphics, fluid dynamics, economic modeling, etc. And they want their applications to be optimized to run faster, to be scalable, and to be power efficient. This requires that they need to target a variety of hardware coming from various vendors. And also they need to use a wide range of software, like libraries, tools, etc., so that they can achieve the performance that they want. Intel One API is an initiative that aims to provide the programmers with a unified model so that they can get towards this goal. So there are various toolkits in One API releases. So this is a big picture of the base toolkit. It contains compilers, some tools for API-based programming, and also analyzers. And with these, programmers can write applications that target CPUs, GPUs, or FPGAs. But today, what's important, what we will be focusing on is that they write programs, they compile it with a compiler that supports such a model, and then they execute their programs on GPUs. And then they will be able to debug it with the GDB. Let's begin with this programming model called SYCL. Sometimes this is, Intel sometimes names this as data parallel C++. This is an abstraction layer on top of C++ 17, and it supports data parallelism and heterogeneous programming. The idea here is that programmers can write code and then they can reuse it in order to offload their computation to various kinds of architectures, and not necessarily only Intel. It can be targeting hardware from other vendors as well. To give an example of how SYCL looks like, I will use a very simple application, vector addition. This is a toy sample, of course. It's an embarrassing the parallel program actually. So we have two arrays of inputs and we want to add the elements pairwise and obtain the output. So how would we write it if we were to do it sequentially? The most obvious approach is to write this for loop. But in this example, I deliberately abstracted out the body of the for loop. You see it on the right-hand side as this function called process. The mental model here is that there is this index I, and based on that index I, we are going to process our data. In this case, we read from input 1, read from input 2, and combine them in some meaningful way, and then write back to the output. If I were to execute this, what would happen is my thread would, a single-threaded sequential, so we would process the elements one by one sequentially. Here's how it would look like in SYCL. We would first create a queue. So this queue is basically a container where we'll be submitting jobs, and the SYCL runtime takes those jobs and it distributes them among the threads, and it handles scheduling. What we want is that we are now submitting a task to be run in parallel to this queue, and the task is specified by a lambda. The lambda takes I as the parameter, and that specifies the index of the element, of the data item that we would be processing. And what we do in the body is basically exactly the same. Okay, we are processing input and producing output. One way to, what we have inside the lambda here is usually called the kernel. Not to be confused with the Linux kernel, but it's the computation kernel. A possible execution scenario is that the SYCL runtime is going to split the data, which is usually very large, into chunks, and then it can assign each chunk to a thread. And when executed, one possible way is that the thread is going to take its assigned range and it's going to process it sequentially. Or in another model, the data could be vectorized, and now the threads are still assigned to a range of data, but what they can do is that by means of vectorization, they actually process the data also in parallel. And this is the SIMD model, single instruction, multiple data. And that's how basically GPUs work. Here is the build and execution flow. In the OpenMP and offloading session for GCC, we saw also a build and execution flow. This is pretty similar, I would say, at a high level. So we have our source code. This is I showed a simple example using SYCL, but it could be OpenMP as well. We also support OpenMP actually. The source code contains the computation kernel. We give it to the compiler. The compiler is going to compile the host part of the application, the part of the application that surrounds the kernel. in an ordinary way, actually. But then it also takes the kernel and compiles it to an intermediate representation called SPIR-V. If the programmer passed -G, it would also produce debug information, again in SPIR-V intermediate format. And this gives us a binary which contains the intermediate code embedded in it. This is sometimes called the FAT binary. And when this is launched, we get the host process. The host process runs, and at some point, it takes the embedded code, the intermediate code, and then it gives it to the device compiler. The device compiler, if we are targeting the CPU, the device compiler would be typically a JIT compiler for CPU. But in the case of GPUs, it would be the graphics compiler. And the device compiler produces a proper ELF together with the dwarf with it, and then this code is then submitted to the target hardware. So, coming back to the original topic, which was about debugging, the task of the debugger is now to debug actually this code and to map it all the way back to the original kernel. Here is the overall debug architecture. So there is GDB, and GDB can start the host application, or it can attach to it if it was already running, and it controls the host application through ptrace. So this is years old, pretty standard debug architecture here. For those who know GDB terminology, here the host application would be referred to as an inferior, actually inferior one, and it would be placed on top of a native target. What happens next is that the host application runs, it uses the SQL runtime or OpenMP runtime, and these runtimes have GPU backends. It would be the level 0 backend in our case. And the level through this backend, it would be, it would be preparing the submission of the workload. And then the debugger comes into the picture here, the actual GPU debugger. This is an instance of a GDB server. Now GDB server, well, we have written a target that's in GDB server that knows and understands the Intel GPU architecture. And it uses level 0 debug API, which is depicted here. And through that, it's able to control the GPU and interact with it for its debug events. And finally, this GDB server ZE is connected to GDB, and this actually means that now in GDB we have a second inferior which runs, which has underneath a remote target. This remote target is not the same as the native target that was for inferior 1, and GDB is able to orchestrate these actually different targets. That's the multi-target feature of GDB. Credits to Pedro. And we rely on that feature.
Is the cheating happening at step 3 or?
Is the cheating happening in this diagram or what?
Yes. So in the previous slides, I showed the build flow that was based on the JIT model. Here, JIT happens at step 3. Yeah, I mean inside the SQL runtime. Yes. But it's also possible to do ahead of time compilation where you can lower down the intermediate representation SPIR-V to the actual device code, and that actual device code would be embedded in the FAT binary. But the idea is actually the same. The runtime would then, instead of invoking the JIT compiler and lowering the intermediate representation to device code, it would immediately load the already compiled device code.
Which makes it simpler.
From our point of view, it's the same. I mean, from the debugger point of view, it doesn't matter. Yeah. The level 0 debug API contains a bunch of functions. You see, I mean, for execution of the of a GPU workload, there are many more functions, but for the debugging part, these are the functions that are defined in the API. They contain things like being able to attach to a device for debugging as a tracer, or detaching, reading and querying for a debug event. Some events require that they need to be acknowledged. There's a function for acknowledging. Debugger can interrupt a whole device or a subset of threads, or it can resume again a set of threads. It can be an individual thread, all the threads, or a subset. Read-write memory, or peek-poke, thread state, etc. So these are the functions that the debugger is built upon. We recently submitted a series of patches, actually, because we are interested in getting this upstream. What we submitted is a basic introduction to a debug capability. In the downstream debugger, there is a lot more, and we are interested in keeping the upstreaming efforts and maintaining this. For instance, what doesn't exist currently in the upstream version is SIMD lane awareness. So GDB doesn't know anything about SIMD lanes, and there's actually a BOF on the third day, on Monday, where this topic would be discussed. So this, in this talk, I would be focusing on this upstream version, not the downstream version. I will try to show you a demo as snapshots, as screenshots. But if anyone is interested in a live demo, I would be happy to give it during the break. So the code that we will be using is the vector addition that I showed at the beginning. Here's the main. We create a queue, and then I just print the queue. And then we create 3 buffers. These are malloced as unified shared memory, which means they would be available at the host and the device memory. With this unified shared memory, the user doesn't have to explicitly copy data to GPU memory. This is handled by the runtime. And then we initialize the input arrays, and finally do a parallel for. This is the process function, and the function is given here. What I will do is that I will insert a breakpoint inside this kernel, and then we will be stopping inside the GPU. So, starting from the beginning, what the user needs to do is first compile the code, and here I use -G-O0, and then we run the program in GDB. Next, we define a breakpoint at a level 0 API function, in this case ZE context create, and this is a function that we know is appropriate for our purposes because it's a function that would be invoked after the backend is initialized, but before the workload is actually offloaded. So it gives us a very nice moment to attach to GPU as a tracer, as a debugger. And next, we need, yeah. Question?
Who triggers that? You say that this is not the downstream GDB, right?
Correct.
Who does that T break? You didn't type it.
I do. I'm the user, I do. The user does it.
I don't see it. Okay.
Sorry?
Yeah, I was wondering what you typed somewhere T break Z.
Yes.
You did it as the end user.
Yes. So this is.
Okay, it's okay. As long as there is no magic, it's okay.
There is a magic too, but I will come to it. But in this version, in the upstream version, the user has to do it manually. And then the user needs to do more. They need to set target non-stop mode on so that both the native target and the remote target are going to operate in non-stop mode. This is necessary because the multi-target feature of GDB doesn't have yet support to handle all stop targets, and a remote target is by default all stop. And what this setting basically does is that GDB would operate having non-stop targets, but on top of that it implements the all stop behavior. And then we run, and then we hit the breakpoint. This breakpoint is well, we call it as the hook breakpoint because that's the moment where we are going to attach to the GPU. So at this moment, the GPU backend has been initialized, and we are ready to attach. And if we take a look at the overall debug architecture, this is what the state is like that. Okay? There's one inferior, the runtime and the level 0 backend have been initialized. So now what comes next? Now we need to add a new inferior, that's the second inferior, which will represent the GPU. We switch to that second inferior. And if we do an info inferiors at this point, we see that, okay, so the first inferior is there, it has the native target, the second inferior is null, it's empty. Next we do the connection. This is a remote connection, and what we connect to is a GDB server ZE instance, and it attaches to GPU for this given PID, and this PID process ID is the process ID of the host process. Another question?
Just a quick question. If you have multiple GPUs, are they all going to be under the same inferior, or is that one inferior per device?
If we have multiple
GPUs, like multiple physical PCI cards, you have one inferior each, or?
Each GPU is represented as a separate inferior.
Thanks.
The PID, the PID is the same. So there is one, okay, there will be multiple inferiors, but one GDB server ZE. The question is, if we have multiple GPUs on the system, how many inferiors do we have in GDB? The answer is, well, there would be one GDB server ZE, but that GDB server ZE connects to multiple GPUs, and from GDB server's point of view, it's as if like we have multiple processes on Linux. For instance, the Linux target for GDB server is able to handle multiple processes. That's the same idea. Each GPU is represented as if like a process inside a single GDB server ZE, and in GDB there would be multiple inferiors, but they would be using the same connection, the same GDB server ZE connection. Okay, let's continue. And after making this connection, we see something here that says unavailable. I will be talking about this a bit more in the upcoming slides. But what this basically means is that we don't have anything on GPU yet. I mean, GPU is not running anything. And then info inferiors, I mean, just for informative purposes, now info inferior says, okay, inferior 1 is the native process, and inferior 2 is a remote connection. Until we came to this point, there are multiple things that the user had to do, like define this temporary breakpoint, the hook breakpoint, start GDB server Z, connect to it, create the second inferior, etc. In the downstream compiler, we do all these boring things using a Python script. It relies on GDB's Python API, so the user doesn't need to do all these manual things. It happens automatically. Now, as the user, now we can define a breakpoint. Here I define it. This maps to a line inside the kernel. And actually, as a user, I could have defined the breakpoint right at the beginning. So I don't have to wait until this point. And in that case, the breakpoint would be defined as with a location mapped to the host, if there is a mapping, or it could have been defined as a pending breakpoint, but it would immediately get a location inside the GPU code as soon as the GPU kernel becomes available to the debugger. So the location would be resolved. And then schedule multiple mode of GDB needs to be turned on because there are multiple inferiors now, and it would be more convenient for the user to, when they say continue, it would be more convenient to resume all of them. And again, the auto-attach script, the Python script that I mentioned, does this behind the curtain. And then we resume and hit the breakpoint. The breakpoint hit comes from thread 2 dot something. Now that we have two inferiors, threads are enumerated with a prefix, and the prefix number here denotes the inferior that they belong to. So thread 1 dot whatever would belong to the host process, and thread 2 dot whatever belongs to the GPU. What works at this point for the upstream version is you can do backtrace, you can switch threads, you can resume them, you can resume all of them with continue, or you can resume only one of them using the scheduler locking mode. You can step them next or step into, etc. So these things work. What doesn't work is variable values would not print. We see an error. The reason is that these variable values depend on the SIMD lane because the data is vectorized, and the compiler says, okay, so the compiler says that the value of this variable depends on the current SIMD lane. And to be able to compute that, it uses a new dwarf operator, push lane, which is currently not recognized because it's new. I mean, it doesn't exist in dwarf 5. It's not recognized by GDB, and also GDB doesn't yet know about lanes, so it wouldn't be able to push the lane. Again, that's a topic of the BOF on Monday. There is already an upstream version of AMD debugger, and I believe there's the same problem there. Yeah. Another question?
By the way, can this setup work with like both AMD and Intel GPUs at the same time?
This debugger, no. This, yes. No. I mean, suppose these are merged into upstream. In the upstream, there's already some level of debug support for AMD, and then there would be some level of debug support for Intel as well, and then you would be able to do both. But both vendors have their downstream versions which do a lot more.
So they don't cooperate it.
The hope is that there will be a consensus and then things will be merged. That's my hope, at least.
We actually have speakers. Huh? I've heard that somewhere. Actually, I think it would work. Like, say, Inferior 1 was an AMD processor attached to an AMD GPU, and then you do add Inferior, and then that's a SQL process.
Mm-hmm.
Then you add a new Inferior and connect to GDB server. And I'm not, accept the lame stuff. Just the basics. I think it would. There's nothing that prevents GDB from having one Inferior attached to the GDB AMD side and another Inferior attached to the Intel side.
Yes, both of them. Okay, I see what you mean. Yeah, sure.
Yeah. There's nothing. There's no data structure or anything inside GDB that prevents you from at the same time debugging two different vendor cards. It's just that typically you don't have a machine like that.
I expect you might have a bit more difficulties having both runtimes on your process using both the GPU than you would have having GDB understand both, actually.
That's like one process, two runtimes.
Yes, one process, two runtimes.
Two separate processes, each one uses its own runtime.
Oh, yeah. Not as interesting. You could do that, but it's more fun if you have one process.
Problems once you want to support lanes until after Monday, maybe we'll come up with some solution.
Mm-hmm.
For instance, at the beginning of your talk, you said that SQL could be used to offload work to GPUs from other vendors, let's say AMD. I don't know if your library has your Z library has debug support for GPUs other than Intel, or it's just like other vendors could implement it if they wanted to, but it's not done today.
So the backend, the level 0 backend, is implemented for Intel GPU only at the moment. But it's an API, it's an abstraction. So if there were an implementation, in principle, it should work.
Right.
But in principle, yeah.
So the workflow would be SQL runtime would be would have two abstraction layers, and it would call into AMD one and into the Intel one to implement offloading to both GPUs.
Doesn't it exist today, like a SQL implementation for AMD?
I think it does.
So there is at least one.
There is at least one project which is called heap SQL that will export the SQL API and use heap, so which is like AMD's framework to access GPU under the hood. But I guess that comes with its own runtime, so I don't really know if that's going to work with the same runtime as Intel's. But I think we may be a bit derailing it a bit, and I'm sure Barish has a lot more stuff to talk us about. But we can come back to that later, I guess.
Yeah. I think I have sufficient time.
Yeah. Well, we have the last talk of the day, so we can run over. That's not an issue.
So heap SQL, yes, as far as I know, they can handle offloading to AMD GPUs, but the backend is not level 0. Yeah. Mm-hmm. So the level 0 backend, which implements the debug API, is really Intel GPU specific. Now, AMD GPU has, Intel GPUs from a debugger point of view have their own peculiarities. And I believe AMD GPU also has its own other interesting features. How to handle these two things using a single, if that was the question, I don't know. I thought that was the question. I don't know. I don't know how it would be. Yeah, in principle, I think it would be possible, but it would be a huge, huge effort, and also a very political one. I fear. Yeah.
Just for the record, I know someone who did that, and that like a proof of concept of one single program that offloads, I think, on different GPU vendors and FPGAs and CPU on the same process. So it's been done. I'm not sure there is anything anyone is pushing like that is production ready today.
I actually think it would just work. SQL would be sitting on, for the AMD side, SQL would be on top of HIP. So imagine you start with a ROC GDB, you're debugging that, you just see your GPU threads as waves, and then you would create a new inferior, and if the process happens to spawn GPU side on the Intel GPU, it would activate the level 0 backend, and then you would use GDB server to attach to that on a separate inferior, and I'm not seeing where's the conflict.
With different, I mean, by managing those, by managing to initialize those two separate targets being connected to two, I mean, corresponding debug APIs and libraries, they would be separate inferiors, and then I believe GDB would be able to orchestrate them.
So on the AMD side, we would not use GDB server. And
but it's a different, it's a different inferior, yeah.
Right.
Yeah.
At this point, it's an academic question.
Like at this point, it's like split code bases, so maybe we can ask the question again once they're all upstream or something. Until then, it's just hand waving.
But it's interesting to me that people think that it wouldn't work out of the box, but I actually think it would. If it doesn't work for some reason, I would like, really, why?
At least for the GDB sides, I think both AMD and Intel are both committing on wanting to have things that are going to be compatible and that's going to be working all well, well together. Like there is, I think we're both committed to put the work so we can have something that's going to be compatible all the way. For GDB, for the runtime, I have no idea.
Okay, going on. Now let's do info threads. There are two inferiors. There are two threads here, one dot something. They are the host threads. And then we see a long list of GPU threads prefixed by the inferior number 2. In my toy application, Vector Edition, I had a very small data and I was utilizing only a handful of threads. And there are thousands of threads in the GPU, so many of them appear as unavailable. What we do here is we model hardware threads. So right at the beginning, right after attaching to the GPU, GDB would show all these hardware threads. And this list stays stable. If there is nothing running, or if the thread is idle, then it would appear as unavailable, as shown here. But if it actually stopped at some breakpoint, then we would see its location. So basically unavailable means that GDB and the debugger, I mean actually GDB server ZE, tried to interrupt the thread, but it was not possible to interact with it. That's how the hardware works. We decided to model hardware threads in GDB for the following reason. One is that the device thread list stays stable. And we thought that this is nice for user experience, because applications that submit workload usually have short running but many kernels. So this would cause proliferation of threads. And if enter and exit events of threads were to be defined and received, then they would be really intrusive. When we model hardware threads, one question that comes into mind immediately is, so suppose I stopped at a thread, at a breakpoint, I do debugging, and then I resume the thread to hit the next breakpoint. Wouldn't it just go somewhere arbitrary? No, that's not the case for our hardware, because there is no context switch. Once a thread is assigned to run a kernel with a particular work item ID, it runs it until termination. For this reason, modeling the hardware thread on staying at a particular thread in the context doesn't cause problems as it would on a CPU, where hardware threads might be switching the context very frequently. And here are another question.
Just a quick question. So does that mean that here you have hit a breakpoint in process, or let's say you have a bigger application, you do continue and you hit another breakpoint, maybe in process or maybe in some other function. Do you have any way to know if that's still the same thread that was running, like the actual instance of a dispatch, or can that be just another wave coming in and just reusing the same spot and hitting either the same or another breakpoint?
So suppose we hit a breakpoint with a thread and then we resume it and it hits the breakpoint, let's say again, or another breakpoint. How do we know that it's still running inside the same kernel instance? Yes. With the same work item ID?
Or is that another one?
Yeah, it is possible. First of all, it's possible that the thread is going to finish its execution of the kernel, and then it will be assigned another work item ID. It will run the same kernel, but as a different thread, basically. Yeah, that's possible.
Like with a different ID in the grid, so that's like in the programming model, that's not the same thread. That's it doing the same work on different data.
Yeah. So you can check whether you are still in the same kernel instance. So in the downstream version, it's possible to print kernel instance IDs. So you can check that. That would be one way to do it. And for the same kernel instance ID, whether you would be getting another work item index, and that's something that you can check by comparing the value of the work item ID, which is also available. So these are in the downstream compiler, in the downstream debugger, these are available as convenience variables. In the upstream version, they don't exist yet.
Thanks.
Just to give some information about how the GPU, Intel GPU works, because this is different from hardware to hardware. Here is how the breakpoint dance is done in all stop mode. For a reminder, let's first check the CPU case. To insert a breakpoint, what the debugger does is that it makes a copy of the original instruction and then it writes the interrupt instruction in place of that original instruction. And then when the breakpoint is hit, it would stop all the threads in the process. And then when we want to resume, it writes the original instruction back, or maybe it had already written that right after stopping. It then makes the current thread execute that single instruction so that it would be stepping over the breakpoint, and then it writes the interrupt again, and then it resumes all the threads. On the right-hand side, we see this for an Intel GPU. There is no specific breakpoint instruction. Instead, in the instruction opcode, there is a bit, a dedicated bit, which would set it as a breakpoint. So that particular bit is set in the instruction opcode, which means the original instruction is still there, except for a difference of 1 bit. And when the breakpoint is hit, the debugger stops all the threads, well, all the available threads. Some of them may be unavailable, as I explained previously. And then when we are about to resume, the debugger doesn't need to do this copy, write, etc. Instead, in the control register of the thread, there is another dedicated bit which is called breakpoint suppress. The debugger sets that breakpoint suppress bit, and then it resumes all the threads. The breakpoint is still inserted, but because of the breakpoint suppress bit, the thread which was supposed to step over the breakpoint will not stop. It will actually do step over, and it will continue. Question?
And when is that breakpoint suppress bit cleared? Do you need to do a single step, then clear it, then?
Yes, the hardware clears it.
Okay, after one instruction.
One instance, yes. Another question?
So this is specific to Intel GPU.
Correct.
And other GPUs are working another way?
Yes. They're very different.
Could you actually exactly explain what having a suppress bit set when you have a particular bit in the instruction opcode for a breakpoint? What does it mean? What does the GPU in this case will do?
So there is an instruction. The instruction has its breakpoint bit set, so which means the thread would normally break, jump to the system routine. But the that individual thread, this is a register of the thread, has 1 bit which we can set to tell the thread when you see the next breakpoint bit, ignore it, and also clear the breakpoint suppress bit and continue. So it would just clear its breakpoint suppress and keep running.
That.
Here is a similar thing in non-stop mode. Again, on the left-hand side, this is for CPU. To insert a breakpoint, we again make a copy of the original instruction and write the interrupt instruction. And then to resume, the debugger writes the original instruction to a well-known area. And then this is separate from the code that's being executed. And then the thread's PC is modified so that it would point to that area, and then the thread is made to execute that single instruction this is called the display stepping mechanism. The idea is that in non-stop mode, the other threads could still be running, and they could still hit the breakpoint, so we cannot remove the breakpoint instruction. And then the PC is set again, and the thread is resumed. For the GPU, again, inserting a breakpoint means we set a particular bit in the instruction, and resuming means, again, we rely on the breakpoint suppress bit. So the flow is simpler here.
How's this working on upstream?
Good question. This was for downstream. In the upstream code, the thread would need to step over.
Like this?
Yes.
So you don't include support for the magic already in this kind of series?
There is no display stepping. What we do is, for resuming, we do breakpoint suppress.
I assume, like
already
in your downstream, you have some kind of target hook or GDB arch hook that says, I don't need to do anything special to step over this breakpoint.
Mm-hmm.
Don't you have something like that?
Yes, we have GDB arch code, which allows us to actually skip the single stepping, the step over one instruction phase, and direct the resume. In the downstream, there is still that phase which is redundant. Yeah.
Right. Yeah. I'm interested in that.
Okay.
Hook.
I'm just wondering, because you are always having a bit reserved for all the instruction, and is it not too costly to have these bits like always reserved for something?
I don't know. I don't know the answer. That's how it was designed, and apparently the hardware architects and the other people didn't think that it was an overhead that was significant enough. Yeah.
Okay, we'll see.
But I don't have more concrete answer. Yeah, sorry.
So in your example here, you're using universal shared memory, so USM. In GDB, can you access that piece of memory from both inferiors, or do you need to be selecting the one which actually, where the memory is actually allocated? Because even if both the host and the device can access this, it's only going to be, physically living in either the host or the GPU.
The memories are separate, and in GDB, because we have two inferiors, they also have different separate program spaces.
Yes, but even if you have two program spaces, they're independent, but you have here, like your input one, you get an address. If you read that, like if you do inferior one and you read the memory at that address, do you see the result? Like you could, from both inferiors, even though they're two address, like two distinct address spaces, they could still alias behind this in the same memory that's available to both the CPU side of your application and the GPU side of your application.
Okay, so suppose we stopped inside GPU.
Yes.
At a breakpoint, and then we want to access input one. It would go through the level 0 API and it would access the GPU memory. Suppose we switch to the host. That's your question.
Yes.
And then we want to print.
Try to print the value at the same address.
the same address, no, I don't think it would work.
It's not mapped to both sides?
Yes.
No, it is with USM, which is, you don't have to use USM with SQL, that's optional. But if you use USM, you can use the pointer on both sides. And
But for the, I mean, okay, so for the host, if I query input 1, it would give me a separate, another address, not the same address.
Although,
But you can know the address and just do a cast.
Yes, if I use the hard-coded address from inferior 1, I don't think it would be accessible.
A related question is, if it is accessible, so you use shared memory, USM is enabled or whatever, causes it to be mapped on both sides. You could imagine that there are situations where you hit issues with GDB's internal caches, which assume that you don't have such sharing. You know, there's a stack cache in GDB, there's a code cache. Maybe on the stack data cache, you could you inspect it from one end and it goes into the cache. Or I guess it's when you modify that there's a problem. You modify and it goes, maybe there's no problem, I don't know. I just suspect there's something wrong here.
I mean, how?
Inferior 2, you read, inferior 1, you modify, you go back to inferior 2, and you read again, and you might not see the modification.
So it's stuck in the cache.
I can repeat that on my, I don't know.
so I guess the case you want is you're on inferior 2, you read the memory, it shows it's all good. You go to inferior 1, you modify the same memory, all good. You come back to inferior 2 and you read again, and there are chances that you will hit GDB caches and you won't see the modification that's been done via inferior 1.
Okay, so what I believe would work, I might be wrong, but based on my information, what would happen is that, so suppose you access GP memory from inferior 2, and then you go into inferior 1, and then you access the memory through the input 1 variable again, which had the address of the CPU copy. What should happen there is that the runtime, that's how the runtime implements the unified shared memory. The page is locked. And when we try to access that page, it should trigger a single handler, and that signal handler copies the data from GPU back to CPU. So we should be able to access a copy, but the same data. And then if we go back to GPU,
That's runtime, that the user...
But this is...
User space signal, that's what you mean? Or is it like kernel level? So it's an interrupt, not...
It is okay, so it is passed to the user space. It is passed to the user space. And GDB can so GDB can actually receive, it would receive that signal, and GDB would have to send it back to the application so that the migration of the page would happen.
But it's all stopped at that point. You're just printing, so you're just accessing memory using
That's a correct,
PID.
yes, that's a good point, yes. So the signal then would not be delivered, it would be...
Yes.
Yeah.
This is, maybe in practice it's not a problem, but maybe it is at some real bizarre or difficult to reproduce problem. It's a consequence of having two inferiors when you have one address space. And there's a workaround that I've seen being used in ports that did something similar enough, which is just to disable caching. There's a command for that. So it would be another command to put in your Python code.
Okay.
I don't recall, it's main set cache off or something. Code cache and stack cache off.
Okay. Another question?
Kind of an unrelated question, but are SIMD lanes in the downstream GDB, are the SIMD lanes supported from the Python scripts point of view?
No, they are built in GDB.
So if I wanted to like run a Python script that would like query the state of the SIMD lanes, it won't. I won't be able to do anything.
We didn't make lanes available through the Python API. That availability doesn't exist. So this is a screenshot of the downstream debugger, just to give you an example. So that's the last slide. Thank you for your patience. So we define a breakpoint and then we run. What happens is that we go and hit the breakpoint. So all this stuff about creating the second inferior, connecting it, etc., is done by the Python script. And this line here, which says Intel GT, GDB server Z started, etc., that's what the auto-attach script prints here for information purposes. And then there's support for SIMD lanes. Here it says we switch to SIMD lane 0. Threads are printed together with their active lanes, and then variables are printed properly because there's awareness of lanes and there's support for that push lane dwarf operator. There are some extensions and new comments to improve user experience. Like for instance, there's this stopped flag with which you can filter out unavailable threads and you get a more concise, shorter thread list. But in real applications, I guess, all the threads would be utilized. I mean, why do people pay for GPUs? But you would still get thousands of threads. There's another question.
So in the previous screenshot, the one that's upstream, each thread had a certain number of lanes in it, just we cannot see them and trick with them. And
correct.
Now we would see the same number of threads, assuming you would show them all, but we can see the lanes.
Yes,
okay.
Correct. This is the same application, yes.
The design choice of you look at the GPU threads as the fixed number of those threads. This means that when you attach, you always see the number of threads you see is always the same. It's always the number of hardware compute units you have, right?
Yes, the number of available hardware threads, it's always the same.
Always the same. So doesn't this mean that you can only ever have one process being debugged in the system at one time? Like it cannot have one SQL process only using half of the resources of the GPU and debugging that, and then another user on the same machine or another process is using some other compute resources at the same time. It cannot debug that at the same time because...
Correct. There is this mode called run alone. If one user is using the GPU for debug purposes, another user won't be able to. I mean, they can submit, but the submitted workload would have to wait until this debug session finishes.
Right.
So they cannot. Another GPU can be used, but the same GPU cannot be shared between two processes.
That is like, I'm looking at this and thinking, the design choice you've made constrains you here.
Okay, this is a constraint coming from the hardware, not top down. It's bottom up.
Current hardware. If this ever changes, then you'd have to change your design. So are you like saying that this will never be supported?
No, we are not saying that.
Because I know from the experience on other hardware that there was that constraint and then there wasn't.
Yes, there is work, but I cannot say when. I mean, in how much time this would be available. But yes, there is work. What would happen in that case is that the two users would still see, like they would see half of the threads would be available, but they can filter them out using the flex. That's the idea.
Or you could do how the AMD guys do, which is basically there's a logical thread ID. It's not the physical core number. So if your process spawns a number of kernels using a number of waves, your kernel spawns enough HIP threads to consume 4 waves. You just see 4 waves when you're debugging. And a different process at the same time can be spawning 10 kernels, each consuming 10 waves. And when debugging that, you'd see 100 waves. And because there's this logical mapping between thread ID and...
What happens when, I mean, I don't know, and I'm curious. What happens when the same process runs another kernel? Do the thread list get updated?
Yes, you'll see more waves.
Yes. In our opinion, I think Simon has a comment, but doesn't this cause too much threads appearing and disappearing?
We disable the notification. When GDB detects a new thread upstream, it always prints, by default it prints new thread appear or new thread disappear.
No, but if I put kernel 1, kernel 2, I have a breakpoint here in the common path, I have a breakpoint here in the common path.
Yeah, I'm sorry, you lost me. Can you say it?
So, suppose all the threads hit a breakpoint in my kernel 1, so wouldn't I see thousands of threads?
You would, yes.
And then I resume, I delete the breakpoint, I resume, and then thousands of threads hit the second breakpoint in the second kernel. Do I see a new set of thousands of threads?
Yes.
That's what we thought would be proliferation of threads.
Right. It's the exact same thing you see on the CPU side, of course, in a bigger scale. But it's just it's a different kernel, it's a different invocation for this dispatch. So logically, it's a different thread.
Okay, so I mean, I will make a claim, but I
see what you're saying.
On the CPU side, I would think that applications don't create and start and kill threads so often. Instead, they would create a pool of threads and that they would assign tasks to them, so that even from the software thread point of view, the number usually stays stable. I would think so.
It's a question of, is that so important compared to then having this concept of unavailable threads and this issue with debugging multiple processes at the same time? These problems only appear because of this design choice. That's what I'm saying, right? On the AMD side, we just weighed, and that was not enough of a problem, the number thing. Different design choices, but I'm just suggesting that this design choice may cause problems in the future, eventually, when you will need to support multiple debugging at the same time. So.
To be seen.
Sorry.
Yeah, I guess those are related. You had a slide where you said we didn't choose to model logical threads because there would be too much notifications or things like that, like thread creation or some. You can come back to, I don't know. Yeah, would cause proliferation, and somehow with the AMD port we don't see that. I was wondering why. But when threads get created, and like when they are created and exit and nothing happened, GDB doesn't report them. So even if thousands of waves get created and exit,
yeah,
it's not like it prints a flood of notifications.
Yes, it
So
can
it's
be.
only if that scenario of the numbers keep incrementing very quickly only happens if, say, you have a breakpoint that triggers on all the kernels, and then you resume execution, then a bunch of new kernels are spawned, and they also hit a breakpoint.
Mm-hmm.
Because if there's no breakpoint hit for a while, and new kernels are constantly being spawned and they die, those new threads come and go, and GDB doesn't see them, so no number is incremented.
Yeah,
So
I
in
mean,
practice, it really doesn't happen that much.
yeah, we thought in practice it would matter. I guess it's yeah.
Fight.
Thank you. Is it muted? I don't know.
It's muted, yeah.
I think it's now fine. Thank you.